Okay, Madhu.
Yes, sir.
So, a very good morning to all of you. This is Sahadat Sarkar. So, it's my great pleasure and honor to welcome you all in the inaugural session of Pune National E-Symposium on Cloud and Precipitation Processes, which is jointly organized by India Meteorological Society, Pune chapter, Savitribai Phule, Pune University, and Indian Institute of Tropical Meteorology. Although due to COVID-19 pandemic, we are unable to meet physically, but we have tried our level best to gather many experts virtually. Thank you all the participants for your tremendous response. And we have received more than 150 abstracts for our workshop. Thank you all for that. Now I request all the dignitaries to come on the virtual dais. Our chief guest of today's function, Professor Nitin Karmalkar, Vice Chancellor, Savitribai Phule, Pune University. He will be joining with us shortly. Our guest of honor, Professor Ravi Shankar Nanjundaya, an eminent meteorologist and director of IITM. Our special guest, Professor P. Pradeep Kumar of Savitribai Phule, Pune University. Along with them, we have Chairman IMSP and Senior Scientist of IITM, Dr. C. Ganesilan. Also, we have Secretary IMSP, Dr. Madhu Chandra Reddy. So I welcome you all, sir, in the virtual dais. Thank you, sir, for being with us today. Now I request all the dignitaries to switch on the camera for a group photo. Padmakar, you can take a group photo of all of us. Now to begin this auspicious occasion, we will now have Saraswati Bandhana by Ms. Lata Sridhar, Sulekha Sonal and Sonika. Now I would like to call Ms. Lata Madam and her team for reciting the same. Lata Madam, please.
Saraswati, Saraswati, Sharade, Ma Sharade, Sharade, Ma Sharade, Surya Brahma Shiva, Vishnu Gadane, Jin Charanon ko sevate, Surya Brahma Shiva, Vishnu Gadane, Jin Charanon ko हमने जाने जननी पूजन वंदन ज्ञान को मूरत हम नहीं जाने जननी पूजन वंदन ज्ञान को आदि शक्ति करिश्मा हमें आदि शक्ति करिश्मा हमें पूजा की उद्गार दे वीरा माई तार दे तार दे तार दे माँ सरस्वती शारदे माँ सरस्वती शारदे सरस्वती सरस्वती शारदे माँ शारदे शारदे माँ शारदे श्वेत हंस तेरा सिर है श्वेत हंस तेरा वाहन है श्वेत कमल तेरा सिर है श्वेत हंस तेरा वाहन है हम पर सिद्ध दृष्टि कर जननी बोध चीरती दार दे वीणा माई तार दे तार दे तार दे माँ सरस्वती शारदे माँ सरस्वती शारदे पूर्ण इस अज्ञान उदधि से पूर्ण इस अज्ञान उदधि से वीणा माई तार दे तार दे तार दे माँ सरस्वती शारदे माँ सरस्वती शारदे माँ सरस्वती शारदे
Thank you, madam.
Thank you. Thanks for joining from Nagpur.
Welcome.
So now I kindly request Chairman IMSP and Senior Scientist of IITM, Dr. C. Ganesilan, to address the gathering and also brief about the workshop. Over to you, sir.
Thank you, sir. A very good morning to all of you. Hope you all are safe. I would like to welcome Professor Karmatkar, Vice Chancellor Savitribai, Pune University, and today's chief guest. Professor Devi Nanjundaya, Director IITM and guest of honor of today's function. Professor Pradeep Kumar, who is our special guest today, Secretary MoES, senior colleagues of IMSP and IMS, senior scientist of IITM and other MoES institutes, Dr. Krishnan, Dr. Sahai, Professor Anand Karipot, Dr. Kulkarni, Mr. Jamadar, Mr. Madhu, the invited speakers, session chairs and judges, my dear colleagues of IITM, IMD, NCMRWF and all the members of IMSP and IMS, and the dear participants of the National E-Symposium. It gives me immense pleasure in welcoming you all for the E-Symposium. We just had the annual Monsoon E-Workshop yesterday with presentations from the forecasters, brainstorming sessions and discussions. I'm sure all of you have benefited from it. This year we have E-Symposium on cloud and precipitation processes in addition to the annual Monsoon E-Workshop to honor Professor Pradeep Kumar, who retired recently as Senior Professor and Head of the Department from Savitribai, Phule, Pune University. IMSP has been organizing the annual Monsoon Workshop for several years and is one of the platforms to discuss the success and failure stories of monsoon prediction. Such discussions are important as they help in improving the forecast. In this context, the annual monsoon workshop is an important activity for monsoon and climate scientists. In spite of making all the arrangements, we could not conduct the workshop last year due to the pandemic. It also forced us to go for the online mode this year. It is important that I record my appreciation for the enthusiasm shown by our young participants, even though it is virtual presentation. In fact, we have received more than 150 high quality abstracts, that too when too many back-to-back conferences and workshops were happening. We are thankful to all the others for their dedicated efforts. We all are looking forward for their excellent presentations today and tomorrow. We are fortunate to have some eminent invited speakers as well, who I am sure will enlighten us with their thoughts on the different topics. We would have loved to see you all in Pune. Hope we will have the next year's program in Pune. I know the limitations of virtual conference, but request all of you to kindly overcome those and get maximum benefit. The IMSP Executive Council and the tech team have been working day and night to have a very successful E-Symposium. I'm sure they will help you in all aspects. Wish you a wonderful E-Symposium ahead. Take care and stay safe. Thank you.
Thank you, sir, for your address and briefing about the workshop. We are very fortunate that today we have Professor Ravi Shankar Nanjundaya, an eminent meteorologist and director of IITM, as the guest of honor of our event. Now, a brief introduction of today's guest of honor, Professor Ravi Shankar Nanjundaya. He is currently the director of Indian Institute of Tropical Meteorology, Pune. Before joining IITM, he was chairman of the Center of Atmospheric and Oceanic Science at the Indian Institute of Science, Bengaluru. Professor Ravi worked on thesis entitled Study on Intraseasonal Variation of the Tropical Convergence Zones in a Simple Monsoon Model, and obtained his PhD in Atmospheric Science from IISc in 1992. He did his ME from IISc in 1986. He obtained his BE degree from Rani Durgavati University, Jabalpur in 1984. Study of monsoon and its variability using climate models, application of high performance computing or grid computing for climate and weather related studies, and use of machine learning techniques for monsoon prediction and downscaling are his key areas of interest. He has worked extensively on various aspects of Indian summer monsoon. He is a fellow of Indian Academy of Science, Bengaluru, fellow of Indian Meteorological Society, adjunct professor of TIFR. He received the NVIDIA Innovation Award in 2013. He was adjunct faculty ICTS TIFR from 2011 to 2014. He is the associate editor, Journal of Earth System Sciences from 2008 to 2014, which is published jointly by Indian Academy of Science and Springer. He has also received Sir C.V. Raman Young Scientist Award in the year 2000 in the field of earth sciences. Professor Ravi started his research career as a postdoctoral fellow at the Mathematics and Computer Science Division of Argonne National Laboratory, USA. He worked there in the CHAM, that is the Computer Hardware, Advanced Mathematics and Model Physics for Studying Global Changes project during February 1993 to February 1995. Then in July 1995, he came back to India and joined the Center for Atmospheric and Oceanic Sciences at IISc Bengaluru as an assistant professor. At Center for Atmospheric and Oceanic Sciences, he became associate professor in July 2001, professor in July 2007, and the chairman of the center in December 2013. Professor Ravi has been active in human resource development and so far has guided 15 PhD students, 4 MSc, and 9 MTech students. He has 90 plus peer-reviewed publications in national and international journals and has presented at many conferences. With this brief introduction, now I would like to call upon our guest of honor, Professor Ravi Shankar Nanjundaya, to kindly release the book on cloud seeding, authored by retired scientist of IITM, Dr. J.R. Kulkarni, which will follow his address. Over to you, sir.
Thank you, Sadat. It's a privilege to be here in this symposium. Okay, just sorry, it's a clarification. Should we release the book first, or shall you like me to address first?
Yes, sir, you can release the book because according to the program, you can release the book.
Release the book. Okay, fine. So I think we will first release the book. It's a pleasure to release the excellent book written by Dr. Kulkarni. He's done a comprehensive job of it. And it's a pleasure. It is an honor. I mean, it's an honor for me to release this book.
Thank you, sir. Sir, he is standing here.
Yeah, I can see him, but I'm trying to stand and yeah.
Great, sir.
Yes.
Thanks a lot, sir.
Padmakar, please take a photo of this one.
पद्माकर एक फोटो लीजिए.
Okay, sir. Thank you, sir.
Thank you.
Thank you.
Now, sir can freely he can talk now.
Yeah.
Yeah, I mean, it was a pleasure releasing that book, and I'm sure everybody will learn a lot about weather modification and cloud seeding reading this book, and I strongly recommend that all of you read this book and get a lot of knowledge which Dr. Kulkarni has gained over quite a few decades of his research work. And I would like to thank him for writing this book. I kind of glanced through an early release version of it he gave me a few months back. It's an excellently written book. Thank you, Dr. Kulkarni, for this job.
Thank you. Thank you, sir. Thanks a lot.
Okay, so I'll now move on to my address. Honorable Vice Chancellor, Professor Nitin Karmarkar ji, Professor Pradeep Kumar,
Yes.
Dr. Gyanshilan, all the dignitaries on the dais, ladies and gentlemen. It's a privilege to be present on this National E-Symposium, which is also the annual Monsoon workshop of IMS Pune. And this year, it's a special symposium on cloud and precipitation processes. As Dr. Shail mentioned yesterday, we had a fairly intense discussion on the predictions for 2020 and the way forward. It was a whole day seminar or symposium, you could say. And it was a pleasure to listen to all the new work that's being done in the field of prediction and how well we are doing the predictions. Today, the focus is on cloud and precipitation processes. And it's a privilege to be part of this symposium, which is in honor of Professor Pradeep Kumar. Professor Pradeep Kumar's contribution to the study of clouds and precipitation processes is immense. He was perhaps the first person to set up a cloud chamber in this country and do innovative studies on cloud-related processes. He also has done a lot of work, and single-handedly he has made the Department of Atmospheric Science of SPPU into a center of high academic learning and research, and one of the best in the country. I would like to thank him for his immense contributions that he has done and also for his long association with IITM, which has enriched the research in our institute. Today's symposium is very interesting and has lectures by top experts in the country. The advantage of having an E-Symposium, of course, there are many disadvantages, but the advantage is you can get the best experts from all over the country or all over the world, and they can give their ideas and we can have discussions with them. That's the advantage of having an E-Symposium. And as Dr. Sheelan said, there are about 150 abstracts which were received, and of course, many invited and contributed lectures. I look forward to an interesting and exciting symposium, and I wish you the very best. Dhanyawad, Jai Hind.
Thank you, sir, for your address. I congratulate Dr. J.R. Kulkarni for his book. So the title of the book and the E-Symposium has close connection. And for the benefit of the participant, I would like to request Ms. Smita to provide a brief about the book on cloud seeding released today. Ms. Smita, please.
Thank you, Mr. Sahadat. The book Cloud Seeding for Precipitation Enhancement, Science and Guidelines for Operational Programs details research in cloud seedings across the world. Cloud seedings in research and operational mode are being carried out in different parts of the world since its discovery in 1947. India is no exception to it. After many years of research and operational programs in India, many questions remained in the minds of people and administrators. This book tries to clear these doubts among people. This book contains scientific basis of cloud seeding and history of the subject. The position statements by the world scientific bodies, namely WMO, AMS, WMA, the American Society of Civil Engineers, about efficacy of cloud seeding are given for enhancing confidence of the program in the minds of people not involved in the subject. First phase of KIPEX program was conducted during 2009 to 2011 with objectives of understanding the cloud aerosol interaction and to prepare guidelines for the operational program. The achievements of the KIPEX are discussed in the book. The guidelines for the operational cloud seeding programs are given in the book for the state governments. The same has been followed in subsequent phases of KIPEX programs and in state cloud seeding programs. The main question arises in the minds of people about estimating percentage of enhancement in rainfall due to seeding. The methodology to estimate this has been discussed to arrive at benefit to cost ratio. The benefit to cost ratio estimated in different cloud seeding programs in the world are discussed. Using the guidelines, Karnataka cloud seeding program was carried out. The benefit to cost ratio of the Karnataka experiment was estimated using methodology given in the book. Different methods used in operational cloud seeding methods, namely rockets, UAV, and ground-based yagna are presented in the book. List of papers published in KIPEX program and in cloud seeding field will be useful to students and researchers. Thank you so much. Over to you, Mr.
Thank you. Thank you, madam, for providing a brief about the book. Now I would like to request Dr. J.R. Kulkarni, the author of the book, to say a few words about the book. Kulkarni, sir, please.
Thank you. I express my sincere thanks to Director IITM, Professor Ravi Nanjundaya, and IMSP for releasing this book on the occasion of this symposium, one-day symposium on the cloud physics. This book is written to explain many things about the cloud seeding and its operational work. The subject of cloud seeding is not covered in the regular academic courses of the universities, nor in the training institutes of the IMD. So there are many contrasting ideas, beliefs about this subject in the mind of, even in the minds of meteorologists, researchers, administrators who are doing the cloud seeding programs, state cloud seeding programs. They have little knowledge about this subject. So this book will help them to get the detailed idea of the program, how to conduct it, what type of permissions are required, what are the addresses, what are the people to whom they can contact. I have given in the book. Also given the protocols to be followed by the persons involved in the cloud seeding, like what pilots should do, what radar meteorologists should do, and what the meteorologists should do, and also the sequence of activities. Cloud seeding is very difficult. Operationally, it is difficult because it involves many components, many ministries, and you have to get the permissions from many departments, and these permissions are in sequential in nature. So if somebody wants to do the cloud seeding, what type of activity they should start and when. So timeline of the activities is given, and at the end, after cloud seeding is done, the question remains in the minds of people, what is the enhancement because of the cloud seeding? So that part has to be estimated, because this is an operational program, not the research program, and there may be rainfall due to natural process, and there may be rainfall because of seeding. So how to separate the rainfall because of seeding from the natural rainfall? So methodology is given, and with that we can estimate the enhancement in rainfall, additional water generated because of the seeding, and what is the benefit to the farmers, to the people in the area. Also, I have given the position statement by world scientific bodies like the World Meteorological Organization, WMO, WMI, Weather Modification Association, then the AMS and ACE. That will increase the confidence of the program in conducting the program and remove the doubts among the people about the efficacy of seeding. I think this book will be useful to researchers, students, and to the media, and to the common people and administrator. The book is written in that form. So many references are given, history of the cloud seeding is also given. And with that, this is a very expanding subject. About 100 countries in the world, they are conducting the cloud seeding every year. And there is large scope for Indian institutions, people to do a work or add more knowledge in the subject and make it program indigenously. So all the methods, technologies are given that in few years this can be done indigenously. Now the programs are conducted by hiring agencies from outside, but we have the capacity, we have developed the capacities, and we can do this program indigenously in our India. And not only that, we can help other countries to do the program efficiently and economically. With this, I end my brief introduction to the book. I hope everybody will like the book. Thank you very much, sir.
Thank you. Thank you. You want water?
Thank you very much, sir, for your brief about the book. I am sure that this book will be very useful for the research community and the students. So they will be benefited from this book, that how the cloud seeding can affect different rain processes. So now it is our privilege to have with us Professor Nitin Karmalkar, Vice Chancellor, Savitribai Phule Pune University, as the chief guest of today's function. Now I request Ms. Smita to provide a brief introduction about him. Smita, please.
Thank you, Mr. Sahadat. Professor Nitin Raghunath Karmalkar is Vice Chancellor, Savitribai Phule, Pune University. He is a well-known scientist in the field of igneous petrology. With more than 25 years of teaching and more than 30 research publications in various national and international journals, he is actively involved in academics and research, along with constantly guiding various facets of academia, being a part of Board of Studies and Research and Recognition Committee for Geology and Environmental Science. Over the years, he has shouldered various administrative duties of Pune University. Dr. Karmalkar has worked with various research collaborators from Australia, France, and Germany. Under his guidance, more than 20 students have completed their MSc dissertations and 4 students have completed their PhDs. He is actively involved in mentoring students for Earth Science Olympiad. He is Council Member, Geological Society of India, Bengaluru, and Fellow of Maharashtra Academy of Sciences, India. And in 2005, Dr. Karmalkar is a recipient of Professor C. Naganna Gold Medal of the Meteorological Society of India towards his contributions in the field of alkaline magmatism of the Kutch region. I, on behalf of IMSP, thank the Honorable VC for his time. Thank you.
So thank you, Smita madam. Now I'd like to call upon Ms. Aditi Deshpande from Savitribai Phule Pune University to start the function from there. Aditi, please.
Thank you, Sahadat. I hope I am visible and audible to everyone.
Yeah, you're audible.
Okay. So I welcome all of you to the felicitation function of Professor P. Pradeep Kumar. Let me begin by saying a few words about Pradeep Kumar sir, although for this audience, I'm sure he doesn't really require any introduction. Professor Pradeep Kumar's career at the university started with the then newly launched UGC-sponsored MTech Atmospheric Physics course at the Department of Physics in June 1988. Since that time, he has single-handedly managed the administration and developmental work implementing the teaching program of MTech Atmospheric Physics, then later Atmospheric Science. In 1997, he took over as the coordinator of the MTech program. As he was the only faculty in the program, he initiated a memorandum of understanding with Indian Institute of Tropical Meteorology to run the MTech teaching program jointly. Additionally, his work on cloud physics has given him international recognition, and in 2004 he was elected as member of the International Commissions on Clouds and Precipitation and served 2 terms from 2004 to 2012. He also worked as member of the expert team on education and training at OPAC 5 of Commission for Climatology of the World Meteorological Organization from 2014 to 2018. At national level, he has served as a member of Program Advisory and Monitoring Committee in the Department of Science and Technology for the Himalayan Glaciology Program from 2002 to 2007, member of PAMC in Ministry of Earth Sciences Program from 2012 to 2016, and currently from 2020 to 2023. He has also served as expert to Government of Andhra Pradesh for 2005 and 2006 cloud seeding operations. And since 2009, he is member of National Steering Committee for the KIPEX program of the Ministry of Earth Sciences carried out by IITM for research on enhancement of precipitation through cloud seeding. Savitribai Phule, Pune University has also recognized his efforts for teaching and research and awarded him with late Principal V.K. Zog Award in 2015. For 30 years, he has been a pillar of strength and support for the department. The atmospheric science program of the university, through his constant dedicated efforts, has made a mark on the international level with its alumni working as top scientists in several international organizations as well as national organizations, which includes IITM, IMD, CDAC, and several other government organizations. Additionally, his research has also been monumental with his cold room research, which was the first of its kind, and to project the achievements of the department, for which he has immensely worked and tirelessly worked for. His farewell gift to the department was to organize the National Space Science Symposium, the 20th National Space Science Symposium, in January 2019, along with AYUCA and NCRA, for which the Savitribai Phule Pune University, the department faculty, and the students have received a lot of appreciation from ISRO. Professor Pradeep Kumar continues to be with us as Emeritus Professor in the best interest of the department and contributes to the teaching and research activities. PPK sir, as he is fondly known by his faculty and all of his students, has been a guiding light for everyone, including the students as well as the junior faculty. And words definitely do not do any justice to the contributions and the tremendous visionary that he has been for the department. So I will now request Professor Pradeep Kumar to say a few words today.
Yeah, good morning, everybody. It's a pleasure and surprise for me to be here for this function. At this, looking back, it has been a long journey of nearly more than 30 years. And when you look back and see that where your students have reached, at various organizations, and some of them are heading various at various departments, not only in India and abroad, you feel the satisfaction that as a teacher and as a researcher, you have accomplished something. Because when I started here, cloud physics, the laboratory research on cloud physics was not at all popular in India. Even now it is, in the world, very few places used to do that kind of a work, because hardly very few groups used to carry out laboratory experiments in cloud room, in the cold room research. Cold room research was hardly 2 or 3 labs in the world. And then we could set up a lab here in Pune University, which was under the funding from the United States Army, which was the first project to be funded in India by the US Army. And we set up the laboratory, and 5 students have successfully completed their PhD working inside the cold room. In this last, we started in 1994. So after that, we had the major contributions into the KIPEX program when we made the ice nuclei measurements over India for the first time, over entirely from starting from the base of Himalayas to all the way till the southern India. The aircrafts which IITM was flying, we could carry out, we could bring in the samples collected from those aircrafts, and we could come up with the number of ice nuclei which is present in the atmosphere during the monsoon season. That was the first time we have reported the measurements from India. So I wish that the conference which is going on in this clouds and precipitation processes good success. Thank you.
Thank you a lot. Thanks a lot, sir. Dhanyawad.
I will now request Dr. C. Gyanshilan to felicitate our chief guest, Honorable Professor Nitin Karmalkar. Thank you, Dr. Gyanshilan. I will also request Dr. Gyanshilan to please present Tarikumar sir with a shawl. The reason why we all are here today, I will request Professor Nitin Karmalkar sir to unveil the souvenir which has been prepared by IMSP and present it to Pradeep Kumar sir.
Aditi, camera can be focused to there. Camera is showing the wall.
Okay. Is it? I hope it is visible to everyone.
No, only you are appearing here.
I am.
Camera should be focused towards other side.
Yeah, the camera is on that.
No,
I see you only.
Now is the souvenir visible?
It's visible.
Okay.
Visible.
Let me try one more thing. Nice. How is it now? I'm just coming closer. Is it visible now?
Yeah, it's visible.
No, it's now. Yeah. Okay, let me try one more thing because it was interfering. Wait. 1 second, sorry. Give me 1 minute. Let us try this one more time. Okay, so now is everyone? Yeah, they should be visible. Yeah. Can someone confirm if it is the souvenir is seen?
Yeah, it's visible.
Okay.
Yeah, it's visible.
Okay, thank you everyone for being here. I will, before we finish, I would like to request our chief guest, Honorable VC Professor Nitin Karmalkar sir, to say a few words.
Yeah. Hello, good morning to every one of you. Indeed, it's a pleasure to welcome you all for this felicitation function of our dearmost Professor Pradeep Kumar. In the introduction, in fact, the contribution he has made to the subject and to the department is already been highlighted. And as rightly been pointed out, words are basically, I would say, very less to speak about his contribution to the department. I've been very happy that I have seen the progress very closely as been a student of this particular university. And when the atmospheric physics began in the physics department as a small unit, in fact, I was just completing my PhD. And since then, I'm closely associated with both the physics department as well as the atmospheric science department. Although the subject is also close and near to me because being a student of geology, I'm on the lithosphere and he's in the atmosphere, speaking about various different basically aspects of atmosphere, especially the cloud formation and various different aspects of it, along with the IITM and the IMD, who are closely associated with the University of Pune. The conference that actually was organized in 2019, in the month of January, under the auspices of ISRO, then IUCA, Pune University, was one of the best conference I could witness happening on the campus of the university for last, say, more than 3 to 4 decades time. And he was mentioning about that he had joined similar conference way back when he was a student, and it was his dream that having this kind of conference on the campus, and that to a great extent he fulfilled, wherein the contributions were coming from different parts of India. The atmospheric physics, a small sort of unit, later on grew into a larger department with a dedicated faculty and now dedicated space also, with dedicated facilities been created, especially the cold room facility. And the students, the alumni of this department are seen virtually working in different parts of India as well as in the other parts of the world. I have seen many of them, in fact, are presently doing a pioneering research in similar areas at the international sort of a forum. And this is what basically is a significant contribution perhaps Pradeep Kumar has ever made. The research and contribution, although has been recognized through a small sort of activity that has been the award of the Principal Joke Award, which to an extent is given to the people who contribute immensely in research as well as in teaching. But apart from that, the most important recognition obviously is the student that he has produced and who to an extent are contributing immensely at the international platform as such. So keeping all these things, in fact, this particular felicitation was due a long time before, but because of the COVID pandemic, we all know, we all been passing through, it got delayed considerably. But I'm happy that in the beginning of this year, in the month of January, we are holding this particular felicitation program in recognition of his basically work that he has done to the department, to this area of atmospheric science, as well as contribution that has been made to the Savitribai Phule Pune University. So in the recognition of that, we all together have gathered, although this should have been a bigger function in a physical mode, but because of basically the protocol that we have to follow during the pandemic situation, in a small gathering we are making it, and it's happening in my own office at the Savitribai Phule Pune University. So once again, I wish a very grand success for the conference that has been organized, as well as basically the department which is doing wonderful work Now the baton is in passed to Karipot, who has been ably handling this particular department. And now we all are probably, you must be aware that we are converting the department into school system. So Karipot is basically leading the School of Earth and Atmospheric Science under his leadership. In fact, 4 other departments, that is the Earth Science Department, Atmospheric, then the Geography, and obviously the remote sensing and other areas to a great extent are doing their work. So I wish a grand success, and the school system perhaps would bring in better collaboration and wider visibility to every one of us working in up till now in silos, and they will come together and basically further take ahead the atmospheric science as well as the earth science. With these, once again, I thank every one of you for joining this particular, I would say, online function, and I wish a very happy onward journey to Mr. Pradeep Kumar, who has been closely associated in the capacity of Emeritus Professor and presently also contributing significantly both in the area of research and teaching. Thank you so very much.
Thank you, Professor Karmalkar. So I will now hand over the charge to IITM again for the remainder of the session. Over to you, Sahadat.
Thank you, Aditi. Finally, I would like to call Dr. Madhuchandra Reddy, Secretary IMSP, to give vote of thanks. Over to you, sir.
Thank you, Sahadat. Very good morning to all of you. First of all, we are very thankful to Honorable Vice Chancellor of Savitribai Phule University, Professor Nitin Kalmarkar sir, for agreeing and felicitating our special guest Pradeep Kumar sir, Professor Pradeep Kumar sir. Thanks to also Professor Pradeep Kumar sir, and our today's guest of honor, Professor Ravi S. Nanjundaya sir. Thank you very much, sir, our beloved director of IITM, so for giving all the facilities and encouragement to conduct and every facility provided for this smooth conduct of this online E-Symposium of cloud physics and precipitation, cloud and precipitation processes. Thank you, sir. And we would like to thank Jilani, sir, the head of the computer division, for providing the support for the online and web, and Shampa madam, the library head. She has given the library side all the facilities. Thanks to both of them. And we also thanks to all the various committees of committees under IMSP, both science, organization, local organizing committee, and technical teams. We are especially thankful to all of them, their support. And we are thankful to ex-chairman JRK sir for his gracious presence today. And we are thankful to Sahai sir and Jamada sir, who is the national committee members. For time to time, they are guiding us and helping us in various ways and various capacities. And we are thankful to Savitribai Phule University Department of Atmospheric Science, earlier head Pradeep Kumar sir and present head Anand Karipot sir, and also the director of Anand Karipot sir. Now, yes, congratulations for the director of Earth Science School of Earth Science things for his directorship. Hope we will have a very good collaborations with Anand sir. And now we would like to thank IMSP Chairman Dr. Jnanasilan sir and his team for all the support for last 1 month, conducting from the abstract review to till today's function. All the things, they are the main persons behind it. The IMSP, each and every member, honorable members of IMSP, thanks for your presence and participation in these things, and all the participants, oral, postal, every participant, we are thankful. And finally, I would like to thank 2 important persons. By their help, this is going to be a seamless online presentation. One is from IT session, the Padmakar, And we are also thankful to Tulasi Ram, the web designing for the, you can see our poster session there. So he has nicely designed. And thanks to these both of things. And thanks one and all who are helped directly, indirectly for these things. Now I move to, immediately I move to the session, clouds and its characteristics. The chairman, Dr. A.K. Kamra sir, is the eminent personality in the cloud electricity and cloud physics, and he will be the co-chair. And sir, with you, Professor Anand Kumar Karipad sir will join after 15 minutes. So you can start the session 1 on clouds and its characteristics. Thank you, sir. Hand over to Dr. A.K. Kamra sir, chairman, for the session 1.
Come here.
Yes, sir. Please come. Yeah, come.
You have to upload my.
Okay.
Hello.
Yes, sir, you are audible. Please start the session.
Am I visible?
Yes, sir, you are visible also.
Oh, thank you. Welcome, good morning, and welcome to all the participants in this session. Session first on clouds and its characteristics. The field of cloud physics has made quite important contributions, and for the last few years in India. Reason being mainly because of recognition of role of aerosols and clouds, not only in modifying the cloud characteristics, but climate also. So mainly these progresses have been made possible by the enhancement of infrastructure in India, instrument-wise. And because of this large body of data we have collected in various programs like CAIPEX and from which has now shifted to mostly shifted to Sholapur experiment region, and this development of HAPCL laboratory at Mahabaleshwar, very heavily instrumented and with the radars capable of penetrating to clouds and collecting the data on microphysical properties. And also this addition of lightning location network at the IITM, this has been one part which has contributed quite a lot and interested many participants, not only in for cloud physics, but also in climate physics. And another reason has been the development of various techniques for simulation of cloud properties, like cold chamber. Just now we heard from Dr. Pradeep Kumar, and he has wind tunnels and some theoretical models developed, simulation models. So by these developments, this field has grown up quite a bit on national and international scales. So with this background, it is appropriate for us to take account of what has happened in India recently, and some very good aspects of this has been that a lot of scientists, not only on a research level, but at the students have been taking interest and doing some very fine work in cloud physics. So I think this kind of work, a symposium will greatly help in interacting with each other, and we really look forward to very active participation of all the participants in this, especially during the discussion section. It will be our endeavor to increase the interaction, not in different lectures. So to start with the first session, first we have some very interesting invited talks, 4 invited talks and a special lecture of 20 minutes each, and then one oral presentation session about a dozen contributions from different scientists and students of 10 minutes each. So what I will, because time will be very short and we do not want to exceed the total time limit, I will request that the invited talks be limited to 20 minutes, and just leave 3-4 minutes, 3 to 5 minutes for discussion to be held after the lecture presentation. And in oral session, 10 minutes duration, and last 2 minutes will be devoted to some one or 2 or 3 short questions. Just we try to make them short, so that they can be, maximum of them can be accommodated. So at the end of 6 minutes in oral presentations, some warning will be given, alert will be given by our reporter, and at 8 minutes I will request that presentation should be stopped, and 2 minutes should be left for this. Another request is that after the presentation, I will request all the participants to switch off the audio button, to unmute them, so that other arrangements can be made. So with that, my co-chairman will join me shortly. Is busy in some university function that you have just watched, so he will join me. So until he joins, we'll begin this session with the first talk of by Dr. J.R. Kulkarni on cloud seeding. Dr. J.R. Kulkarni. Dr. J.R. Kulkarni.
Thank you, Dr. Samra. And I will stick to your time schedule. And after 15 minutes, you give me bell. 5 minutes for the question and answer. The topic of my talk is rain shadow and area harboring grey ocean cloud.
After 15 minutes, I will give you a signal.
Okay. So this work is done collaboration with Padma Kumari, Mahesh Kumar, Hari, and Dr. Morwal. And this work has been published in the Atmospheric Research Journal 2016. Begin with chamber set up by Professor. Not audible?
Yes.
Please, please.
JFK sir को allow करो. ठीक है.
Madhu is,
Can you come to here once, please?
Madhu is helping.
Okay, okay.
Madhu,
Mr. Mute है बोलो.
I am getting the echo. Sorry for inconvenience. It was not okay.
Yeah.
Hello. Hello. Now, am I audible?
Yeah, you are audible.
Okay, okay. So, I start my talk by wishing Professor Pradeep Kumar good health and best wishes for his future endeavors. In CAIPEX 2009-2011 program, we collected ice nuclear samples on filters. Dr. Mahesh Kumar took all these samples which were analyzed in the cloud chamber set up by Professor Pradeep Kumar in Space Physics Laboratory, Pune University. And those were first observations of ice nuclei over Indian region, and that resulted into many publications. On behalf of CAIPEX team and from my personal behalf, I express sincere thanks for collaborating in CAIPEX program. Thanks, Professor Pradeep Kumar. One of the references I am giving here, deposition ice nuclei observations over Indian region during the CAIPEX. I have many memories of Pradeep Kumar. In one sentence I will tell, I have the longest association with Pradeep Kumar. As I remember, in 1987, when we were discussing about the timetable of the semester, myself, Asnani, Anand Krishnan, Ramkrishnan and Srinivasan, we were talking, and Agashi came and introduced Pradeep Kumar to all of us. That was the first meeting with Pradeep Kumar. Then I had been there up to 2005 as a visiting faculty in the department. Now coming to the subject. Regarding book I had spoken, I will not spend time on this one, but this book will be useful for students, researchers, administrators, farmers, stakeholders, media and press persons. Now coming to the topic of my talk. So WM has classified the clouds and published the international atlas. So the classification is based on height, base of height, top structure of the cloud, like horizontal spread or vertical development, based on the convective cloud, stratiform cloud, stratocumulus, altostratus, altocumulus, cirrus, like that. Another way of classification of cloud is based on the microphysics. In the WMO cloud atlas, no microphysics was considered. But the another way of classification of clouds is based on the microphysics. So this has been done by Andrei 2004. So the classification is like that: blue ocean clouds. These clouds occur over oceans, have low cloud condensation nuclear concentration and low CDNC. These clouds develop precipitation very efficiently because of the availability of giant salt particles as condensation nuclei. The second is the green ocean, the clouds which developed over forest land in western Amazonia in unpolluted conditions. These are oceanic type. So clouds which are developed over forest land, but they are of oceanic type, having low CCN and CDNC and are efficient in producing the precipitation. The third type is smoky clouds. These develop over smoke areas caused by fires and have high CCN and CDNC. The cloud droplet size is small and hence unable to grow by collision coalescence process. And fourth type is a pyro type. So pyro, these develop due to direct feeding with smoke, heat produced from the biomass fires. Similar to smoky clouds, these have high CCN concentration, CDNC and smaller drop size spectrum which inhibit the precipitation. So the question addressed is what type of category, what is the category of monsoon clouds over rain shadow region of peninsular India as per the criterion based on the microphysics suggested by NGA. So for this we collected the cloud microphysics data in the KIPES program conducted during the period 2009-2011 using an instrumented research aircraft over the peninsular India of the rain shadow region. The aircraft flights were conducted from base station Hyderabad and data were collected from the cloud profiles conducted 50 to 80 nautical miles away in the southeast and southwest of the base station, and these are utilized to characterize the clouds prevailing over the study region. So aircraft instrument, we have used cloud droplet probe, CDP, and then the passive cavity aerosol spectrometer probe, that is PCAPS. CCN concentration were measured by supersaturation cycles 0.2 to 0.8 by CCN counter. So this is the CCN counter. Then the liquid water content, cloud liquid water content was measured by JW Hotwire LW sensor Williams, which was capable of measuring in the range 0.01 to 3 grams per meter cube, and the vertical velocity from the aircraft integrated meteorological measurement system, that is the EMS probe. Here are the pictures of the instrument, that is this is road mount thermometer, this is EMS probe, King hot wire measuring instrument, this is PCAPS instrument, this is CDP, SIP, and then the CCN counter and isokinetic inlet. These give the tracks of the flights conducted from the Hyderabad in different months: June, August, September, October 2009 and 2010. So the flight data considered in 2009 monsoon season are of 22nd June, 14 and 16 August. In the 2010, withdrawal of monsoon occurred on October 20th. The flight data considered in this year are of September 12, 14, 19, 20. We had 2 flights, 21, 25, and October 2nd, 3rd, 11, 13, 15, 19. So during the period, the radio Sunday flights were conducted simultaneously with the aircraft operation from the base station. Bowen ratio is indicating of type of the surface on which convective clouds are generated due to thermals. Latent and sensible heat fluxes are obtained from NCEP reanalysis daily data to compute the BR to understand the behavior of surface of the study. These are results of our analysis. These are the cloud vertical motions, that is updrafts and downdrafts. This shows the cloud vertical motion in the different days. And here shows the timeline, time series of the vertical motion, and the blue line shows the height of the aircraft. So these are the descending types of flights. First, the samples were correct at the top of cloud and the aircraft descend down. So these are the descending type of cloud, and last is the ascending type of the flight. So in all cases, if you see the vertical, the updrafts are of the order of few meters, 2 to 3 meters, and downdraft also of that order. So these are the order of updrafts and downdrafts over the study region, which are low in magnitude, about 2 to 3 meters. This shows the liquid water content over the region for different days in 2009 and 2010. You can see the amount of liquid water content is 3 to 4 grams, and this is the adiabatic liquid water content. So the low liquid water content concentrated in the lower levels and extending up to the height of 5 kilometers. This is the CDNC, cloud drop number concentration. So this number concentration is around 200 to 300 per centimeter cube on different days, extending up to 300 to 400 for some days. So it is a low concentration, and this is the parameterization for the concentration CDNC in terms of the velocity. Then the cloud efficiency, that is very important thing. What is the cloud efficiency? It is estimated using the formula as the maximum liquid water content in the cloud and mass of water vapor entering from the base, and based on that we estimate the cloud efficiency, and cloud efficiency is in the range of from 10 to 20, minimum is 6 and maximum is 21. So cloud efficiency is very low during that period. Then the effective radii. The effective radii on different days with height has been shown in this figure for different days. It is effective radii is important parameter in coalescence and collision process and the growing of the cloud drop to raindrop processes. So the effective radii is more than the critical value of 12 microns in all the cases. You can see it is extending up to 16 micrometer. Then this is the BR ratio is also very low, about 0.9 to 7. Sometimes it is going to 11. So the Bowen ratio is very small in that condition. Now the relationship between CDNC and aerosol concentration. This shows the relationship between, this is the aerosol concentration and cloud drop nuclear CDNC. The relationship is non-linear, and the relation between the two, that is CDNC to aerosol concentration, is given by this equation where X is the aerosol concentration. Now in terms of the vertical velocity, liquid water content, and the effective radii, the clouds have properties like that oceanic condition, but the relationship between CDNC and aerosol concentration, it shows the continental type of clouds. So the congested clouds over the rain shadow region in monsoon season have characteristic values of CDNC vertical velocity closely similar to those observed over the ocean. The frequency of cloud updrafts was more than frequency of downdrafts, and intensities were similar to that observed over the oceanic region. BR values indicate that surface of study behaves like the ocean. So it is similar to ocean type of clouds. The surface also behaves like the ocean because in the monsoon season, lot of moisture, a lot of precipitation, and surface is wet and behaves like the ocean. But the sounding characteristics also shows that of a oceanic type closely associated to moist adiabatic type of thing. The clouds have effective radii above the threshold value of warm rain initiation. Therefore, the collision collation process seems to be active in these clouds. However, the rainfall is low over this area due to low cloud efficiency. So, cloud efficiency is very low. Over the ocean, efficient collision collation process occur due to the presence of giant and ultra-giant solid nuclei. Clouds over the rain shadow region are either advected from the Arabian Sea or formed in situ. So there is absence of natural giant nuclei. During the long travel from the Arabian to the study area, the salt particles are scavenged out due to heavy rain over the Western Ghats region, and there are no hygroscopic giant particle sources over the land. Therefore, even though these clouds have oceanic characteristics, they have low efficiency. That we have seen the efficiency is very low in converting cloud droplets into raindrops. So, the nonlinear relationship between aerosol concentration and CDNC is indicative of continental air mass. So, cloud parameters CDNC W, that is vertical velocity or updrafts, exhibit a similar property as that of oceanic clouds, but existing over a gray land. BR values indicate oceanic type of surface. Therefore, in furtherance of cloud classification by Andrea, we categorize these clouds as gray ocean clouds. So these are ocean clouds, but over the gray land, as the oceanic type clouds are formed over the gray ocean. Importance of study: the cloud seeding programs, they aim to enhance the precipitation by increasing cloud efficiency. So the purpose is to increase the cloud efficiency. Addition of giant hygroscopic particle is considered to enhance the efficiency of clouds. Hence, as these clouds have low efficiency, these clouds are considered as the best possible candidates for seeding to enhance the rainfall. The study provides scientific basis for carrying out the cloud seeding programs for peninsular India rain shadow region. So we have named these clouds and found that these clouds over the rain shadow area are oceanic type, but over the land region they have the mixed characteristics of oceanic clouds and the continental clouds. So we have coined them as the gray ocean clouds. With this, I end my presentation. Thank you.
Oh, thank you, Dr. J.R. Kulkarni. You have set up a good precedence of finishing your talk exactly in 15 minutes. Thank you for that. To start with the questions and answers, I just wanted to have a very general question. In India, different states feel shortage of rainfall in almost every year in some states, and decisions taken by those states are taken when monsoon is almost halfway or more than that, like that one shortage. And under those conditions, seeding conditions are maybe very poor to keep the clouds. So, do you have any suggestion for such decisions to be taken?
Thank you, Dr. Kamra sir. It is a very good question. So, people, they start thinking of cloud seeding when there is a low rainfall or half the season is already over. But in my book, I have given the guidelines to start working on the cloud seeding from the month of January itself. So IMD forecast is available in month of April. So you get some idea whether the monsoon will be good or monsoon will be very strong or very weak. Based on that, have a preliminary preparation right from the April onwards, have the tenders invited and keep everything ready by month of at the end of the month of May. Now June gives some indication. We have done some research and published some papers how June rainfall is connected with the rest of the monsoon season. So we get some idea based on the rainfall in month of June. Again, in month of June, we get revised IMD forecast. So you get some idea about how the monsoon will be developing within the coming 3-4 months. Also, we know by that time whether the El Nino, La Nina conditions are developing or mature and other things. So we get very good idea in the month of June. And if you are prepared from the hello, if we are prepared from the month of April onwards, we can start the program right in the month of July when the monsoon is in the peak and when the more conducive atmosphere is there for doing the cloud seeding. July and August, they contribute about 70% of the rainfall of the monsoon season. So we can catch those opportunities in month of July and August if we are prepared from the month of January itself. So when we wake up in the month of July, then half the season is over and preparation itself takes 1 month time, and most of the season is lost by August. So very few opportunities are exist. So in my book, I have given how to start in. If you have to start the program, be ready from month of January itself.
Yeah. No, thank you very much. And secondly, I just wanted to know from you that in such emergency situations, people generally switch over to ground seeding. This ground seeding, does it, in your opinion, what does it contribute or can contribute at all?
This is another very good question, sir. Ground seeding is attempted in many places because it is cheap also. But the principle and science behind this cloud seeding is to enhance the efficiency of cloud by seeding some material in the abrupt regions of the cloud. Now, in the monsoon, there are strong winds. At the lower level, we have the jet at S50, and our cloud basis in rain shadow region is about 2 kilometers and high. When we do some material spread in from the ground, it is very unlikely that it will reach in the desired regions of the absorbed regions of the cloud. It has to go in the absorbed region, not anywhere in the cloud. So ground seeding has many problems, and the material will be transported to other areas, and it may not reach to the particular areas of the clouds and will have the efficiency or turn the cloud into rain. So this is not a very viable solution, though it is a cheap, but not very useful. So in my book, I have discussed about the limitations of the ground-based seeding.
Thank you very much. And any question from audience or this?
Yes, may I ask one question, sir?
Yeah, sure. Go ahead.
Yeah, sir. Thank you very much, sir. JRK sir, for his green, blue, and smoky and pyro type of clouds. And you talked about the cloud efficiency, where the water vapor is converting into the cloud liquid water content. So, how much water vapor is usually converted into cloud liquid? So, in a percentages, can you tell? One question. And the second question is that in the natural cloud seeding is happening in the monsoon time. So, can you put some light on that? Like, means ice cloud process from the spraying of ice particles snows which come into the warm clouds and seeds and it gives a rain. It is a natural cloud seeding process. On these two aspects, can you deliberate a little bit? Thank you, sir.
Thank you, Madhu. The first question is cloud efficiency. So these clouds, they are low efficient rain-making system. So cloud efficiency, even if you take the thunderstorm, big thunderstorm, the cloud efficiency is not more than 20 to 30%. So all the moisture which is going from the base of the cloud is not converted into the rainwater because there is a lot of mixings. Clouds are in the dry air, and dry air from the boundary it is mixing, and that mixing is very, very forcible because winds are very strong. So all the water, all the moisture which is entering from the cloud base is not converted. So we have calculated the efficiency given the formula, and it is varying from 6% to about 21-22% over the rain shadow area. In other area, this percentage may go to 30%, but not more than that. So that is the main thing and main problem. So we have to extract more and more water, and we have to convert. That is the basic scientific premises for cloud seeding. We have to convert more amount of cloud moisture into the liquid form and get the rain. This is the answer to the first question. Second question, yes, there is a natural cloud shedding when ice particles are there on the top of cloud, and they fall into the cloud, and they get the ice nuclear processes and convert into the liquid water into the ice phase. So it happens, but it requires a special condition. We have to have ice clouds above this convective cloud. And so this is a natural process, and many times it happens also. Okay.
Thank you, sir.
Any other question? If there is no further question, thank you, Dr. Kulkarni, for a very informative talk.
Thank you, sir.
And we move to the second presentation by Dr. Tara Prabhakaran. She has been very busy for the last 4 years in conducting some cloud measurements, and this thing, let us know what she has to tell us.
Thank you very much, sir. And may I share my presentation?
Yeah, sure. Good.
One second.
I talk with you more after this. So Naina will take care of that presentation. Yeah.
Fine.
Is it visible now?
Yes, yes.
Okay.
It is visible. You can go ahead.
Yes, sir. Thank you. And I just want to thank the IMSP and the organizers of this conference. And also, I want to recognize and pay my respect to Kamra sir and director and all others who are there, including Pradeep sir. Actually, I'm indeed presenting this talk on behalf of several students of PPK sir. We call him PPK sir. So I met him in 1988, I think, as a MSc student at the university. And since then, I have been a student with him, and I am still learning. And I just want to say that I am also sharing some of the committee memberships with him. And as well as KIPEX has got a steering committee, and he has been immensely supportive, and he actually also involved in our experiment. I want to thank him for everything, and my presentation today, it is dedicated to him. Just 1 second. I think I have a problem with the. Okay. So let me proceed. This is indeed, I want to tell you that this particular topic I have selected because we are making, I think from the KIPEX science point of view, we are making some significant progress to understand the mixed phase clouds, as well as especially focusing on the secondary ice production in the cloud. So which is in a very nascent stage, even when you consider the world situation. Actually, we need to understand it much better. There is a big scope with the KIPEX observations with that. So I just want to show you some background. This is actually the structure of the cloud from Kanyi et al. To 2017. He talks about the liquid phase, the mixed phase, as well as the ice phase in the cloud. So when we talk about the ice phase, there are these primary ice formation where water drops can freeze at very low temperatures below -38. And ice formation also happens in the mixed phase where water and liquid can coexist, and we have heterogeneous freezing as well as secondary ice production there. Heterogeneous freezing is with the aid of an aerosol particle, which is it could be a water drop, or it could be an aerosol particle as illustrated here. So I'm not going into details of that. Then my focus today will be on the secondary ice production, which needs presence of an ice particle. So the ice nuclei, which Pradeep sir will be talking about today, I think so. So I will focus on the secondary ice production, which is happening after the primary ice nucleation. Somehow it is not moving. Okay. Yeah. Well, how important is this? See, where there are a number of studies. This the left one is from the observations using a Calypso observations, CloudSat observations, I think. So they talk about the phase fraction of raining clouds, which are raining from the ice phase, liquid phase, or the mixed phase. So our region, all three are quite important, especially over the continental regions. You can see that the ice phases are quite dominant. And this on the right, you can see a paper by Hazra et al. Published in 2016. They indeed show the freezing cloud ice, and these are the rates. And from MERA data, they show this, and the snow accretion as well. So these are the determining factors which are indeed bringing us more rain and are also radiatively very important for our region. So how it becomes important when you talk about the pristine ice, actually it forms at different temperatures. So this red line here, this is called the habit diagram. The red line here, it is the water saturation. So as the difference between the ice and the water saturation depends, you can see that there are different types of ice particles formed at very cooler temperatures. At warmer temperatures, for example, for us, this up to -20 is quite important. Even -22 is quite important. And we are measuring in our KIPEX observations are mostly concentrated in this region where we have the mixed phase. Okay, so the point here is that the ice crystals, what we find in the observations, they are much more higher than the ice nuclei particles that we are measuring. So we have also noted this in our observations. So one of the very early findings from the MoES 1976, they did a laboratory study where they are showing the secondary ice production rate or the crystal production rate using lab experiment at different temperatures. You can see the minus these temperatures between -3 and -8, where there is a very big peak here. And then this was further modified by Hansfield and Willis. So for the marine tropical convection, where they also found that. And then in our KIPIX observations, we have indeed documented the vertical structure of the presence of ice in the cloud. And we have seen that there are many different types of particles present. See, these are the gropal, and there are liquid particles present. Ice and the water are coexisting in these are from some of our early observations. So another important point here is that we have a large amount of supercooled liquid present in our cloud. Even in the monsoon clouds, we can see that there are a large amount of supercooled liquid that is actually present. This is the vertical structure of the cloud, and these supercooled liquid have the potential.
Yeah, this was broken somewhere. We can't hear you.
Sarah madam, could you connect back again, please? Sadar, just call madam.
Audio connection is not working. Audio is not working. Both audio and video.
Padmakar, what happened?
Your connection was gone.
We can move to the next presentation now then.
No, sir. She's just in the beginning slides. I think she may come back.
Okay.
So let us see another 1 minute or so.
So madam got some problem in her laptop. So she will be joining soon.
Shall we wait?
Yeah, she will be joining in 2 minutes.
Okay. Or whether she want to do it after Pandit sir.
See, her laptop restarted, so it will take time. So we can move to the next one.
Okay.
We can. Should we wait for her? Or
yeah.
After this.
Shall we ask Pandit sir? Can you join, sir?
Yes, I can join.
Yeah.
I think Madam
yes,
also
I
joined.
She is ready.
He's ready. Okay.
Yeah.
Yeah, sorry about the disconnect. Somehow laptop got restarted. So I will continue from here. Just
Yes, sir. Please. Thank you, Pandit sir. She is joining back. Thank you.
Good morning, Dr. Karipat. Good.
Good morning, sir.
So sorry about the disconnect, and I'm back. I was talking about the immense amount of supercooled liquid water that is present in our clouds, which has been observed by KIPEX observations, and this is a comparison of liquid water content in the monsoon cloud with various other observations in tropical as well as mid-latitude convection. So you can see that there is these are quite large. And so now with that background, I want to introduce this paper that we have co-authored. Actually, I am presenting this particular paper in the honor of Professor PPK sir, where there are several of his students, and students are also involved in this paper. So let me go into this. This paper basically it is talking about what is the role of the warm cloud on the ice phase processes or the mixed phase processes. So the point here is that what you see here is the relationship between the warm layer depth, which is the cloud base, the difference between the freezing level and the cloud base height, and the effective radius. As the warm layer depth increases, we can see that the effective radius of the drops are also increasing. Actually, this is an indication for the formation of raindrops, as you see. So this is a condition that would favor secondary ice production in the cloud in the freezing zone. So now again, there is also one another condition that large drops should be present, and then the rhyming process also will become active. So that we can see that this is this is the relationship between the large drops that are of size more than 400 micrometers and the ice water content in the cloud. So that also shows a linear relationship. We have seen that. And then there is also, we can also identify the hydrometeors type, that is by looking at their aspect ratios. This is the aspect ratio. This one will be 0 and the round one will be 1. So as you see, this is a joint probability distribution between the size of the particle as well as the area ratio. So you can see in the pre-monsoon, this is the pre-monsoon polluted clouds, the size is quite small, even the ice particle size is quite small, but there is a wide variety of particles present. And in the polluted monsoon clouds, they start growing at a certain region where we can see the gropal is there, and then there are some ice particles growing. These are actually indications for the Hallett-Mossop processes. And in the clean monsoon clouds, we can see a lot of ice processes happening, and which is actually harboring a lot of ice. So we collected all that we could learn from the observations, and we did also some numerical simulations using larger D simulation model. And illustrated that what are the characteristics of the polluted monsoon and the polluted pre-monsoon clouds. Actually, the basic difference, initially what you can see is the cloud base heights are different, and that makes a big difference for the particles to grow also. So the warm layer depth makes a big difference. So the cloud particles are growing bigger, and they are indeed, as they cross the freezing level, this is they cross the freezing level, they become they actually they harbor the active Hallett-Mossop processes here. But in the pre-monsoon cloud, droplets are too small, but they don't make such an active Hallett-Mossop process. So that active Hallett-Mossop process we have documented. How we have documented is that these processes actually they contribute to significant rhyming here, and you can see the groups of these columns here and needles here, and also the Groppel particle, and then there is this ice, there is this snow falling which melt into precipitation. So this is a close look at those ice particles. So the secondary ice production in the cloud, actually it is happening through various processes. Now the fracture of ice crystals is one mechanism, then the splintering on freezing droplets, splintering and freezing, then rhymed splinters like the Hallett-Mossop process I just mentioned, and then collisions of ice particles, shattering of ice particles, sublimation, fragmentation, and secondary splinter ejection. And actually these processes are one after another, it is coming up. So we need to identify which processes are active in our clouds and which processes are really contributing to a big difference. So one of the recent study which published in 2018, actually they talk about a secondary ice formation by bubble bursting events. See, this is a drop. It is bursting bubbles one after another, and then it forms an ice, numerous ice particles. And I can show you one. I don't know whether I'll be able to. Initial actually there are certain videos which are indeed showing a particle comes and hits, and then it is indeed forming the drop is freezing, and then breaking up of a drop also you can see, which is by these are all laboratory simulations, and then this is indeed an idea for the ejection of that particle bubble bursting, and then this is another way of ejection of the particle. So in our KIPIX 2019, we have also documented the liquid water content in the clouds, and we have observed clouds up to 8 kilometers or even 8.5 kilometers. You see, these are all the observations conducted over a period of 4 months during the monsoon, and we can see the cloud bases change according to how moist our conditions are. And then the liquid water content, you can see that it is actually, there are a couple of many cases where liquid water content is quite large. And I show you some examples of such bubble bursting type event, where although we are not able to see very clearly the small particles because the instrument is not able to register them. Some of the typical signatures I can show you here. They are indeed showing some features. These are the images of the particles that are indeed resembling those bubble bursting events. So this is a new finding. This has not been observed earlier in our whole of KIPIX, and this is actually happening outside of the HM zone, HM temperature region. This is happening at minus 14 degrees C. Yes, sir. Yes, sir.
Yeah, 15 minutes or 5 minutes we give you for this tool. So please try to wind up.
Yes, sir. Yes, sir. I'm winding up. And then if we look at the cloud particle properties also, we can see large size particles present there, which is also indeed an indication that this is not indeed produced by the HM process. So we want to indeed add different types of processes that may be contributing. Raindrop fragmentation, we have some ideas on that. We have ideas on the Hallett-Mossop zone, rime splintering process. And then these also can go up in the abrupt up there. And then we are thinking to modify our model based on what we find in our observations, actually. So And some of the model simulations also we have conducted where we have seen that the Hallet-Moser process.
ती वायर लावून सुरू केला ना इंटरनेटची तर सुरू नाही होत. काय झालं होतं हा फोन इन बिटवीन खराब झाला होता.
Sorry sir, I am having
ते अडॅप्टर लावलं आणि म्हणाले याला कधीच डिस्टर्ब करू नका. तर मी काय केलं त्या दिवशी सतीश.
Yeah, actually we are also studying the impact of pollution in the different moist environments. So one thing we have looked at is the impact of Hallet-Moser process in different polluted environments. And here the red curve, but what you see here, it is for the polluted environments, and by the continuous curve is for the Hallet-Moser pond, and the dashed curve is for the Hallet-Moser process off. So you can see that there is a significant difference in the number concentration. This is the number size distribution. So there is a significant difference contributed in the number concentration contributed by the Hallet-Moser process. So this work is under process, and I am kind of not, due to the current my situation, I'm not describing the other aspects. I am coming to the conclusion, possibly the secondary ice production may introduce, I just want to make a few points here, may produce numerous ice particles, and they actually lead to complete glaciation of the cloud. And the studies show that the HM process alone cannot describe rapid glaciation of the clouds. Actually, we have seen certain clouds with rapid glaciation, so we may be looking at in more detail. And the secondary ice production mechanisms and their production rates are not well understood as per the monograph by Phule et al. And then also the droplet fragmentation is a process that we have to understand further. And actually the models may have some unrealistic coalescence rates, especially when we are using bulk models, and because from the cloud to rain formation is not very clear. So there is a very interesting study. If students are interested, they need to look at this. Actually, there are a number of processes they have investigated in this study, and how it impacts the secondary ice production in the cloud. For example, this droplet shattering. When the droplet shatters, actually at a particular level, many ice particles are emitted, and if models are not able to reproduce this, it is of no use. So there are several gaps in the understanding of secondary ice production. Actually, we need to have better observations of ice nuclei particles, and role of immersion freezing to be investigated further, and observations to confirm different secondary ice production mechanisms. As I mentioned, 2 different mechanisms we could able to see in the monsoon clouds, and likewise we have to look at other mechanisms, and there is a actually in different cloud types or in different geographical conditions, we need to look at them and need to measure small ice crystals, which is very difficult. We cannot really with the current set of observations, we cannot get very small ice crystal number concentration. And we also need to do model intercomparison studies. Actually, I want to bring the point that the ICCP conference is going to happen as a hybrid or a virtual conference just in August this year. And there will be a cloud modeling workshop where we also have a CAPEX case study. The students should be able to participate and contribute to the case study. And there are also airborne data processing workshops. One will be able to learn about the aircraft observations further, and also there will be radar training program. So the last date is extended to 30th January. So I think it is a very golden opportunity. There are I think over 700 abstracts we have received so far, and it may even be more. So with that, I want to actually thank Pradeep sir, and thank you all. And I want to thank you, Pradeep sir, for giving. You have been like a spark in our life. I must say that we have all learned a lot from you, and thank you for everything.
Thank you, Tara, for very interesting aspect of the clouds. This secondary ice particles is really an important aspect with respect to temperatures and type of dynamic motions in a cloud. I'm afraid not much time has been left. Unfortunately, there was some electronic glitch. Can we can discuss this afterwards if time remains. But one short question, if somebody has, we can entertain that.
Good morning, madam. Thank you for your nice talk. I just want to ask that during the active and break monsoon phases, how much is the percentage difference of this SIP, secondary ice production?
This is a this will totally depend on if the cloud is able to go beyond the freezing level. Okay, so the right now there are no continuous in situ observations are very few, and I must say that for the break conditions, maybe the clouds are very shallow and there may not be. So that is what I wanted to discuss. And there was one slide that if Kamra sir permits, I can just show that one slide where.
Sure, go on.
Yeah, just yeah. This is this. Are you able to see this?
Yes.
Yeah, so this is actually a break monsoon polluted clouds. In the break monsoon polluted clouds, what happens? We have very less liquid going above the freezing level in this particular situation. And in the polluted monsoon, we have the water vapor. We have we have a lot of large droplets, the supercool droplets that are going above. So there are more drops available to freeze. But in the clean monsoon case, even if the situation is much more better. So this itself gives us an idea that there is a priority for the availability of more moisture, more ice production that way. Okay, so even the break conditions also might have a typical scenario, like if the water vapor is trapped in the middle atmosphere, then indeed we can have some even deeper convection also. But the situation that we considered here is only for the shallow. It means there was not such a increase in the middle atmosphere. So it depends on various aspects, but it's an interesting aspect to investigate further. So I just wanted to bring this aspect so that we will think about it and will do something more. Maybe more students will take it up as a topic for their research or so. So I thank you.
Well, thank you very much. I am sure that you have a lot of data available with you that you have collected from your aircraft measurements and this thing, and this data will be very useful for your studies and others. But just because of shortage of time, we have to close it. At the end of the session, if we have some spare time, we can ask more, discuss it more. Thank you very much.
Thank you, sir.
And next speaker is Dr. Panditarai. He's looking after the JPSL at Mahabaleshwar.
Thank you, Dr. Kamra.
Yes.
Am I audible and visible?
Yes, you are visible, audible, yeah.
Oh, thank you. First of all, I thank IMS Pune chapter for having me in this conference. Also, I thank Professor Pradeep Kumar. I'm privileged to speak on this occasion that we are felicitating by conducting this small session. So with this, I will share my presentation. Is it visible?
Not yet.
No?
No.
No?
No.
Actually, it came and disappeared.
Is it? Oh, okay.
Please share the entire screen.
Yeah, I'm going to application window and selecting this presentation and sharing.
Yeah, now it has come. Now it has come.
Yes. Very good. Okay, thank you.
Full screen.
Full screen. Is it visible?
Yes, sir.
Yes, it is good.
Okay. Yeah. I'll be talking on aerosol cloud interactions, some glimpses from high altitude cloud physics laboratory set up at Mahabaleshwar. So when we say aerosol cloud interactions, we often use to convey a few underlying microphysical processes. The first is the cloud albedo effect proposed by Tony, which is higher aerosols means that higher droplet number and smaller droplet size and enhanced cloud albedo. The second effect is cloud lifetime effect. When the droplets are very small, so there's a suppression of collision coalescence and warm rain initiation. I think better you will appreciate by seeing this picture. For the same volume, if we have more droplets, then there is a more surface area for enhanced reflectivity. So in addition, when the drops are small, because of increased aerosols, then the clouds will not precipitate as much. If the cloud does not precipitate, then it retains its water, lasts longer, and becomes larger and more reflective. This is the lifetime effect. And high altitude cloud physics laboratory was demonstrated that we can understand the processes relating to cloud aerosol and precipitation interactions. So we have a good suite of instruments, for example, like cloud droplet probe, which previous speakers mentioned, which was used in aircraft. So the same can be used in surface also by modifying slightly with the aspirator system. So what you see is the cloud droplet number concentration observed by one probe, the cloud droplet probe. And this is a combination probe. What you can see here is a laser beam, and the cloud droplets pass through, and we will be able to size and count it. And when we combine both the probes, we will be able to observe from 3 micrometer to about 250 micrometer. So with this, in addition to these cloud probe, there are several aerosol instruments. We can get the aerosol size, chemistry, and cloud condensation nuclei, cloud-based height, liquid water path, and the continuous images of sky. So with this suite of instruments, I think I'm showing only a few instruments here. So with that, we are able to study the cloud aerosol interactions. So this this is some one of the results that how if you look at this picture, if there is for a same liquid water content, if there are higher droplet number, then there is a reduction in droplet size. So which also can be seen from here. When the CCN concentration is high, the cloud droplet number concentration increases, and when the CCN concentration increases, the cloud droplet size gets reduced. So this is the cloud albedo effect. From this, we can estimate how many watts per meter square it can the enhanced cloud albedo can reduce. Then I thought I will show some important recent works which are being undertaken in this lab. One is CCN activity. So for an aerosol to activate as a cloud condensation nuclei, so it need to be there should be a threshold size, which is a dry diameter of the particle, and chemical composition, and its water uptake or hygroscopicity parameter. Also, I thought I'll show some results because this session is to honor Professor Pradeep Kumar. I thought I will share some ice nuclei measurements and some recent efforts on parameterizing it. So, simple description of CCN activity of complex atmospheric aerosols are needed to better constrain cloud resolving models, chemical transport models, and GCM simulations. So, initially we attempted the aerosol CCN closure using bulk aerosol composition datasets observed at HACPL. Currently, attempts are being made to derive aerosol hygroscopicity through growth factor measurements for better understanding on CCN activity. Generally, the hygroscopicity parameter lies between 0.5 to 1.4 for highly hygroscopic salts, such as sodium chloride, whereas 0.05 to 0.5 for slightly to very hygroscopic organic species, and it's a 0 for non-hygroscopic components. It's popularly called as a kappa component, hygroscopicity. In general, atmospheric particulate matter is typically characterized by kappa values lying between 0.1 to 0.9. So this is some earlier research wherein we did not have kappa measurements directly, but by having the aerosol chemical composition, we try to have different sets of assumptions that, so if we have only inorganics, so what happens, and if we have by combining organics and inorganics, and also adding the aged organic aerosols, which are oxygenated organic aerosols. So we found that by including oxygenated organic aerosols, we were able to better model the CCN compared to observed CCN. So recently we thought we wanted to actually measure the hygroscopicity parameter. We had a experimental setup using hygroscopic tandem differential mobility analyzer and CCN counter. So the polydispersed aerosols, first it goes through it dried at low RH conditions and passed through a DMA, and after DMA you get only the monodispersed aerosols at desired diameter. Then you count how many particles are there, and also you send to another humidifying system. So after humidification, so how much the aerosol size grown. So you can get the growth factor. So from the growth factor, we'll be able to calculate the hygroscopicity parameter. These are some of the experiments which are done for different sizes at different relative humidity values and compared with the theoretical model. And this is a diurnal variation of hygroscopicity for 1 month, and you can see the hygroscopicity is not constant throughout the day, and it is depending on the chemical composition and depending on the transport of aerosols and the aging of aerosols, the hygroscopicity or hygroscopic growth factor changes. This is for a given diameter about 110 nanometer. You can see these higher values during the early morning hours or late night hours. So that is mainly due to the inorganic aerosols are predominant, whereas during daytime, in the initial part of the day, So because of high organics, hygroscopicity reduces, and with aging, then it starts building up. So we also try to look at how the chemistry influences the hygroscopicity. So we notice that this yellow curve is hygroscopicity, and what we see is the chemical composition of sub-micrometer particles. So the green shows organics and blue is nitrate. So when the organics are high in the early morning hours, the hygroscopicity tend to reduce. So this is a currently a PhD student working on it, Abhishek Ray. And also he also looking at the hygroscopic growth. So for example, this graph shows the dry diameter, and you look at the after humidification, what happens to the size of the particles. So ranging from 50 nanometer to about 250 nanometer, you change the relative humidity and look at the change in the size. So also we try to look at the activation fraction versus hygroscopicity. Activation fraction is nothing but what fraction of aerosols are got activated as a CCM. So if it is 1 means all 100%, all the aerosols are activated as a hygroscope, activated as cloud condensation nuclei. So I thought I will show some results from ice nucleating particle measurements. So this is INP. It's a small set of atmospheric aerosol, helps in the formation of ice particles. Its concentration is very less compared to cloud condensation nuclei. For example, say 1 in million of aerosol particles. So in this study, we used a continuous flow diffusion chamber for online measurements of INP in an air sample. So these are some results we reported recently with the temperature in the lower temperature, like -25 to -35 degrees Celsius. What is the ice nuclei particle concentration? So we also compared with the previous studies, so to operate in the lower temperature, we need to still use dry nitrogen gas as a sheath air. So right now we are not yet implemented. So in future we plan to implement this additional facility so that we can have measurements in the lower temperature range also. So we can see that there are so we are complementing in the lower temperature range as compared to the previous measurements. Also you can see the experiments conducted worldwide, and also given is the different ice nuclei parameterization schemes. So this the disagreements between the heterogeneous ice nuclei parameterization schemes suggest the importance of formulating a better INP parameterization over this region. So we also looked at INP concentration versus aerosol number concentration. You can see that there is a if the coarse mode aerosol concentrations are high, and you have a high ice nucleating particle concentration. So we also try to look at the chemistry. So when we have a higher organic fraction, so we have higher INP concentration, but this needs further studies. Extensive studies are required to quantify the role of chemistry in activating INP. So here we have, first time we have a seasonal variation in different seasons, how the ice nucleating particle vary. So you can see the pre-monsoon and post-monsoon seasons, we have high INP concentration relatively because of lower scavenging potential. Some of the existing parameterization widely used in numerical model or for heterogeneous ice nucleation process are, some are supersaturation dependent, some are temperature dependent, and some are temperature and aerosol concentration dependent. So this is one of the widely used scheme which uses temperature and aerosol concentration dependent formulation. We utilize this parameterization for our observation and try to see that the measured ice nuclei concentration and predicted INP concentrations have disagreements. So then we thought we'll modify the scheme, and we found that so they have used different criteria in selecting the size threshold for aerosol number concentration. So when we modified this, that we have a better parameterization for our region. So even though the DMARDITEL have used observations from several places, but very limited observations must have gone into this for the Indian region. So this paper is under review in atmospheric research. So with this, I will summarize that we have we are currently utilizing the hygroscopic growth on CCN activity representation, and also aerosol dependent ice nuclei parameterization for our region is developed and tested in numerical models. So with this, I thank the organizers for giving me this opportunity. I'll be happy to take questions. Thank you.
Hello.
Yes, sir.
Yeah, thank you, Dr. Pandit. Well within the time. So I have one question that in one slide you showed the variation of ICN with the organic aerosols. Now, INP nuclei, they are generally produced by this combustion or fossil combustion, or there you are talking of some other source.
Yeah, INP, the potential ice nuclei are dust particles, but there are studies, dust and biological aerosols. Biological aerosols.
On the other hand, INP is generally produced by inorganic this thing, no?
Yeah, but recent studies are showing that there are organics also, aged organics are also playing a role. But these are some preliminary results. We need to have still more.
So both going hand by hand, increasing or decreasing. So that means two independent processes. No?
Yeah, it looks like when organics are increasing and there is a organic fraction gets increased, then you have a higher INP. But
I see. Very interesting results. Now floor is open for question and answers. You can, if anybody has a question.
Thank you for your nice presentation, sir. One clarity for me: these INPs, organic or inorganic, they are very cold temperatures. How it is measured, sir?
Oh, the organics or inorganic, that is the independent measurements. Okay, so these are so INP concentration is measured from ambient air, but it is not connected. These both ice nuclei and chemistry is not a connected process. Means it's separately it is measured. Okay.
Okay, sir.
So at that point of time, during the experimental period, what is the major chemical composition? That's what independently it was looked at, and we are seeing that. So still there is a lot of work to combine these instruments and only allow certain size. It can be possible in future.
Thank you.
Your instrument can differentiate between variety of organic compounds.
Yeah, so it can distinguish the oxygenated organic aerosols, biomass burning organic aerosols, and fossil fuel means hydrocarbon like organic aerosols, because it's a mass spectrometer. From the mass to charge ratios will be different for different types of organics. So we can even look at the cooking emissions. So biomass burning or cooking, the emissions from cooking, all these can be seen with this mass spectrometer. Yeah.
So air mass is coming from Arabian Sea to this high altitude laboratory. They have a lot of bioaerosols due to the vegetation.
Yes, definitely. Right now, we don't have any measurements on bioaerosols. We are planning in future because the Western Ghats is a dense vegetated area, and definitely there will be a lot of biological aerosols. So in future, we are planning to have biological aerosols, and also that can even activate at lower temperatures. So we want to have additional setup for this ice nucleation chamber for having conducting experiments at even at lower temperatures.
I see.
And the air mass is, yeah, we have. I have not shown some of the results because the air mass is wherein in pre-monsoon we have the dust concentration may be high because of westerlies. So the dust will be a potential icing field, very high potential icing field.
Any other questions? If not, we'll thank Dr. Panditaraji for excellent presentation. And I think I would like to advise our colleagues to visit his lab in Mahabaleshwar. So in addition to strawberry, they can have a variety of instruments. I think he has heavily instrumented that observatory, and that's worth visiting.
Yes, I join in Dr. Kamra to welcome all those who have not seen the laboratory. You are welcome to visit our lab. Thank you. Thank you.
Thank you very much. Thank you. So next talk is by Dr. Pawar, S.T. Pawar, on about who is looking after the development of lightning location network, not over Maharashtra, but I think he plans to cover it all over India, and what he wants to say about the electrified nature of clouds. Dr. Pawar?
Yeah. Okay. Good morning, everybody. I will first like to thank.
Can you have the full screen?
Just a minute. Yeah. Okay. Okay. Can you see my presentation?
Yeah.
Okay. Okay. First of all, I would like to thank organizer for giving me opportunity to speak in this special session. I will be talking about the drop site distribution, role of drop site distribution in the formation of inverted polarity charge structure. As we know that even in 1751 or 52, Benjamin Franklin first time showed that lightning is or he proved that lightning is nothing but an electrical phenomenon. Lightning discharge is an electrical discharge. But almost it took 200 years to understand the exact nature of a thundercloud or charge structure inside thundercloud. Wilson in 1920, based on his electric field and electric field changes after lightning below thundercloud, he concluded or he showed that this electrical structure means there will be positive charge in the upper portion of the cloud and there will be negative charge in the lower portion of the cloud, what is called as a positive dipole. But Simpson in 1927, he observed that whenever there is a rain charge or he measured the charge on the precipitation particle at the surface, and he found that most of the time it is a positive charge. This rain drops are carrying positive charge, and from that he concluded that there should be positive charge in the lower portion of the cloud and negative charge will be in the top of the cloud. From that he concluded that thundercloud can have negative dipole. And of course, after that many measurement, people proved that it is not exactly positive dipole or negative dipole, but it can be a tripole type of structure. Means there will be positive charge, means just like this, there will be positive charge at the top of the cloud, there is a negative charge in somewhere the middle or lower portion of the cloud, and again there is some positive charge packets at the base of the cloud. And this is nowadays accepted charge model, or it is accepted charge structure in the thundercloud, which is generally we call it as a tripole charge structure of thundercloud. And this also can be seen here also. Actually, even though this is accepted, but very early in 1958 itself, Venegat and Murray, they observed electric field changes measured at one severe thunderstorm, and they concluded that this thunderstorm can have a different charge structure. It will have an inverted polarity charge structure. And after so many, almost many years after that conclusion, this step experiment was carried out in US to study the electrification and precipitation in a severe thunderstorm in 2000 somewhere. And many papers after that 2000 experiment, there came many papers which shows that many severe thunderstorm can have this inverted polarity star structure. They found that exactly the place where a general or normal thundercloud can have positive charge, there they found it is a negative charge, and where there is a negative charge, they found it is positive charge. Means exactly inverted polarity charge structure they found in many severe thunderstorms. Actually this charge structure, generally this many charging mechanism people have proposed to explain this charge structure, but only one charging structure, the charge mechanism, that is non-inductive charging mechanism, can only explain this non-inductive charging process, this inverted polarity charge structure, because this non-inductive charging mechanism at many experiments people have shown that this charge transfer, means when ice crystal collides with bigger ice particle or grapples, then there is a charge separation will occur, and they've observed that at one point, at one temperature, it is called as a reversal temperature, that temperature sign of transfer is changing. Means generally in a temperature higher than lower than around -18 or -20, the grapples will get negative charge and ice crystal will get positive charge, and that ice crystal will form upper level positive charge, and grapples or bigger ice particle will form this negative charge region. But if this collision is happening at some higher temperature, then the situation is reversing. Similarly, this many experiments, specifically this Takashi, he's shown that this reversal temperature is a function of cloud liquid water content. Inside the mixed phase region, how much the liquid water is there, from that that can be any temperature can be the reversal temperature, and he's shown that if liquid water content is very high, then in that condition even already means normal temperature, what is observed in mixed phase region -15 or -20, that also can be charging process can reverse, and thundercloud can become an inverted polarity. Then after many studies, this Saunders, he concluded, of course there are many papers to conclude this actually, and he found that when surface is growing, means faster growing crystal and this slower growing grapple, when they collide, generally these crystals will get positive charge and these grapples will get negative charge, and therefore they get separated, and there will be the positive charge in the upper portion and negative charge in the lower portion. Dr. Pradeep Kumar with Saunders also, he did some experiment about this cloud chamber. Of course, he developed that cloud chamber in Pune University also, did very good research about this charging mechanism. But his first experiment in this with Saunders, he studied this interaction or collision of ice crystals with dreamed target, and he found two important conclusion. Of course, first one is he just confirmed that the surface states of the interacting particles affects on the polarity of charge. But the second conclusion also is very important actually. He found that charge transfer, magnitude of the charge transfer is depend on mainly when the ice crystal are growing from the vapor, the charge separation can be substantially high. And I think that may be the main reason that this most of the clouds are forming with normal polarity, because this charge separation, if ice crystal is growing faster, then there will be large substantial charge separation, and therefore more number of normal polarity thunderclouds may be forming. Then I will come to some of our observations of inverted polarity charge structure. Actually, as I told, many researchers or many people in US and some other parts of world, they shown that severe thunderstorm can have inverted charge structure. But first time in 2002, myself and Dr. Kamra, we shown that even ordinary thunderstorms can also behave as an inverted polarity. Means generally criteria to say it is normal polarity or inverted polarity is considered as lightning discharges. If more than 50% lightning discharges, If more than 50% lightning discharges are positive, then generally people call it as a inverted polarity star structure. And myself and Dr. Kamra, when we started measuring this electric field below thundercloud in 1996, then we observed that many thunderclouds forming over Pune region, they are having that inverted type of charge structure. And after that, we measured many things. Then, of course, I have shown here only one observation, but over Tibetan plateau also Chinese people also have shown that many thunderstorms forming over that region also are similar to what we are observed. You can see here actually electric field during normal thunderstorm, there will be electric field is increasing, then this is a discharge, lightning discharge, electric field will decrease. But if you see this type of discharges here, actually electric field, instead of growing this way, it is growing this way. It is showing that accumulation of positive charge over it, means whatever may be the charge region, but the lowest charge region is a positive. And you can see when lightning is discharging, it is discharging or destroying the positive charge. Here it is destroying the negative charge. From that, actually, so many measurements, we concluded that in Pune region, there are three types of charge structure, we can say. This is a normal type of charge structure, then this is a tripole type of, there is a positive charge, negative charge, and there is equally strong positive charge. Therefore, both type of lightning discharges, we can see positive as well as negative. But some are forming, even though we can say it is a tripole because there is a possibility of some positive charge over it, but it is exactly opposite to what we generally observe. This is exactly opposite to that. Therefore, we have called it as a negative dipole or inverted polarity charge structure. Then what is the possible cause of this formation? Actually, this many people, as I told, many thunderstorms they observed when it is a severe thunderstorm only can form inverted polarity. Therefore, high Cape was the main, and this enhanced aerosol concentration. And of course, Williams collected all this observation, and he put one theory, that is superlative liquid water content. Means he told if it is a very high liquid water content is there in the mixed phase region, then thundercloud can become an inverted polarity. Then effect of drop side distribution, this Avila 1999 and Prakash and Pradeep Kumar in 2010 and some many people, they shown actually that when drop side distribution also affects on the charge separation. This I have shown Dr. Pradeep Kumar's one results, and here we can see actually if drop side distribution is a smaller size, then there is a positive propel charging is very high. Actually here means it can convert into inverted polarity star structure. Then as I told, our observations also, whenever we observe that there is a negative or inverted polarity star structure, the aerosol possibility of having high aerosol concentration was very high in this also. Then we observed one in over Kharagpur also. You can see actually this is a very severe thunderstorm over Kharagpur. Cape also was very high, and the cloud top has reached almost 18 kilometers. There also we observed on that day when we observed this inverted polarity, AOD was very high, means aerosol concentration was very high, and even dew point depression also was very high, actually showing the drier condition. Then recently in 2017, actually we collected all the observations what we were having in Pune, and we here also we observed actually we can see very clearly actually this inverted polarity charge structure, they are coming in when there is a high AOD. Even here also we can see very clearly actually this whisker plot also show very clear distinction between this inverted polarity and normal thunderstorms. This AOD is very high actually. From this actually we can say actually that this AOD, if AOD is very high, or here as we have shown actually here, this dew point depression and AOD together, they can make the drop side distribution smaller size, and smaller side drop side distribution can be useful or that is the main cause of this inverted polarity charge structure what we have observed in Pune. Therefore, our conclusion is actually our measurements of this is not the conclusion of this talk only, but this is the conclusion of whatever research we have done with Dr. Kamra and whatever our colleagues. What we concluded that this electric field measurement and Maxwell current density measurement, it clearly suggests that some of the thunderstorm forming here are inverted dipole charge structure. Of course, we don't know it is a tripole or inverted dipole because we don't know exactly what height there is a positive charge or negative charge. We are talking only about the lightning discharges. If positive lightning discharges, more than 50% lightning discharges are transferring positive charge to the ground, then we can say it is a inverted polarity. Therefore, we are always using this tripole structure also because we don't know it is a inverted or tripole structure, but it is as good as inverted tripole structure we have observed over here. And almost all the cases we have observed that this high aerosol concentration and high dew point depression or high cloud base height, which suggests that smaller topside distribution in the mixed phase region can be the cause of inverted polarity star structure. Okay, that's all. I would like to thank Dr. Pradeep Kumar also for his help and cooperation in our health encouragement he gave to us very valuable. And I wish him healthy and active retirement life. Thank you. Thank you very much.
Thank you, Dr. Pawar, for your measurements, showing your measurements and discussing the history of results. I think this area of interaction of electrification of clouds with the microphysics is gaining importance in the present international scenario. And what you are doing in with the lightning location network, they are very useful for our state departments for hazard incidents. So I will like to open this question and answer session. If somebody has some comments or questions.
Sir, there is one WhatsApp question. Are the cloud microphysical process for tropics and mid-latitude same?
Definitely they are not the same because microphysical, specifically this dynamical structure of extratropics and tropics are very different. Therefore, definitely they are separate. They are not exactly equal to or similar to each other. Actually, they are different.
Sir, you told that this tripole and dipole and inverted things, how it is in a very good monsoon time and bad monsoon as far as rain is concerned. At that time, where this particularly plays a role?
Actually, this monsoon cloud, generally they are not thunder cloud, but generally what we have observed during monsoon also a lot of thunderstorms are getting formed actually. And I have not shown here actually, but we have studied the polarity of these thunder clouds or lightning during monsoon because as Dr. Kamra told, now we have this lightning detection network because earlier we have to limit our things only using this field bills and Maxwell current antenna, which have very small range up to 20-25 kilometers from the observational site. But now because of this lightning network, we can study all over the India where this inverted polarity of thunderstorms are forming. And we definitely observe that during monsoon, this inverted polarity thunderstorm formation is very high compared to even pre-monsoon or post-monsoon.
Thank you very much, sir.
Thank you.
Thank you.
Any other questions? comments? I'd like to have some questions from our younger students who are maybe interested in this area. If there are no more questions, I will like to thank Dr. Pawar for his presentation.
Thank you, sir.
Thank you. And finally, in this series of invited lectures, we have one special lecture by Dr. Pradeep Kumar. You might have seen, most of you, his felicitation, and in his honor, this session is being, not this session only, but the whole symposium is being organized, and we have heard some of the views of different speakers about his work and their collaboration with this, and we will be very pleased to see about his measurements and research work. So, Dr. Pradeep Kumar?
Yes, I'm here.
Yes, go ahead.
I'll share the screen. Is visible now?
Yeah.
It's in the, this visible now in the full mode?
Yeah.
Okay, my talk will be on ice nuclei and its role in cloud microphysics. I'll start with little basics and then go to our measurements and then look at how the measurements around the world are there, and then look at some other aspects of ice processes in the cloud. Okay, but first of all, I would like to dedicate to my teachers this talk. And the first comes late Professor N.C. Varshnaya of IIT Roorkee, who introduced me as an MSc student to the area of atmospheric science and cloud physics. And it was his inspiration that I came to this field. Next to my guide, Professor Jagdish Rai, from whom I learned a lot about lightning. And then to Professor Clive Saunders of University of Manchester, UK, with whom I did my postdoc research, who introduced me into the cold room research of thunderstorm electrification process. And then to my collaborating US Army scientist, Dr. Hugh Carlin, who made special efforts to fund this project for me in India, with which I could establish the cloud physics laboratory with the walk-in cold room at Savitribai, Pune University way back in 1994. So this talk will be dedicated to all my teachers. Let's come to why ice phase is important for monsoon clouds. If you look at the scenario, more than 50% of the mid-latitude precipitation is produced via cold cloud involving ice processes. And even in the tropics, this proportion is almost about 30%. And if you look at, this is a typical monsoon situation of the clouds in India. You see that most of the clouded region here, they are reaching as high as -40 to -50 degrees Celsius temperature. So, but very few in situ observation of ice microphysical properties are available. So if you look at a typical deep convective cloud in the tropics, you will have up to freezing level, you have only liquid water, and from 0 degrees to -40 you have ice as well as supercooled droplets, which we call it as a mixed phase. and above -40 you have only glaciated clouds. Now what are the different ice nucleation pathways which are there? You have the homogeneous nucleation, which is typically happens only below -38°C. So therefore, in the clouds from 0 to around -38, some other processes have to initiate the ice nucleation, and that is the heterogeneous nucleation. Wherein we have the deposition nucleation, wherein on a foreign particle the vapor can deposit and grow, and they have an immersion freezing where it is the particle is embedded in a droplet, and when cooling is there and sufficient cooling has happened, it will freeze. Or you have a particle on which first drop condenses and then this one, but these two, immersion and condensation freezing processes, are very difficult to separate out from each other. And then you have a contact freezing, which is externally, if a particle hits the droplet, it can collide and then freeze. So ice nucleating particles are material substance. Hello? Object, item, unit or other that is assumed to be the agent responsible for observed heterogeneous nucleation. Am I audible?
Yes, you are.
Okay.
Yes, sir, you are audible.
Okay. Now, once the ice crystal forms, it can take a variety of habits. Okay, it can take plates, columns and plates, and there are a variety of shapes it will take, like dendrites, needles, hollow columns, solid prisms, like that. Okay. And that depends upon the temperature at which these are forming and what is the supersaturation with respect to ice in the clouds. After that, ice can grow by aggregation or accretion process. Okay, aggregates is when they are sticking together and then the growth is happening. Or during the accretion process, when the supercooled droplets will collide on the ice crystals and then collide on them and freeze, and they call it as a rimed crystal. And when riming has grown beyond a certain stage, we call it as a graupel, and further growth of graupel will result into hail. So this is, once a basic ice crystal has formed, it can grow through these different mechanisms. But there is another process which is very important, which is the Wegener-Bergeren-Findensen process, more popularly called as the Bergeren-Findensen process, that relies on the fact that the equilibrium vapor pressure of water vapor with respect to ice is less than that with respect to liquid water at the same sub-freezing temperatures. So as a result, what happens is, because the vapor pressure on the supercooled droplets is higher, they will begin to evaporate and supply the vapor to the ice crystals. So ice crystals would gain in mass by vapor deposition at the expense of liquid drops that would lose its mass by evaporation. So this is another process which is responsible for the ice particle growth in the cloud. Okay. Now in the Kypex phase 1, for the first time over the Indian region, we documented the vertical structure of hydrometeor distribution in the deep cumulus cloud. And what they found is there is up to about 7 kilometers they had gone, and they have found high supercooled liquid water content in the cloud. They have found a mixture of graupel and ice particles. And they also showed that mechanisms other than Wegener-Bergeren-Findensen process are active. And this was by Tara et al., published in Journal of Atmospheric Science. Now, if you look at the ice nucleating particles, the basic things which are required is its crystalline match should be with that of ice. So basically, the crystalline structure of the particle should match with that of the ice crystal structure, molecular structure, and ability to form hydrogen bond with water. And it should have active nucleation sites, wherein the ice ice formation can initiate. So active nucleation sites, which we call in material science, may be dislocations while the formation of the particle is happening. So what are the main groups of ice nuclei? Mineral dust is one of the main group of ice nuclei, which are kaolinite, etc. Then common clay minerals. And you can have soot, can have biological aerosols including bacteria, can have solid ammonium sulfate, which is specifically important for cirrus cloud formation, organic acids, and others. This is a figure giving an overview of ice nucleation onset, temperatures, and supersaturation ratio. These are basically all laboratory results which compiled by Hoos and Muller, the 2012 paper. It's a very famous diagram. If you look at it, the temperature is here and supersaturation with respect to ice is given here. So you have all these different, this one given, deposition, condensation with black carbon, immersion, freezing, like that. But one thing which, if you look at it, at the lower temperatures, it is mostly the bioaerosols which are activating. That is the most important thing to note. At temperatures which are closer to -10, and there you don't have any other compounds are not very good at activating at ice nuclei. So here in this region, it is the bioaerosols which are these green ones which are there. They are the most active here. Now, if I summarize what are the analysis of these laboratory results, for mineral dust, for submicron particles, there seems to be a tendency of natural dust to activate at higher ice supersaturation. If you take soot particles, it depends upon combustion type. And Muller and Crawford found significant decrease in ice nucleation activation with increase in organic carbon content. I will continue with this analysis. Bioaerosols, in particular bacteria, the ability to nucleate is selective. Only a small number of bacterial strain and fungal species have been identified as ice nuclei activated. Temperatures higher than -10 degrees Celsius, that is, it is around -5 or something. Very few strains have been identified. Solid ammonium sulfate is found to nucleate efficiently at temperatures which are relevant to cirrus cloud, mainly around -50 and things temperatures. Organic acids in crystalline form observed to nucleate as ice, again at cirrus temperatures. Silver iodide is a well patented one because mostly the cloud seeding people use silver iodide because its structure is very close to the ice crystal structure. Then coatings, mineral dust, soot bioaerosols coated with sulfuric acid, ammonium sulfate, nitric acid, etc. need higher saturation ratio as compared to uncoated ones. So coatings are very, very important because most of these aerosols, whether dust or soot, will be spending a lot of time in the atmosphere where they can get coated with various compounds. So coating is plays an important role. Now, what do we do in field observations? Field observation techniques, which is started by Big 1957. Big et al. Paper is very, very famous. Okay, they take a cloud chamber where a sample of air is cooled by sudden expansion to create supersaturation. This is his chamber, 1957's publications. Okay, and this is his results, and you collect the number of ice crystals which are formed, and then your number of ice crystals is proportional to the ice nuclei in the atmosphere. That is how you arrive at the number of ice nuclei in the atmosphere. Next is a continuous flow thermal gradient diffusion chamber, which is basically you have two plates, and in between you have your you first make an ice sheet, and you have the ice sheets here, and if you have the relative humidity with respect to ice is greater than 100%, relative humidity with respect to water less than 100%, you have deposition ice nucleation, and with greater than 100% you have condensation ice nucleation. So you have a high velocity sheet flow here, to the side of the chamber, and you bring in your aerosols from the air and take it through the center of the chamber, and they will form ice in the chamber, and you detect it, and that is proportional to the. So this is a kind of instrument which is being operated now at the Mahabaleshwar also. Now I'll come to our work, what we did at Savitribai Pune University. What we did was we built a static thermal gradient diffusion, because this is not taken into the field. But what we do in the field is we collect aerosols on filter paper, and we bring it back to the lab, and we keep it in between the two ice plates and close this chamber. And then we change the temperature in the chamber, and as the temperature between the plates, two plates are changed, you can vary the supersaturation with respect to ice in the chamber. And after some time we open it and count the number of ice crystals which have been formed, and that number of ice crystals is proportional to the number of ice nuclei in the atmosphere. And you can measure the condensation freezing nuclei if your saturation ratio with respect to water is greater than 1, or a deposition ice nuclei if your saturation ratio with respect to water is less than 1. Okay, and your with respect to ice is always greater than 1. So during the first phase of KIPEX, we collected 90 samples from 5 regions were collected. These are the regions which are shown, the 5 regions over India, which the IITM's KIPEX aircraft, which we made use of, and around 90 samples were collected in 2009, and another 50 samples were collected in 2010 and 11. Minimum sample collection was at 220 meter, maximum height we could go to was around 7 kilometers. So this gives you the spatial distribution of the ice nuclei concentration or different regions of India at various ice supersaturations. And this is from 5 to 10%, 10 to 15, 15 to 20%, and 20 to 25% ice supersaturations. Okay, and maximum we could get in some regions only was around up to 5 nuclei per liter of air. And we also carried out the SEM-EDX analysis to find out what are the compounds which were there on the filter. And these are the kind of compounds: magnesium, copper, zinc, ferrous, and these compounds were. And this is a published work by my PhD student. Jointly, Tara was the guide and I was the co-guide. Tara was my student. So we published this work in 2014. Now, if you look at a few results from different locations globally, this is our work, where our variation was 0.276 to 5 per liter, and in the temperature region minus 13.5 to minus 18.5 degrees. And these are from different regions in the world. You could see that we are comparable. Okay. And this is KIPEX results again compared with different regions around the different observations. And these red boxes are the Patade et al. Which we got from the KIPEX. So they fall in the region, they fall in the range. Okay, it is not way out of the range. Then we did some high altitude observations at Ooty, and about 100 kilometers from Pune, there is an Ayuka's Girvali Observatory, which is around at a height of 1,005 meters, and Ooty was 2,240 meters, which is the radio astronomy center. We went on a campaign mode during 2011, 13, and 14. And we have given the activation factor. See, activation factor is very, very small. It is only 1 in 10 to the power of 5 to 10 to the power of 6. And some years it was more, it was 1 in 10 to the power of 4. And this is at this one, Ooty, RAC. Ooty, it was pretty higher. It was 1 in 10 to the power of 3. 1 is to 10 to the power of 3. And Ooty, the concentration was 1.6 per liter, and at Girvali Observatory, it was 1 per liter. This is again a published work in 2017, and we have done the chemical analysis. Chemicals, most of the compounds found are similar over Indian region. Then what we observed was that we could not see any diurnal variation, but in Ooty there were morning and evening peaks could be observed, and at Girvali there was sometimes a rapid increase in ice nuclei concentration, which we call it as iron storms, and we excluded such samples from the study. But when this one was the air mass originated mostly from the Arabian desert, whenever there was such ice nuclei, heavy concentration was observed. These are the air mass trajectory paths which are shown here. So mostly during 11 and 13 it was coming from the Arabian side, and during 2014 it was coming from the eastern side of India. Okay. Then we did observations. We wanted to go more nearer to the desert because we wanted to see what is happening with the desert dust. So we went to the PRL has a physical research laboratory. Ahmedabad has got an observatory in Mount Abu, which is called as the Guru Shikhar Observatory. That was at 1700 meter, and we carried out a campaign mode. We made the measurements, and what we found was there is no relationship with aerosol shape and ice nuclei concentration. That was one observation which we made. And on days when sulfur content was absent, the ice nucleation activity was higher. So sulfur is somehow that is suppressing the ice nucleation activity. And this is agreeing with the laboratory results of Hoos and Muller 2012, and also field observations made by some other people. So it is in agreement with there. Then if you look at now Anil Kumar's observations from HACPL, which IITM has been carrying it out, okay, which using the commercially available spin. So the results at -25, they have carried it out at -25, -30 and -34. And these at -25, it is in good agreement with Wag et al, which for high altitude observations, and also Patade et al.'s 2014 CAPEX 1 campaign. Then we went, we wanted to see what is happening at the sea coast. So we went in 2013, we went to the Indian Institute of Geomagnetism's Magnetic Observatory at Alibag, which is just on the sea coast. And we carried out again the ice nuclei measurements there. And they are not even though sea salt aerosols contribute towards ice nuclei, but there again, the ice nucleating particle was again less than 1 per liter. And composition analysis we carried out to see what are the elements present. Among sodium and chlorine, of course, are the major elements there. But apart from that, silica, aluminum, magnesium, and zirconium we have found in our analysis. Then in December 2016 to 2017, we participated in the winter fog experiments being carried out at the Indira Gandhi International Airport. And this is during fog condition, haze condition, and clear condition, we made the measurements. And if you see the maximum ice nuclei concentration, 9.56 per liter, we could observe in the fog. And haze is slightly less. And these are the pictures. When the clear conditions are there, it is 4.7. These are clear conditions. All these are the crystals, the ice crystals which are formed on the filter paper. And this is during the haze condition. This is during the fog condition. See, the number concentration is very, very large. And this is in the clear air condition. Okay. And this we have just recently communicated just around a week back to atmospheric research. Now, if you look at all those ice nuclei measurements, you have seen that the number of ice nuclei particles are very, very small. It is almost approximately only 1 per liter. but observed ice particle concentration in the clouds are a factor of 10 to the power of more than active ice nuclei. So historically, if you look at it, the first mechanism of this ice multiplication was proposed by Latham and Mason in 1958. They proposed that droplet fragmentation during freezing is happening, fracture of ice crystals. But then in 1974, they came the Hallett-Mossop process, which gained a lot of attention because very systematically they carried out the laboratory experiments and splinter formation during riming under very selective conditions they could find, because it is dependent upon the cloud droplet spectrum is very, very important. Supercooled cloud droplet spectrum is very important. And this is the picture. It is it's a peak is there, so it is kind of a bell-shaped curve. So cloud droplet spectrum contains appropriate number of small droplets smaller than 13 micron and greater than 25 micron. And presence of Graupel is there, is important. So different target velocities they have count. So this is the process which most of the people try to invoke to explain this ice multiplication process. And this was again, Tara's group has identified the Hallett-Mossop because she has covered all this in her lecture, but I think I should have spoken first and she should have come later. So she was identifying the Hallett-Mossop process from Typek observations. Okay, this is her images in the range -5 to -8 degrees. So she has identified the Hallett-Mossop process from this Typek observations. So again, observation and simulations of mixed phase cloud observed during CAIPEX is again from Tara's group. The conditions required for Hallett-Mossop process to occur are cloud temperatures should be between -3 and -8 degrees Celsius, presence of supercooled droplets with diameter greater than 23 micron at concentration of 1 centimeter per cube, and ice particle velocity in the range 0.2 to 5 meter per second. Their LES simulations, the large eddy simulations have shown that shows within the temperature zone -3 to -8 degrees Celsius, the Hallett-Mossop process of secondary ice formation was responsible for this observed increase in ice concentration. This is from their modeling, this one, which they compared with their this one. Okay, this is again from their paper I am giving you. This is the actual particles measured in this one. This is expanded one. Okay, this is in the active Hallett-Mossop region. But then some other observations, which is by Lawson et al. 2015 in the ice clouds experiments tropical at ICE-T, which it is called. What they found is they found numerous ice particles near the cloud top at -15 degrees Celsius. So this is outside the range of Hallett-Mossop. This one, this is from their ice, this one, and water content is given, and this is their spectrum. So this is one of their main observations, that is numerous ice particles are suddenly growing at around the top of the cloud at -15 degrees Celsius. So this is again from the ICE-T observations, INP, ice nuclear particle, 10 to the power of -4 per liter at temperature -5 degrees Celsius, and 10 to the power of -1 per liter at temperature -20 degrees Celsius. Okay. So ice nuclear concentration are very ice nuclear particles concentration is very small, but ice particle concentration was around 500 per liter. So Hallett-Mossop mechanism may not always be operative because of the narrow range of temperature at which it is working. So other secondary ice formation mechanisms must explain the ice particle concentration observed in these field campaigns. So ice nuclear particles are rare in the atmosphere, approximately 1 per liter. Observed ice particle concentration 10 to the power of 4 more than the active ice nuclear. So different secondary ice production mechanisms You have the droplet fragmentation happening during freezing. Okay. So during freezing, your droplets are fragmenting. Then you have the splintering during the riming process, which is the Hallett-Mossop mechanism process. Then you have the fragmentation during ice collisions. Then you have the ice fragmentation, which is during the thermal shock, and fragmentation during sublimation. These are the various processes of which secondary ice nucleation production process which are there. But in most of the cloud models, the secondary ice processes are neglected, which may actually could result in underestimation of the ice number concentrations. Now let us look at some experiments of simulations of ice-T. Okay, so this is the Hebrew University cloud model with spectral wind microphysics. They use the two ice multiplication process mechanisms, and they could produce concentration several hundreds per liter in the temperature region -8 to -15, which is outside the Hallett-Mossop regions. And the droplet and ice particle distributions agree well within the measurements of ice-T. So when they could introduce the ice multiplication mechanisms, they could simulate what was observed in the ice-T. This is again recent. Patade is our student who is now in Sweden. And this is from the IITM group simulating for the Indian summer monsoon rainfall. They have 3 sets of experiments. Control run by default heterogeneous ice nucleation formula, which is a function of temperature, and they ran mod 1 by using formulation of ice nucleation, which is a function of supersaturation, and mod 2 which is a function of temperature. So mod 1 has shown considerable improvement in the simulation of Indian summer monsoon total rainfall representation by reducing wet bias specifically over the central Indian region. This is by Hazras et al. Work. Then again in the coupled global climate model experiments with ice and no ice, this is again Hazras group, Hazra Hemant Chaudhary. And ice microphysics, when they introduce the ice microphysics, it is seen that it improves the strength of the Hadley circulation with respect to the observations. This is the ice, no ice, and this is the Hadley circulation, NCEP Hadley circulation. Okay, so with ice, it is more or less the Hadley circulation is. So ice simulation enhances contribution of high cloud fraction and stratiform rain. So that is what is their observation. Now let's look at what are the gaps in understanding the ice nucleation process. Okay, because let us come to the electric field, because this is often neglected, although Dr. Pawar has covered about this one, but basically covered on the electrification process. But what is happening into the nucleation process? We've seen that is when electric fields is there is an enormous increase in ice crystal size in the presence of electric field. And ice nucleation during electric discharges, we have shown it in our paper published in 2000 in atmospheric research. Okay, so this is from our laboratory. This one, these are nucleated in very high electric field. You could get normal size crystals. What we could get normally is around 50 to 70 microns, but when there are electric fields present, we could go as high as 450 microns with the presence of electric field. And these are some of the ice crystals which have been nucleated when there is an electric discharge is present. So it is possible that nucleation is also happening in when the electric field is building up in the cloud. The supercooled droplets can begin to freeze and form ice crystals. So ice crystals from splinters from freezing of charged droplets peaking at -10 has been reported by Lauber et al. 2018, and Tara has shown you that video, so I am not showing that again. So, but we need to understand the role of strong and weak electric fields on the ice nucleating capabilities in the clouds, which is not much attention is being paid to it. Then there are several gaps in understanding the biogenic ice nuclei, wherein because they are attributed, although they are attributed to with a very higher nucleation ability, because I have shown you the diagram of Hoos and Muller. They activate from right from very high temperatures as high as -5, -4, and then its range is pretty high. But then there are a lot of this one, because I've typically shown you the different kind of bioaerosols which are there. So all these investigations, their research is still nascent in this area. So this is one area which has to pick up a lot of, but it is a very tough area to work with, especially the bio ice nucleation process, to understand it. So that is another area wherein a lot of research can be done. Then there is gaps in understanding of the sea spray aerosol. Sea spray aerosol is something which is responsible, because that is very important to understand, because a lot of clouds, what is happening over the oceans, if one has to understand. So MAGIC is a field campaign, and which was there, and so these are from the MAGIC Demott et al.'s paper 2016 in the MAGIC field campaign which they have done. And they have plausibility of strong increase in sea salt aerosol ice nucleating particle emission is associated with phytoplankton bloom, and it has been shown in laboratory studies, because basically they have been collecting field samples and bringing in and then doing the online as well as offline analysis. So assembly of data of ice nuclei particles, red is in the laboratory, and blue is from the ambient marine aerosol, and open are offline closed symbols. Okay, so there is again sea spray aerosols which needs a lot of attention. So that is again a gap in understanding. So if you look at the gaps in understanding of the ice nucleation process, so we have to understand abundance and sources of particles that can act as ice nuclei particle across a range of temperatures and different cloud types. That is including the supersaturations. Okay. Then relative contributions of heterogeneous ice nucleation with ice nucleating particles. Then and secondary ice mechanisms. And this is ice nucleating materials, ice nucleating entity, and secondary ice mechanisms to the ice crystal concentration found in clouds. That is again a gap which has to be. And understanding of the active nucleation sites, because that is very, very important. Active nucleation sites, that is, you have to go into the very micron level at the particles, and for that lot of samples have to be collected, and then it has to be carried out under the SEM-EDX kind of analysis has to be looked at for the finding the active nucleation sites. So there is that area is a gray area. And then effect of chemical processing and mixing state of aerosol on ice nucleation. That is also an area which is very, very important, and not much studies is done, because some results which I have shown and which others have also shown, that is how the effect of sulfur is suppressing an ability of the dust to activate as an ice nuclei when a coating is formed. So effect of chemical and processing of mixed state is very, very important. So these are the gaps in understanding the ice nucleation process. So long-term ice nucleating particle measurements from 4 geographically different locations around the world. This is again a recent paper by Schrod et al. 2020. They have carried out during a 3-year period, 2015 to 17, over Amazon region, which is mostly you'll be having bioaerosol kind of regions, then over the Caribbean region, sea, this one, then Central Europe, which is kind of a polluted this one, and Arctic. So these sites feature diverse geographical climates and ecosystems that are associated with dissimilar transport patterns, aerosol characteristics, and different levels of anthropogenic impact. They studied both deposition and condensation freezing modes, at these temperatures, -20, -25, and -30 degrees Celsius. The period was May 2015 to January 2017. And their conclusions is observed ice nucleating particle concentration do not differ greatly from site to site, but usually fall well within the same order of magnitude. So we need more such observations globally to understand the knowledge and understand the knowledge gaps about the ice nucleating particles. So that is where I will give you a take-home message that to initiate heterogeneous ice nucleation in clouds at temperatures less than -40 degrees Celsius, ice nucleating particles are required for primary ice production. The concentration of ice particles in the clouds are a few orders magnitude higher than the observed concentration of ice nucleating particles. So secondary ice production mechanisms are required to explain the observed concentration of ice particles in the cloud. So this is the take-home message I will give, and this is the various precipitation mechanisms. So if you look at it, you have the homogeneous freezing process, heterogeneous ice nucleation, the Bergerant process, the vapor deposition process. These are all actual images of ice particles in the clouds. Aggregation process, riming process, Graupel, and all these again melting layer. So these are all the different ice precipitation processes which are there in addition to your warm cloud, warm rain processes. Okay. So this talk has been, my students have helped me to prepare this talk, so I should acknowledge them. Dr. Tara Prabhakaran from Indian Institute of Tropical Meteorology, Dr. Babban Nagare from Dalhousie University, Canada, Dr. Sachin Patade from Lund University, Sweden, and Dr. Sandeep Wagh from University of Notre Dame, USA. So I can conclude my talk here.
Thank you, Dr. Pradeep Kumar, for a very comprehensive and detailed and valuable contributions of your measurements and laboratory studies. It is really very important, and I think our student community will be encouraged a lot to pursue such. Now, before I start question and answer question, I have one question which is not related directly to your subject topic of talk. That you say you have different shapes of the cloud, of the ice crystals, starting from base of clouds to the top of clouds, needles, columns, stars, and grapples. Are you aware of any studies relating to physics of that type of crystal development? Because why I am asking that if one studies this presence of ice crystals, different varieties, can we use this information as a tracer for existing meteorological and other properties of the cloud at different levels?
I doubt whether that is the initiating nuclei, whether it has any role to play in the shape of the crystal, because we have simulated in our laboratory those different shapes, and what my observation is clearly it was clearly function of, we didn't use any ice nuclei because we use the liquid nitrogen for all these seeding purpose. But these shapes are, we could reproduce all the shapes in the textbooks, which are given in the textbooks.
Yeah, actually some shapes are so good they can decorate your drawing room.
Yeah. But we could purely reproduce those as a function of temperature and supersaturation alone. So
But-
that is why I have my doubt whether the ice nucleating particle, whether it will have any role to play in the final shape which the particle is taking. Maybe because it is totally controlled by the temperature and the supersaturation. Supersaturation is the main thing. That is what I believe.
True.
Yeah.
And electric field also, as you have shown.
Yeah, electric field, because we have seen that there is a preferential growth in the direction of the electric field.
Yeah, there is a.
Yeah.
So as you may be aware that electric field is a difficult to measure in thunder clouds.
Yeah.
So such type of information, if it is based on a kind of tracer on the and measurements are made of only ice crystals type, then can it serve as a measurement of electrification at that level?
It's a gray area. We have to look at it. Yeah.
Well, I would like to open this interesting talk to question and answer in case some people have inquiries, they can go ahead.
Sir, there is one question, sir. Pradeep Kumar sir, nice talk. Thank you. Does secondary ice production plays any crucial role in active break phases of monsoon? Kindly comment. Unmesh Datta.
Secondary ice production, whether it plays an important
crucial role in active break phases of monsoon.
I don't think so.
Okay.
Yeah, because active break monsoons phases are different entirely. It is some other dynamics dominating it. Whether he wants to know whether it is the cloud types.
Maybe the cloud vertical structure during active and break time is very different. So that way they can go into secondary ice production height levels. Yeah,
if the heights, the cloud, the vertical growth is going more, then the secondary ice productions will be more in number.
Yes, exactly. I think he wants that clarity.
Yeah, it will be more in number. Yeah, it depends upon the vertical growth.
Yes, correct. Thank you, sir.
Any other question?
PPK sir, this is Tara. Hello,
yes,
sir. May I ask you, sir, what is your guidance for the young generation that actually that are wanting to study cloud microphysics, and now the aerosol cloud interaction is one of the puzzles that many climate models also are having difficulty. So what is your guidance to the students that are actually wanting to take up the cloud microphysics as one topic?
Yeah, first of all, still a lot of field observations are required. Okay, field sample analysis is very, very important, because so that is one region which has to be concentrated. And then understanding again from the field, you have to come back into the lab. And then get into the modeling aspect, what the model is going to finally give. But field measurements to lab are the most important. These are the two areas which still needs a lot of attention for understanding the aerosol cloud interactions. And then your large scale data analysis has to be carried out. Because I've given you the gray areas I have pointed out in the gaps in understanding. Those gaps in understanding first has to come jointly from the field observations and the laboratory observations to bridge the gap. And then we can get into the modeling aspects.
Yeah, most of the models, all these processes that you talked about, most of them use some empirical relationships that are established in the laboratory. So the point is that just don't blindly use the model. Just also look inside the model and look at how exactly these processors are described. Are there anything new that we can find or modify? Right, sir?
Yeah, that is what it has to be done. Whether what you have to look at, because most of these processes, whether they are not fully brought into the models.
Exactly.
So, yeah, so model needs an improvement from your field observations and from the laboratory analysis.
Yeah, I want to thank you, sir, for all the very nice talk and a lot of information. I think many students also will benefit from this talk and whatever is going on. Thank you so much.
Thank you.
Any other comment?
Dr. Kamra, may I ask a question? This is Ravi Nanjundaya here.
Yes, please go on.
Thank you, Professor Pradeep, for a very excellent presentation. I enjoyed it a lot. Okay, I have one question. Supposing we wanted to parameterize electrical effects on cloud ice nucleation in a model, how should we be going about doing it?
Electrical effects on the ice nucleation.
Yeah.
Because firstly, not much study has been done with that electrical aspect of ice nucleation. So, whether there is enough research that is lab data available to get into a parameterization, that is my first doubt. So, unless we systematically carry out from the kind of the electric fields observed in a cloud and the nucleation, which is because we have not systematic experiments are not there, because starting, let us say, about 1 kilovolt per meter field strength, as you keep increasing the field to a breakdown field, what happens? So that is that kind of a study is not there, and so that is the most important thing to get the laboratory data. First is the most important thing to go for a parameterization purpose. So once you have that, then with the function of electric field, whether we can go for a, because what we have found is in our laboratory experiments, even as the field, it is not just the electric field. We have also found that the drop size is also very, very important, and the liquid water content is also very, very important. That is one project which I wanted to take it up, like it was proposed by Dr. Avila from Argentina, and we had put it up as an Indo-Argentinian collaboration, but unfortunately it couldn't materialize. That is as a function of drop size and as a function of liquid water content in the cloud, because that is one observation in my 2009 atmospheric research paper 2000, which I had pointed out that at higher liquid water contents, the ice nucleation doesn't happen. So why it does not happen? So it's not just the electric field, it is also the drop sizes which are there, and also the liquid water content. Whether drop size is contributing to the liquid water content, that is still not clear. So it is still an area open for research. That is what, once we do that, probably we can bring in once we have enough laboratory experiments done, probably we can bring in the parameterizations like we do with the charging process. Does that answer your question?
Yeah, more or less. I think all I could figure out was that we still have a long way to go before we can put it in. But though I guess it's an important process that we need to put in.
Yeah, definitely, because once a lightning has, because see, once even a corona discharge happens inside the cloud, it will start nucleating.
Okay.
So because that is something which we have shown, that is even a corona discharge it can happen in the cloud, not only just lightning, but a small corona discharge happens inside the clouds, it can start the nucleation process. So that is definitely there.
Thank you, Professor Pradeep. Excellent
Yeah,
presentation.
if I can add to it, Ravi, this
Yes.
effect of electric field on the microphysical processes in clouds is so complicated that it almost affects everything. But the thing is that electrical field and the electrical charge on the different particles have to be sometimes very strong to have those effects. And it is depends upon the magnitude of the effect on different processes, like what you are saying, this nature of ice crystal growth or different types of ice crystals and ice phase, and then water drops, whether it's a collision coalescence process or breakup of water drops. It affects almost every microphysical phenomena. So, as a sum, if somebody wants to take in cloud models or this thing, it becomes a complicated whether from this point of view, that whether this process is dominating or that process is dominating. And they are not unidirectional. They can affect the process in opposite ways. So what is the magnitude of one effect over the other is, I think, it has still to be quantified. They affect, but their quantification of effect is what you require for parameterization and these things in models. That has been the difficulty.
Okay, thank you.
Any other questions? If none, we will very much like to thank Dr. Pradeep Kumar for a very detailed and a very comprehensive description of what his work has been and in laboratory and field experiments. And I'm sure our younger generation will be very much encouraged by his research work. Thank you, Dr. Pradeep Kumar.
Thank you, sir.
Now we have to go to our presentations of oral papers, and in this session we have a long list of about a dozen papers, more than dozen, and these are by our young scientists mostly and students. So what we have to follow to finish this session in time, that we 10 minutes each for each presentation. So at 8 minutes for the presentation, after 6 minutes, our reporters will give a signal that the 6 minutes are also in next 2 minutes you have to complete your presentations, and last 2 minutes will leave it for question and answer question. That's because we want to encourage this discussion session. So if earlier you can finish, that's so much better. So my advice will be not to go through detailed introduction or the process, but just concentrate on your results and what is the novelty of results in the existing position of the topic they are talking about. So is that clear? So we will begin with the first presentation by Dr. Manisha Dutraj.
Sir, sorry to interrupt. Manisha Dutraj is facing some internet issue, so she is not joining. Next presenter is Rohit Mangla. I request him to start presenting.
Okay.
Okay. Good afternoon, everyone.
Yeah, go ahead.
Good afternoon, everyone. Shall I start? Shall I
just
share my
open your slides more.
Rohit, go to open share tray. Yeah.
Yeah. Can you open it on the full screen?
Yes, yes. Is it visible?
Yeah, yeah. Go ahead.
Shall I start?
Yeah.
Okay. So good afternoon, everyone. The topic of the presentation is study of aerosol cloud interaction on precipitation system using spaceborne radars. So in figure 1, you can here there are two figures of convective clouds, figure A and figure B, and one can observe that the aerosol present in the lower portion of the atmosphere have the capability to change the vertical properties of the cloud. So and at the end they will affect the rain processes. So in this study we are working on the how the aerosol affect the precipitation system. And for that we are using spaceborne radars. Like in space we have two radars. One is CloudSat CPR, which has frequency 94 GHz, and we have GPM DPR 13 and 35 GHz. And the data of cloud and precipitation are available globally. So the objective of the study is to study the indirect effect of aerosols on precipitation cloud using radar signatures over Indo-Gangetic plains and Western Ghats region. So here we test on two cases. First case is single layer warm clouds, and how we define using cloud CPR dataset is we have applied two conditions. One is cloud mass greater than 30. It means if we have high probability of cloud detection if we took this condition, and the temperature greater than 273 Kelvin. So these conditions are taken from this Michita et al. 2014 paper, and then we estimate the liquid water path, which is 5 times of CLDR and TOCT. CLDR is the cloud droplet radius, TOCT is total cloud optical thickness, and it indicates the different life stages of cloud. Then we also test second case, mixed phase clouds using DPR profiles, and the condition for defining the mixed phase cloud is cloud reflective Z is greater than 30 decibel at 8 km, and the data period we use for 2014-2017 monsoon period. And so we constructed the contour frequency optical depth diagram, which is a function of cloud droplet radius and the liquid water path. So here x-axis represent the reflectivity, y-axis represent the integrated cloud optical depth, and top panel shows for the ACE for Indo-Gangetic plains, and B, D and F shows for Western Ghat region. And then when we classified this C of OD diagram for 3 types. So based on the CLDR and LWP. So first A and B represent for cloud droplets, C and D represent for drizzles, and E and represent for rain. So this high occurrence in this region represent the cloud droplets based on the reflectivity signature values. So for example, -25 to -10 decibel. This represent the cloud droplet signature. So when we compare the rain profiles, for example, here the in Indo-Gangetic plains there is a less signature of rain profile, but in Western Ghats there is a high signature. So it shows that warm rain is suppressed in Indo-Gangetic plains. Then we look for the statistical relationship between the aerosol optical depth and maximum precipitation rate for mixed phase clouds. So A for Indo-Gangetic plains, B for Western Ghats region. So when we compare, so when we look for this diagram, A diagram, as the AOD increases, the rainfall increases initially, then it becomes saturated. So it means, so when initially aerosols invigorate the convective clouds, but after that it suppresses the rain. But in Western Ghats region, as the aerosol increases, the maximum precipitation it increases with increase in the aerosol. It means the dust aerosols from Arab region enter the mixed phase region through warm region of shallow convective, because the Western Ghats is having large number of shallow convective clouds. So these dust aerosols will act as a efficient ice nuclei, and it contribute the ice formation, and that ice will contribute the cold rain processes. So when these cold rain processes along with the warm rain processes, it increases total rain. So that's why there is a large increase in precipitation over Western Ghats region. So I conclude my study that over Indo-Gangetic plains, aerosol suppresses the warm rain, while the cold rain over Western Ghats region enhances the total rain. And combined, like we uses two radar observation, KU and W band radar, it reveals greater potential for cloud aerosol interaction studies. Thank you for your attention. Any question?
Thank you for making it short. It's now open for discussion, question and answer.
Yeah, can I ask, sir, a question?
Yeah.
Yes.
Yeah, I am Subramanian from SPL. Rohit, good presentation. I just want to know how many profiles have been gone into the analysis, because you know that after 2014, this CloudSat is only operating the daylight mode, right?
Yes, yes.
So how you have taken care of what it is only your analysis is meant for only one certain timings only, right?
Yes, yes.
So could you comment on that?
Yes, actually, I just take only the monsoon season, and I put these conditions also. So like there are around 6,000 profiles which I have used in this first case, and in defining the six layer warm clouds. So we have sufficient data set to justify this case. Yes.
Okay, why I am telling is actually during the monsoon, where we have this rapid evaluation of the vertical structure of precipitating clouds, and time also is very important. So if you see, you can see that TRMM, all the studies where we have seen the very nice. So the CloudSat is having very less passages, but this gives the non-precipitating vertical structure of the clouds as we have presented. But good. Okay, thank you.
Thank you, sir. Thank you so much.
Can I ask one question?
Yes.
Supplementing. So you have already having the cloud satellite and also the GPM. You will have a vertical structure of the cloud for the same time. So you can interpret this whatever the temperature things you are talking, and mix it with process. From the vertical structure of the reflectivity, you can interpret much better way.
Actually, I use the vertical profile of reflectivity. This chat is going a vertical profile. And
correct. But you can plot it, and where the this radiuses you are talking, cloud droplet radius, you can infer from the both reflectivity and maybe theoretical the values of the fall velocity.
Okay. So, okay.
You don't have a droplet velocity observation, but you can interpret because you are having a radius.
Okay. So, okay. I will think in future. Thank you for your suggestion.
Yeah, thank you.
Any other question? I have one question that precipitation doesn't depend only on the aerosol present in the atmosphere. There are so many other factors: liquid water content, size distribution, and thermodynamic conditions of the cloud. So why? Your conclusions are based on as if aerosols is the only culprit. How do you distinguish that it is only due to the aerosols, except that they coincide with the?
Okay, sure. Actually, we are using the radar dataset, and for W band radar, which is like high frequency, so it can give more. It gives more information about the small radius, small cloud droplets. So which is like we can detect the aerosols also, and these kind of vertical frequency plots are mainly for to give you more information about aerosols. And we, like, your question is like cloud mass, we have not observing those things also, but like it's a kind of signature actually. So we are based on our previous literature experience, and that's why we are giving this finding as a aerosol impression, because the radar is also more sensitive to that kind of aerosols, plus and based on the previous literature experience, that's why we are giving this conclusion with respect to aerosols actually. But yes, we should, there are many phenomena happening in the atmosphere, so we cannot be assuming all these at one time. So we are assuming that all these are constant, and we are focusing on one or two components at this moment.
Okay.
This is Tara. May I ask one question?
Yes, sure.
Yeah, actually, it is subsequent to Kamra sir's question that I think any analysis you are doing with any kind of data like this, relating with the AOD and the precipitation, you have to be careful. You have to at least know you are considering the same meteorological conditions, because meteorology has a very important role there in whatever you are presenting here. So the type of cloud or whether its vertical growth, all are also controlled by meteorology, and aerosol is having a different type of effect that will be hiding within all the signature that you are getting. So it is worth classifying your data based on meteorology, similar meteorological conditions, and even the for example, when the inversion layers, strength of inversion layers, or the stability in the boundary layer, or moisture content, or whatever, you can keep different criteria and classify your data and repeat the analysis. But please don't try to do a scatter plot or between such with the parameters. It's quite a non-linear process, so it will not work out. Thank you.
Okay, thank you for your suggestion. I will look for it.
On YouTube, there are the questions that how did you measure the aerosols? CPR doesn't measure aerosols. So could you kindly answer?
Sorry, can you repeat the question?
How did you measure aerosols? No, CPR doesn't measure aerosols or aerosol number concentration.
Actually, I use MoES AOD data for this work.
For the same time?
Yes, for the same time.
Is it A-train?
Is it?
Is it a A-train observations? That means within a short time gap you are made these observations?
Yes. So yes, so I use MoES AOD data for this work.
Oh. Then area of the sampling will also be a problem.
Actually,
Sindhu is asking this question.
Okay, so so when I did this analysis, so I made all the observations in a 1 degree by 1 degree grid. So for example, so when I plot this graph, so I took samples. So I created I arranged the data set in a 1 degree by 1 degree grid over Indo-Gangetic and Western Ghats. So I use those samples only, which are overlapping with each other.
Correct, but CPR will not pass. That's what he is telling. It is not pass very frequently on the same location. So because its revisit time is 14 days for any one place. So be little careful about the interpretations.
Okay.
Yeah. Thank you.
Thank you so much.
Sorry, so far we have not heard Dr. Kerrypot, my co-chair. I'm also a little.
Hello, sir. Yeah, I can take care of.
You have any further comments or anything to say, add to our proceedings?
No, sir, I can take care of the rest of the presentations. You may
okay, go
relax
ahead.
for some time. Yeah.
Yeah, please.
Okay. So is Manisha ready?
Yeah, I think Manisha Dutraj is ready. She can present now.
Okay.
Yes, sir.
Yeah, please wait. Mr. Rohit, will you please close your presentation?
Okay, yes, sir.
Okay, our next presentation is by Ms. Manisha Dutraj, and she will be talking on tropospheric aerosols and different types of clouds. Ms. Manisha, please share your PPT. Ms. Manisha? We don't see her, right? Yeah, okay, she's. Ms. Manisha, you may share your screen.
Yes, sir.
Yeah.
If it is a mobile, you please turn it into the landscape, I think. Okay, fine, as you wish.
Sir, is my PPT visible?
Yes. Yeah.
Yes, it's
okay.
Yeah, you may start
Okay, so
now.
shall I
Yes.
begin?
Yes.
Yeah, okay. Okay. So good afternoon. My name is Manisha Dhutaraj. I'm from Department of Physics, Ferguson College, Pune. Here my project topic is tropospheric aerosols and different types of clouds. So firstly, I would like to introduce my project. So here, aerosol is nothing but the suspension of fine solid particles or liquid droplets in air. Aerosol is classified into two types, naturally occurring aerosols and anthropogenic aerosols. And there is types of clouds, that is a low level cloud, mid level cloud and high level cloud. The basic principle which I have used in this project is the twilight technique. So the twilight is the time between days and night when there is light outside but the sun is below the horizon. The morning twilight is called dawn, while the evening one is called as dusk. Here the instrument which we use to measure the aerosol number density is the semi-automatic twilight photometer. This twilight photometer consists of the telescopic lens, filter, shutter, detector and recorder. Now second thing is the formulas. Here in this case, time t and intensity I are the important parameters of twilight technique. We use this formula which is already there in the Professor Shah's paper, which is published in 1970. So we just used that formula, and by using that formula we calculated the aerosol number density by putting their di and dh values, which is nothing but the differences in intensities and shadow heights respectively at the time t and time t plus dt. So here is my result first part. So here we have the data of about 3 years, that is 2009, 2010 and 2011. This semi-automatic twilight photometer is unable to take the observations during rainy seasons. So we have the observations only for about the 4 seasons, that is pre-monsoon season, post-monsoon season, summer season and winter season. This photometer was not able to take the observations during the rainy season. So this first result part I would like to explain. For whatever the data we get by using the semi-automatic twilight photometer, we used the origin software for the further calculations. So here, aerosol number density, that is AND, vertical profiles at 6 to 7 km obtained at clear sky days preceding the high level cloudy sky days. If we observe the graph carefully from left to right, this graph is aerosol number density versus altitude graphs. If we observe that carefully, one broad peak was observed 3 days prior to high level clouds. 3 days prior, it was moving down with nearly 0.2 to 0.3 kilometers per day. At 6 kilometer, the aerosol number density is nearly about 1000 particles per centimeter cube prior to high level clouds. For other clear days, less than 300 particles per centimeter cube. Next part is here the variation in the aerosol loading Q from 6 to 7 km obtained at clear sky days preceding the middle level cloudy sky days. So here the graph, so here I have mentioned some graphs which is day number versus altitude graph. In this graph the red dot indicates the cloudy days while the black point indicates the aerosol loading. Result third, the middle level cloudy days. Middle level and low level clouds were frequently observed following with the high level clouds. It implies that the CN particles perturb downward. In very rare cases, middle level cloudy days were noticed separately after any clear sky days. Base for mid-level 2 to 6 km. An attempt was also made to study the variation in aerosol loading Q at 6 to 7 km in terms of that is aerosol number density obtained on clear sky days preceding the middle level cloudy sky days. Result 4. Here the aerosol number density vertical profiles between 8 to 12 km obtained at clear sky days preceding the contrail. Contrail is arised from the condensation trails or vapor trails, which are line-shaped clouds produced by aircraft engine exhaust. If we observe the graph carefully, this graph is aerosol number density versus altitude graphs. If we observe them carefully, we can see that at about 8 kilometers we find a broad peaks at there, and the aerosol number density is maximum, which is about 19 particles per centimeter cube. Results 5. Invisible cirrus cloud. The invisible cirrus clouds, that is optically thin cirrus layers, frequently observed. Tropopause is the layer which distinguishes troposphere and stratosphere. The thin cirrus layers extend several hundred to more than 1,000 kilometers horizontally and persist for time periods of several hours to several days before dissipating. These clouds are invisible for normal eyes. We cannot see them by our naked eyes, but by using the twilight technique, we can take the observations for these clouds, that is invisible cirrus clouds. One more attempt was also made.
Manisha, you have 2 minutes left
To study the
Please
variation.
conclude fast.
Yes, sir. Yes, sir. So one attempt was also made that variation of aerosol loading Q at 8 to 11 kilometer in terms of aerosol number density. The results pointed out that the aerosol loading at the level increased considerably prior to existence of this type of cloudy days. Here, I would like to summarize whatever I have discussed. The detailed study of aerosol number density vertical profiles in between 6 and 7 kilometer gives pre-information about the occurrence of high-level cloudy days. The sudden increase in the values of Q at any day, followed by sudden decrease at subsequent day, could be precursor of middle-level cloudy days. One or two broad aerosol layers noticed in between 8 to 12 kilometers. The increased aerosol loading in between 8 to 11 kilometers at any day is responsible to create the favorable condition for invisible cirrus clouds. However, at a present, the definite relation between the variation and tropospheric aerosol number density and weather condition could not be established with so few data events, but it is possible if a greater number of events are available. As I told before, we have a less number of data. We have approximately only 3 years of data. If possible, if we have the greater events of data, then we can definitely conclude something related to the weather conditions and the variation between the tropospheric aerosol number density. Acknowledgement. Here I'm grateful to the authorities of the Ferguson College, Pune, for the encouragement during the course of this work. Further deep sense of gratitude goes towards the DST Women Scientist Scheme, India, for providing the fellowship and funds for the development of twilight photometer and potential research work. Thank you.
Thank you, Ms. Manisha. You mentioned you did this measurement over a period of 3 years, right?
Yes, sir.
But then analysis based on different seasons. How many days of data from each season? You didn't mention anything. You are doing the measurement continuously except the rainy days, I think, right?
Yes, sir.
So how many days approximately you got from each season?
Approximately, sir, 1 month, nearly about 60 to 61 days.
From each season, you mean? Or all together?
Yes. No, sir, for each season.
Okay. Questions, comments from the audience?
I have one. This is Tara. I have one question, please.
Yeah, please.
Yeah, Manisha, nice work, but the point is that your observations, have you verified with any other observations available? For example, Calypso or any like co-located observations?
Actually, ma'am, I have not done that. I have not cross-related any observations, my observation with any other observation, because it is my project topic, and my guide is Dr. Pratibha Mane. So whatever data she is given, I have just work on that data.
That's fine, but if the instrument is more dependable, it is quite useful data that it can provide. So the validation is very much necessary before you do any research with it.
Yes, sir. Yes, ma'am. Yes, ma'am.
Yeah. Please pursue that. Very nice. Thank you.
Thank you, ma'am.
Camera, sir, you have any questions? Camera, sir.
Don't have any further questions.
Okay. Any questions from audience? Dr. Madhu?
Yeah, thank you, sir. It's a very good work, and as Tara madam already raised the point, validation is very important, especially you are bringing a very good aerosol profiles. You should have a comparison, maybe Calypso, as madam suggested already. So that is one point. And twilight photometry is also operated at IITM sometime, like Jadhav sir and Padma Kumari. You can see those publications. I think they have not done the AOD, but that is the new point with you. Good work.
Okay,
thank you.
Definitely, sir. Thank you, sir.
Okay. Thank you, Ms. Manisha. Next,
Yes,
next speaker is Lois Thomas, right?
Yes.
Yeah. Okay.
So shall I give the meeting now?
Yeah, please share the PPT. Yes.
But the other screen is already, yeah, just a second.
Yeah. Okay, our next speaker is Ms. Lois Thomas, and she will be presenting her work on diffusional growth of cloud droplets in homogeneous isotropic turbulence, scaled up DNS. Lois, you may start now.
Is my presentation visible?
Yes, please put it on full screen mode.
Yes.
Yeah.
Okay. Good afternoon. I'm Lois Thomas. I'm a PhD student at IITM. Title of my talk is Diffusional Growth of Cloud Droplets in Homogeneous Isotropic Turbulence, Scaled Up DNS. The turbulence associated with clouds is of multi-scale in nature. It can be as large as the cloud flow or as small as the dissipative eddies. The impact of turbulence on growth of cloud droplets is an important aspect, but not yet complete. That is direct numerical simulation. It is believed to be the only numerical approach capable of simulating the growth of individual cloud particles in turbulent flows. The first one to use such an approach to study diffusional growth was Wellencott in 2001, and several other people followed, several other studies were followed, but all of them were limited by the computational domain size. Recent studies have shown that impact of supersaturation fluctuations on the spectral width increases with domain size, which means the largest eddies are the key for condensational growth. Making use of this argument, we propose a new methodology new approach called scaled up DNS, which is similar to the traditional DNS but can reach significantly larger spatial scales like tens and hundreds of meters. This work has been published and the details are on the slide. Objectives: to develop a modeling approach similar to the traditional DNS but capable of reaching significantly larger spatial scales that is comparable to the LES grid volumes. Second one, to use this to study diffusional growth of cloud droplets in larger domains, that is a domains that is not currently possible with the real DNS. Methodology: the base code is from Kumar et al. It's the same as the one used in Kumar et al. 2018. This is a spectral code with evolution equations for velocity components, temperature, and water vapor mixing ratio. These Eulerian fields are coupled with Lagrangian droplets. I have written the equation for temperature fluctuation on the screen, and we have on the slide, we have added the additional term at the end, which is the feedback from the vertical velocity fluctuations. And the last but one term is the feedback from condensation rate. And the equation for condensation rate is also given on the slide. This is calculated for every single droplet, and then it feedbacks the temperature and water vapor evolutions. Then comes the scaled up DNS. The main idea is to increase the domain size without changing the number of grid points. Now, in traditional DNS, the grid length has to be close to the Kolmogorov microscale. But for this study, our interest is in the larger studies of the domain. So we increase the domain size, keeping the grid points same. But the key point is to scale up the molecular transport coefficients. So I've given the equations and how we arrive to the scale-up relation for the viscosity. Nu is the viscosity, 2 stands for the scaled-up domain, and 1 stands for the real domain. And the same way, we will scale up the thermal and vapor thermal diffusivities as well as the moisture diffusivity. And once we scale up this way, we expect that the TKE, which is given as E on the screen, the TKE scale up according to this, TKE also scale up according to this relationship, the second one. Now that was about the scaling up of the domain. Once we have a larger domain, we will have billions of droplets to be given into the domain. To follow each of this droplet is not computationally possible with the resources available now. So what we do, we replace the real droplets with something called super droplet. This was a concept introduced by Shima in 2009, and the additional multiplicity attribute marks the number of real droplets represented by a super droplet. Now the equation for condensation rate calculation is given. The difference is the multiplicity attribute. And this approach, super droplet approach, was first tested in real DNS and then applied in scaled up DNS. Modeling setup, we used a 256 cube DNS and initial monodisperse distribution. Other details are on the slide. Now, we conducted several simulations with droplets and without super droplets. On the screen, I have given details of 5 scaled up domains starting from 2.56 meters to 64 meter. The first column is the domain size, domain length. Second one is the grid length. Third one is the scaled up viscosity value. Fourth one is the TKA that is obtained from the simulation. Then comes the super droplet NS. As you can see, it is in millions. And then there is multiplicity. So the total number of droplets, real droplets in the domain, will be a product of NS and mu. And then the number of droplets per volume, grid volume. Now I'm only showing few important results. The first one is comparison of energy spectra for real and scaled up DNS. This result is from 4 scaled up domains from 0.256 meter to 256 meter. The plot on the right side, that is the red one, is the energy spectra for the real DNS. Towards the left, the plots for scaled up DNS. As you can see, when it shifts to the spectral peak shifts to the left and its value increases with the domain size, keeping the -5/3, preserving the -5/3 slope, -5/3 slope. So the scaling up accurately predicts the energy at large scales.
Lois, you have 2 minutes left.
Yes.
Please try to conclude fast.
Yeah. So how do we know that this is from the TKE plots? This slide shows the TKE plots. The first 4 panels on the upper panels show the TKE evolution. The horizontal line is what we expect from the theory. And the bold line is what we get from the model. As you can see, they match really well. Now, the second panel shows that the dissipative rate is forced and it is maintained. So the scaled up DNS with modified viscosity produced the expected TKE. Now, once we have this scaled up domain, we have to introduce a super droplets. So here we analyze the standard deviation of supersaturation fluctuations. Now, as you can see, as the domain size increases, the supersaturation fluctuations also increase. And we have done this for different multiplicities to just check the robustness of this method. So results suggest that the multiplicities selected for the scaled up DNS provide robust outcomes. This one is the standard deviation, radius squared standard deviation. The standard deviations increase in time as t to the power half. That is what we expect from the theory and stochastic models. And for larger domains, the spectral width reach values up to 1 to 2 micrometer. The error bar is for different multiplicities and it is negligible. Errors are very less. Now, this is comparable to those observed in near adiabatic cores, small cumuli or subtropical stratocumulus. To conclude, we have developed a modeling approach called scaled-up DNS, which is similar to the traditional DNS but can reach significantly larger spatial scales. This was done in two parts, first by increasing or scaling up the turbulence and then by introducing super droplets. This study extended the validity of scaling relationships obtained in previous studies and also exhibited the spectral broadening. This is also being extended to activation studies. Now, scales of atmospheric motion has a wide range and it can be of thousands of kilometers to the millimeter scale. And we have modeling approaches suitable for each of these regions. Now, scaled up DNS falls in that region of LES grid volume. So we hope that this method can help in improving the subgrid scale representation of cloud precipitation in cloud microphysics and precipitation in numerical weather and climate prediction. Thank you.
Okay, thank you very much for your presentation, Lois. Open for questions, comments.
Yeah, it's a good presentation, Louis. I have one question, sir. Can I ask Anand, sir?
Yeah, please.
Yeah, this cloud to means whatever you are doing the turbulence, roll up the turbulence. How much is the time you expect that after turbulence initiated collision corrosion frost, purely the warm clouds, how much time it takes to become a raindrop?
In this study, we have only considered the condensational growth because in the first slide, in the introduction, we said that we make use of the argument that for condensational growth, largest eddies are the key. So as the initial part, we have only considered the condensational growth, not the collision coalescence processes.
Okay, for a condensational growth, how much time it took for you from the before to after condensational growth happening? How much time it required?
Required for?
To become a condensationally grown the cloud particle.
So the initial droplets are itself cloud droplets of 13 micrometer, and the simulation was run for like few, you can say 250 seconds or more than that. But it is already, it's not CCN droplets, it is already cloud droplets, and it has grown in that time. So the domain itself is in supersaturation. Initial condition is such that it is in supersaturation. So as soon as the simulation starts, the droplet starts growing.
Okay, thank you.
May I ask one question? This is Tara.
Yes, please.
Lois, you have shown the spectra from all your simulations from the small domain to 60 plus, yeah. So here you show that the spectra is dropping off drastically for all the simulations. So how will you, for example, the magenta, from three of these spectra, indeed, they are not realistic, right? So it is dropping off because you are only considering the super droplets in those.
Yeah, they are dropping off because we have scaled up the viscosity. So the active spectra of the largest one, that is the magenta line, should actually start from its point to till the red line. Like it should be like that. But but here.
So is it right to show the drop off for all those three runs? I think you only need to show the red one so that it is actually following the minus pi by 3 slope, the remaining, isn't it? Yeah. And how did you arrive at that 62, right? 64 meters. How did you arrive at that domain? Why you did not go further?
For this, the particular spectra which I have shown, we have gone up to 256 meters. This is 64 meters, yeah. But with the droplets, we have checked only up to 64. But without droplets, we tried till 256.
Okay. So what is your future plan? Like, do you plan to take it to the LES domain or from here?
Yes, we would like to use the results, but first I will have to. Now I have done only with monodispersed droplets without activation. So first I have to include the cesium activation and aerosols into the scaled up DNS. Once that is done, then I can move to LES. Take this to.
You are not considering the droplet evaporation in here, or it is there, right?
It is there. Both condensation and evaporation is there.
So your spectral width you mentioned it should be more, right, in such regions. Anyway, you mentioned 2. I think
yes.
Mentioned as 2. Oh.
1
yeah.
meters, yes.
Yeah.
I'll have to look into that.
Yeah, I think you should have a look at that where evaporating regions where maybe spectral width will be more. Yeah.
Okay. Okay.
Yeah.
Okay. Sure. Any other questions, comments? Okay. Okay. If no more questions, let us move on to the next speaker. Lois, please close your screen. Our next speaker is Mr. Saurabh Patil.
Sir, shall we go for a lunch because old means Kamra sir may have to have a food. Okay. Lunch is getting late.
Okay, okay. So no,
and we'll close now and 2:40 we'll join.
Okay, that's fine.
Is it okay to all of you, please? Because senior colleagues has to take food.
2:40.
Okay. Yeah.
We start at 2:40, right?
Yes, yes, sir.
Okay. So Saurabh, you please. Yeah, we will start your lecture at 2:40. Okay.
Sure, sir. Yeah, please. Thank you very much. Thanks for your cooperation.
Okay, everyone, please join back at 2:40. Thank you. post-lunch session, we have 13 lectures to go, and we are already running late by nearly 1.5 hours. So I request everyone, all participants, to stick to the time strictly. Okay. So the first presentation is by Mr. Saurabh Patil, and the title of his talk is Sensitivity Experiments with Surface Temperature and Impact on Cloud Processes Using Cloud Resolving Simulations. Saurabh, please start.
Thank you, sir. Good afternoon, everyone. My name is Saurabh. So the motivation behind this study was that typically surface temperatures were not available, and they are either taken from large-scale model or estimated from observations of energy budget. Or in other hand, we have also seen the warming trend all over India in recent few years. So it would be very interesting to see what are the impacts of surface temperatures on cloud processes. Now for this particular experiment, I have used a cloud resolving simulation, and to validate that simulation outputs, I have used the KIPEX data, which was taken long back in 2011. So these, just please excuse. Yeah, so these are the coastal observations near the Vijayawada, which I will be referring hereafter, and these are the inland observations. So a modeling study was indeed required to address such kind of questions. So because modeling study provides us the four-dimensional fields of meteorological variables, so that we can study the details of numerous operative. So for that modeling study, I used a cloud resolving model. So it has a horizontal resolution of around 1 kilometer. So it can explicitly simulate the convective processes. So therefore, we can try to understand the convective cloud related transient motion involving water phase changes in the atmosphere. So for this experiment, I obtained the surface temperatures of around 301 Kelvin for coast and 303 Kelvin for inland from the ERA interim dataset, and then I increased the surface temperatures from 301 to 311 Kelvin for the coastal case and 303 to 313 Kelvin for the inland case. These are my model. These are my model inputs. So first, to validate my model outputs, I used a KIPEX data. Here in these diagrams, you can see I have plotted cloud water content, droplet number concentration, and effective radius over both the domains. The green dashed line shows the mix, the mean profile and the standard deviation, and the purple dotted line shows the maximum profile of the model outputs. And the blue dots are the in situ observations. You can see that in situ observations are very nicely captured by the models in both cloud water content and droplet number concentration. However, it seems that effective radius is slightly overestimated by the model. But actually the fact is that usually the aircraft observations are carried out during initial growth phase of the cloud. So that's why the effective radius measured by the aircraft is usually little bit smaller than what is expected. So to summarize, we can go ahead with our model outputs to draw our conclusion. So the most interesting thing in this study was that with increasing surface temperatures, we observed the increasing accumulated precipitation, and it was even more exciting to see what are the meteorological, what are the microphysical parameters or the ice hydrometeors which are responsible for this increase of accumulated precipitation. So for this purpose, I then looked at the updrafts. We all know that when we increase the surface temperatures, it will increase the low level instability, which will help the updraft to get strengthened. So that is what we have seen here. These are the surface temperatures which I have plotted on x-axis. You can see the strength of updraft increase with the surface temperatures and over both the domains. However, the updrafts over the coast was slightly stronger than that of an inland. So in this diagram, you can see I have plotted cloud water content, cloud droplet number concentration, and effective radius. First thing we note is that if surface temperatures has increased the cloud depth. You can see it has increased in both the domains. Also, it has elevated the cloud base. And most interesting thing to note was that the effective radius was found to be very weakly sensitive to the surface temperatures. What I mean is that you can see the effective radius in initial temperatures and in after very high temperatures, there is not much a difference. So I think that warm rain processes must not be contributing to that enhanced accumulated precipitation. Now to delve deeper into this aspect, I looked at cold cloud microphysics and I found that I have plotted this ice content, snow content and the Graupel content, and I found that it was increasing with the surface temperatures. So it was very exciting to see, and this increase was in both the coastal and inland domain. However, the coastal domain had slightly higher mass as compared to the inland domain. Now, I also looked at the number concentration of these ice hydrometeors, and I saw the number concentration was also found to be sensitive to the surface temperature. One thing I forgot to mention, you please note this very high ice content, snow content and Graupel content at this temperature 309 and 311 Kelvin. It will be used to, it will be helpful to address the rainwater, rain microphysics. See there, the rain microphysics, we can see at 309 and 3011, it is very high, the rainwater content. So the surface temperature increased the rainwater content, and also it was saturating more close to the freezing level. So we might
Saurabh, you have 2 minutes left. Please wrap up soon.
Yeah. So to conclude, this enhanced rainwater mass and rain droplet number must be originating due to the melting of ice hydrometeors, which we previously observed. So this was very interesting result which we have found due to in surface sensitivity experiment. Now to conclude or summarize, we have seen I have seen the precipitation increase with increasing surface temperatures. Surface temperatures have a profound impact on low-level instability, which further impact the strength of vertical velocities, cloud base height, and cloud depth. The effective radius, or in other words, warm rain, showed very weak sensitivity towards the surface temperatures. However, the cold cloud hydrometeors were responsible for the enhanced precipitation at the higher surface temperatures. So the importance of this study is that a change in surface temperatures indeed modify the conditions favorable for the deep cloud development and prevalence of a mixed phase processes. So surface temperature is indeed one of the very important aspects which needs to be considered during all of the studies related to these two things. So these are my references, and I thank you organizers to giving me an opportunity to present our works. Thank you so much. Hello.
Saurabh.
Yes, sir.
No, just one clarification. The simulation, the results you presented are from how many hours of simulation for each case of increased temperature?
Yes, sir. For each temperature, I ran the model for around 15 hours. And I also took the time average of all those variables, 30 minutes time average, to show all the variables which I have plotted.
Okay. Yeah, now it's open for questions. We have 1 or 2 minutes.
Yeah. One comment I have.
Yeah, please, sir.
Sure, sir.
Yeah. This is a good attempt to relate, but keep in mind that surface temperature only is not the factor, but it's the vertical instability which is more related with the formation of clouds and its microphysics. So surface temperature, of course, it can affect the vertical stability, but in different seasons, the effects may be different.
Yes, indeed. I completely agree with you, sir. And my only point was, or my motive was to know the impact of particularly the surface temperatures, not considering any other thing. So that is what I have tried to show.
Yeah, direction of work is very good, but just keep, keep thinking and expanding your work in taking account of other factors.
Sure, sir, definitely.
I do agree with the JRK, Kamra sir, that you have to quantify the surface temperature role in this increase. There are many factors, but you have to quantify. Yeah. And have you done any quantification and validation?
No, sir, not yet. I have not quantified, but I will definitely look forward to do that aspect also.
Right. Another thing, you assumed that if your freezing level constant, but it changes with the different season.
It is not constant. If you look very closely, maybe I will try to zoom out. You know, it's slightly changing. You know, very slight change.
Okay. And one more thing, updrafts and downdrafts. So as to be need to be verified. That is very important actually. For that, winds are very important.
Yes.
Yeah. Thank you. Good work.
Okay. Any other questions? Okay. If not, thank you very much, Saurabh, for your presentation. So we move on to the next one. Please. The next presentation is by Ushnanshu Datta.
Yes, sir.
And the topic is role of cloud hydrometeors in Indian summer monsoon rainfall predictability.
Yes, sir.
Please share your PPT and start.
Sure, sir. So is it visible?
Not yet. Yeah. Please put in full screen mode and start.
Okay, sir.
Yeah.
Okay. Good afternoon, everyone. So I'm going to present role of cloud hydrometeors in Indian summer monsoon rainfall predictability. So these are my objectives. So what is the variability of cloud hydrometers in different time scales? The synoptic 3 to 7, QPM 10 to 20, and MESO 30 to 60 day. And what is their interseasonal relationship between cloud condensate, convection, and circulations? And whether the subseasonal variance of cloud condensate are predictable. And we'll be seeing in the model perspective. So these are the data and methodology. I have used these variables and data, and they have been taken for various analysis and observational sources. And these are the short methodology. I have used filtering using the Langos filter, lead lag correlations I have performed, and methodology regarding one plot we will show later that has been adapted from the Shah et al. 2019 study. So first I have seen a global picture of mean rainfall and distribution of cloud hydrometeors. And here in today also lectures in Thara ma'am and Professor PPK is also showing the importance of ice phase processes. And here if we look into the cloud ice mixing ratio, this is the average of 30 years climatology, and this is the cloud water 30-year climatology. And here is this side is the pattern correlations. So here you can see that pattern correlation with the cloud ice and rainfall is more as compared to the cloud water and rainfall. That is true for global tropics as well as for EIMR. Even satellite observations, they also show that in Indian summer monsoon region, 40 to 50% rainfall events originate from the melting of ice. So cloud ice is important for monsoon. So now let's look into the variance of rain and cloud hydrometers in different subseasonal scale. So the rainfall variance has been well studied in different literatures, it can be found, but looking into the literatures, we have found very limited studies regarding the variance of cloud hydrometers, that is cloud ice and cloud water as well. And here you can see that cloud ice and cloud water both have significant variance in synoptic, QPM, and MESO scale. And one interesting point to note here, the variance of cloud ice in all the scales are more as compared to the cloud water. Now, what may be the reason between this to get such a high variance of cloud ice in this synoptic scale? The reason may be found from this literature that we have shown a picture from the IMD Cyclone Atlas 1981-2010, where all the lows and depressions and their propagations are pointed over here, and you can see here majority of these lows and depressions are forming over the Bay of Bengal, and they are moving towards central India. And this synoptic scale activity may have a stronger vertical velocity, which will uplift more moisture below freezing level, and it may form super cool cloud water and cloud ice via several microphysical processes. Now going into the other scenario, that lead lag, how the cloud ice propagation. So we have just shown here the central Bay of Bengal, they are originating over and they are propagating through central India. Now here I have plotted the lead lag composite of synoptic cloud ice anomalies and rainfall anomalies are in contours and cloud ice anomalies are in shaded plot. So this is the maxima, which is denoted by lag 0, and these are the before 2 days lag -2, lag -1, and these are the next 2 days lag 1 and lag 2. And here you can see this is the maxima point, and a clear westward propagations you can note here, that over this Bay of Bengal box and over the central India box. If you look into this picture, you can see a clear evident westward propagations. And looking into this maxima point here, this contour maxima is for the rainfall and the shaded maxima is for the cloud ice, and they does not they are not concentric. So we can say that cloud ice here, they are leading the rainfall events. Now what may be the background process and what is the link between the cloud, convection and circulations? For that we have taken the Euler, which is a proxy for convection, and here we are putting the lead lag correlation -30 to 30 days window. This side is Euler leading and this side is cloud ice or cloud water leading. Cloud ice is in black lines and cloud water is in red line. And here you can see during the Euler leading part, the correlation coefficient, which is supposed to be negative, and all are 99.99% significant or more. So here you can see that it is first showing a peak here around 8 days, and then with the cloud water it is showing a peak around 5 to 6 days. But interesting results happens with this cloud ice. It first shows a peak around 2 days, 5 to 6 days, and then it drops. And when the cloud ice and cloud ice is leading here, you can show another drop and a maximum negative correlation with the Euler around the leading of 2 to 3 days. Now going into the other segment, that is a zonal wind 850 HPA, which may taken as a proxy of the circulations as mentioned in the Joseph and Sijikumar 2003 study. So we have again plotted the correlation with the cloud condensate with the U850 over the Bay of Bengal box, and here you can see one peak around the 3 to 4 days. Now they found that Euler over Bay of Bengal, they can strengthen the circulation in 1 to 2 days lead. Now we are finding the background process of it. So what is our conclusion from this slide? That convection increases CI. So you can see here a negative correlation first peaking over here, and then which can further deepen the convection. So which is shown over here, and which can in turn strengthen the circulations. So this is we can say that this is the background process which is occurring. Now going to the next part, that is, can we predict the subseasonal variance of cloud condensate on a seasonal time scale? If we follow the yesterday's lectures in this conference, so people are talking about the seasonal prediction and seasonal forecast, which is doing, and so let us see that whether we can contribute to this part or not. So it has been believed that significant part of ISMR is unpredictable due to the strong influence of subseasonal variability, which are chaotic in nature. But a recent study by Shah et al. 2019, where they have shown the synoptic variabilities, this is the synoptic variabilities are well correlated with the mean rainfall. It shows around more than 0.6, and side by side they are correlated with the ENSO. And this is NINO 3.4 SST. They are correlated with the NINO 3 SST region also, so which are the global predictors. And if we follow the Chandy-Shukla hypothesis, so these are the basis of the seasonal predictions. And Shah et al. 2019, they concluded that the synoptic variability, which contributes about 25 to 30% of the total subseasonal variance, is predictable, and this ENSO has a stronger relationship with the synoptic variability than that of the MESO. So these are the synoptic variability averaged over the central India, and they have been correlated with the global SST for the oceanic region and 2-meter air temperature for the land region. So this is for the less than 6 days periodicity, and this is less than 15 days periodicity. And in both of this picture, you can get a canonical ENSO picture. So we can hope that this synoptic variability, they are associated with this global predictors like ENSO, and it may increase our seasonal prediction skill. Now looking into the cloud hydrometers, so they have done with the rainfall, and now our target is to whether this cloud hydrometers which may show how their association with this global predictors. So here I have plotted the cloud ice, and this is for cloud ice, this is for cloud water. So same cloud ice variance. And
you have 1 minute left. Please conclude.
Okay, sir. So we can see here the good correlation, and this ENSO is also having a good correlations, and that is also shown here. And here you can see one equinolar pattern, and here this variance is showing one canonical ENSO pattern. Now what's the status in model? So if you look into the model, this is the control run. So here this teleconnections which is observed here, they shown a opposite relationship, and in our modified microphysics scheme we get a remarkable improvement in this modified microphysics scheme, which may lead to the more skill. So this is the MPHI. It can also, this is a modified scheme which can also depict the westward propagations, and control it was opposite, and modified microphysics are in line with the observations. So these are my conclusions. So here synoptic is important, is in line with the rainfall variance, and here in the schematic I have shown here, this is the ENSO, which is synoptic scale is interacting with the cloud ice. It is a deep cloud, and this interseasonal scale it is interacting with the cloud water, and this is the equino, which is also influencing the synoptic scale cloud ice, and which is also important for the rainfall prediction. And the sensitivity model simulations using CFS-V2 with modified microphysics clearly demonstrate the support of the model development activity based on the new observational findings. So these are acknowledgements, and I thank my project director of IITM Pune and IMS Pune chapter for giving me opportunity to present, DISS for SPPU for my registration of PhD, and Minister of Earth Sciences, Protush and Aditya HPC, and friends and family. Thank you for your attention.
Thank you, Usnanshu, for your good presentation.
Thank you, sir.
Open for questions, comments. No questions. Okay. Thank you, Usnanshu, again. We move on to the next presentation. Please close your screen sharing. Okay. Our next presentation is by Dr. Suvarna Fadnavis, and she will be talking on elevated aerosol layer over South Asia versus the Indian routes. Dr. Suvarna?
Yes, can you hear?
Yeah, yes, please share your screen.
Yeah. Yes. So, are you able to see the screen?
Yeah, please share your PPT and stop.
I did that.
Not yet.
So, yeah, I'm sharing my screen. Is it visible to all?
Not yet. It is yet to come.
So, is it okay now?
Yeah, it's coming. Yes.
Yes.
Yeah.
Okay.
Full screen, please, and start.
Yeah. So, yeah, I have to share in a full screen mode. So today I will talk something different than a previous presentation. Here I take a new concept that we say that during the monsoon season, convection lifts the aerosol from the boundary layer and it forms a layer in the UTLS, that means upper troposphere and lower stratosphere, and that then affect the monsoon circulation and clouds below in the troposphere. So some small introduction, I will go very quickly. Here this figure shows that during the monsoon season, aerosols and trace gases are lifted by the monsoon convection, that is clouds, in the upper troposphere. And this latest paper by Livid et al. Says that although 2/3 of these aerosols are removed by the monsoon wave scavenging processes, 1/3 of them are managed to transport upward, and they form a layer in the anticyclone, just below the anticyclone. This is a figure from Parker et al., which says that majority of aerosols are their outflow occurs around 12 kilometers, but part of them are further transported into the anticyclone and they form the layer. So trajectory analysis shows that 2/3 of these aerosols come from the South Asia and 1/3 from East Asia, and very small amount of this aerosol which form aerosol layer in the UTLS are from the rest of the world. So now this is not only the hypothesis, but Calypso measurement also shows that there is a layer of aerosol in the UTLS around 14 to 18 kilometers, and this is quite every year during the monsoon season. It occurs over the Asian region. It is quite well spread over the Asian region, covering India and China. And our we have used ECAM6 HAMOS simulation, and our model simulation also shows this layer in the upper troposphere and lower stratosphere, and this is distribution of BC and organic carbon, and we can see there is existence of these aerosols in the UTLS. We have taken the measurements of aerosol backscatter at Nainital in 2016 during the monsoon season, and this is a figure from balloon measurements taken at the Nainital during the monsoon season, and it clearly shows a layer of aerosols around 140 to 100 HPM is in the UTLS, which is also seen in Calypso and our model simulation. So in order to understand the impact of this aerosol layer, we have made model simulations. We have used ECAM5 HAMOS model. It is an aerosol chemistry climate model. It has all aerosol properties. Aerosol module is HAM, MoES has all gases, and we have used it at 1.8 by 1.8 degree resolution and from surface to around 80 kilometer, and we have used ACMEP emission inventory. We performed 2 simulations with aerosol and without aerosols, and during El Nino year and non-El Nino year. And for observations, we have used Calypso data for the period 2006 to 2016. So this is figure from Calypso backscatter, and right hand side is from the ECAM6 HAMOS simulation, ECAM5 HAMOS simulation for the year 2015 top panel, and we can see that aerosol backscatter shows high concentration, mostly concentrated over the Indian region during 2015, that is an El Nino year, and which is well simulated by our model. But during non-El Nino year, it is quite well spread in the anticyclone, which is also simulated in the model simulation. So we see that dynamical changes which occur during El Nino time, this aerosol mostly are concentrated over the Indian region, and this layer is quite thicker and mostly densely situated over the Indian region. So we want to know what are its impact. So this is another figure from model simulation, again showing aerosol extinction. It also shows the aerosol layer over the Indian region. This is for the control simulation, and this is for the El Nino simulation. And we can see that during El Nino simulation, this aerosol layer is quite well spread, and supply of aerosols to the UTLS mostly occur from the East Asia, that is from the Chinese region. And this is difference between control simulation and El Nino, and we can see that during El Nino, it is mostly situated over the Indian region, 18 to 90 degree.
Madam, your first slide is only there. All slides we couldn't see.
Your slides are not moving. We are still looking at your second slide.
I don't know what is happening. Can you hear me?
Yeah, yeah.
Now it is moving. Now it has changed.
Now it is there.
Okay, this slide. Okay, when I made a slideshow, it is not showing. Okay, could you see this slide?
Yeah, now it is moving. Yeah.
Yeah,
Okay,
then can you make that 100% to maybe 150%?
Okay, I'll keep like this. Is it okay? Is it okay?
Yeah, we don't see the
bottom is cutting. Bottom
part we are not able to see. The figure caption and all not coming.
Yeah, you put 100 only.
Oh, sorry. Okay. Okay, now is it okay?
Yeah.
Hello?
Still it is cut off. Anyway, you please proceed.
Okay, so at least figures you can see, right?
Yeah.
So this is a aerosol extinction from the model simulation, and we can see that this is for the control simulation and this is for El Nino simulation, and we can see that during control in the control situation, means a normal year, we see that aerosol layer in the UTLS over the Indian region. But what happens in El Nino year, supply of aerosol mostly occur from the East Asian region to the monsoon anticyclone, and which makes it more thicker and wider over the Indian region. This is then we have analyzed all aerosol species, and I have shown here the distribution for black carbon aerosol as a representative. And we can see that during control year, control simulation means normal year, there are two branches which supply aerosols in the upper troposphere. One is rising from the South Asia and another rising from the East Asia. But what happens during El Nino year, because of subsidence over the Indian region, this branch become weaker, Indian branch become weaker, and supply of aerosol mostly occur from the East Asian region to the monsoon anticyclone. And difference between control and El Nino year, we can see that during El Nino there is a stronger aerosol layer, mostly densely concentrated over the Indian region. So in order to understand this impact, what we have done, we have taken an offline model where we have accounted only aerosol layer in the UTLS, and we have not accounted the aerosols in the troposphere. So our model, and we have taken the difference between El Nino minus control simulation, and we see that because of this aerosol layer, there is significant cooling over northern India here, and we have then also analyzed the solar flux reaching at the surface, and figure C shows that this aerosol layer has blocked the solar flux reaching at the surface. We have also analyzed the Brunt-Väisälä frequency. So anomalies in Brunt-Väisälä frequency shows positive, means it indicates that because of reduction of solar radiation reaching at the surface, it has increased the stability of the troposphere. And this figure D shows the heating rate anomaly, and we can see that this complete troposphere over the Indian region, even in fact the South Asian region is quite cool, and we know that increasing stability, cooling of the troposphere, cooling of the surface temperature inhibit the monsoon processes. We have also given the detail in our paper that it decreases the Hadley circulation, it decreases the cloud formation processes. This is a figure showing the anomalies in rainfall, precipitation for simulation without aerosols, means El Nino minus control, but there are no aerosols in the model, and we see that El Nino itself produces the less negative rainfall anomalies over the Indian region. But when we switch on the aerosols in the model, again El Nino minus control, we analyze and we see that aerosol has further decreased the rainfall over the Indian region. So in a brief, we have shown here a schematic. We show that during normal year there are aerosol in the troposphere, there is an aerosol layer in the upper troposphere. But what happens during El Nino year, because of dryness?
Please try to conclude soon.
Yes, this is last slide. Because of El Nino dry year,
still not moving, I think.
are you able to see the schematic?
No, we didn't see the schematic.
Actually, now? Can you see now?
It's not the schematic, right?
Yeah, last one is the schematic. Can you see now? Oh my God.
What we see is the seasonal mean precipitation anomalies.
Below that is a schematic.
Okay.
Is a figure where my cursor is there.
Okay.
Okay, so red here shows higher aerosol during El Nino year, and during El Nino there is transport of aerosol from the East Asia, which are then transported further eastward over the Indian region, and which forms a lead over the Indian region, which is thicker and wider, and which inhibit the solar radiation reaching at the surface. It causes cooling of the surface. A complete troposphere is cool, and it increases the stability of the troposphere and decreases the rainfall over the Indian region. So in a nutshell, we say that these aerosols which are lifted up by the monsoon circulation itself form a layer, and which then produces a feedback of reducing the rainfall over the Indian region.
Okay, thank you, Dr. Suvarna. Open for questions, comments.
I don't know, sharing of screen was because of.
Sorry.
Yeah, camera, sir, please.
Yeah, Swarna, of course, you have considered the transportation of aerosols from lower atmosphere and from upper atmosphere also. But do you consider the new particle formation, since your trace gases and organics are being pumped up at those temperatures? New particle formation may be there?
Yes, yeah. Our ECAL6 HAMOS model has all processes, new particle formation, organics, inorganics, all kind of aerosols, 7 log normal modes of aerosols. Here, when we switch on the aerosol and switch off the aerosol, we switch off all the aerosols, means primary and secondary both. So these are the impact of total aerosols. So there can be study which can be we can do different simulations, and where we can selectively switch off some aerosols and see the impact of secondary aerosols.
Right. Thank you.
Okay. Any other questions? Okay. Then thank you, Dr. Suvarna, for your good presentation, and we move on to the next presentation.
Thank you, sir. Thank you, Dr. Kamra.
Thank you.
The next presentation is by Dr. Divya Surendran on the study of cloud condensation nuclei behavior in relation to fog occurrences. Divya? Yeah, she is closed. Divya, you may share your PPT and start the presentation.
Okay, sir. 1 second. Are you able to see my PPT?
Not yet.
Not yet. Now?
No.
So now is it visible?
No, not yet.
So can you hear me?
Yes, we can hear you, we can see you, but not the PPT. I hope you are clicking on that share content.
Open share tray.
Open share tray.
Yeah. Divya, are you there? I think she has a connection problem. Shall we move to the next one and come back to her later? Dr. Madhu?
Yes, sir. Yes, sir. Please go ahead, sir.
Miss Sneha, are you ready? Sneha Sunil, are you ready for the presentation? We don't see her here, I think. Divya has come back. Divya, are you trying to share the screen?
Or otherwise, maybe we can go for Kandula. No.
Divya is trying to connect, but
please click open share tray. Please unmute your mic first. Yeah. Click open share tray.
Yes, sir, I have done that.
Yeah, then
you choose
now
the
is it able to see?
Desktop, yeah. You click desktop and
No, open share tray, when you press, there is a window will open down. That window you have to select and hide
Is it okay, sir, now?
No,
not
click,
yet.
click on, click on the window, click on the square inside, then share it. Yeah, now
So can you see my screen now?
No.
Actually, after open share tray, you will get something down that you have to select.
share it?
Yeah, now something is coming.
Yeah, it's coming.
Yes, now you are right. You are there.
Yes.
Okay.
Yes, you make it full screen now.
Is it okay, sir?
Yeah, please start. Yes.
Excellent, continue.
Okay. Good afternoon, everyone. I am Divya Surendran. The title of my topic is Study of Cloud Condensation Nuclei Behavior in relation to the fog occurrences over Delhi. The objectives of my study: analyze the variations in cloud condensation nuclei in different dense fog events. We have considered the fog events which were the visibility reduces to less than 1,000 meter and it reaches up to 50 meter or less. Second one, understand the role of total CCN number and relative humidity in the visibility reduction during the dense fog events. Data and methodology. Here I have taken the fog observational campaign data, WIFEX data at Indira Gandhi Airport, Delhi during the winter season. The fog events I consider for this studies are dense fog events. There are three major fog events happened in 2016 January. Then the data used, tower data for relative humidity, DMT CCN counter data, and fog analyzer data, also transmissometer data for runway visibility range. So this shows the variations in the size distribution of CCN in all three events which I considered for the study. Here we can see the CCN which are having a size of 1.5 to 2 micrometer, which their number are more during all the three dense fog events, and it is followed by the other type of particles which have a size 2 to 2.5 micrometer. And if we see the complete spectrum, we can see the most of the particles from 0.75 micrometer to 4 micrometer are mostly present in the during this period, and the CCN which have a particle size more than 4 micrometer, which has a very less value, means if we see the table, it is the total of the CCN which have a size more than 4 micrometer. It is coming even in less than 100 in number. Now, the first fog event of 7th to 9th January 2016. This figure shows the hourly variation of CCN and visibility. Visibility here I have taken runway visibility range and relative humidity. Here we can see whenever there is a good visibility, the value of CCN and the relative humidity are comparatively low before commencing a fog event. So here the first dense fog event starts nearly at 7th of Jan, 13th hour in the afternoon. So here we can see before the commencement of the dense fog event, here there is a sharp increase in the cloud condensation nuclei. Associated with there is a sharp increase in the relative humidity also, and this is this pattern we have observed in the continuous next fog event also. So here also we can see before the commencement of a dense fog event, there is a sharp increase in cloud condensation nuclei associated with relative humidity. This is seen in the third fog event which happened in the 30th to 31st January. The similar type of observation we have found. So the conclusions are like among different sizes of cloud condensation nuclei, maximum contribution towards the total CCN is mainly from the particles which are having a size between 1.5 to 2 micrometer, followed by the size 2.5 to 3 micrometer. Particles which are having a size more than 4 micrometer are showing very less influence in fog events, and their contribution towards the total CCN also very less. RH are increasing in initial stages of the fog development and showing a very high value throughout the fog event. Before the commencement of a fog event, the number of concentration of CCN is found to be sharply increasing to a high value. It is providing the surface to the water vapor to condense on it. Once the condensation begins and the fog starts to form, the CCN number is found to gradually decreasing. This may be due to the CCN particles are utilized for the formation of fog droplets and they are getting removed from the atmosphere. So, thank you. That's all.
Thank you, Divya. Open for questions, comments. Yes, sir, please.
Go ahead.
Camera, sir, please.
Yeah. I have one very trivial question. Why do you go for CCN concentration? Why not for aerosol concentration?
Total aerosol you are telling?
Total aerosol.
So for this campaign, actually,
because these fog events are occurring at ground level.
Yes.
And you are not interested in physics of development of these small droplets to large drops, raindrops in cloud.
Yeah.
So maybe development of small size particles may be enough to reduce the visibility.
Okay, sir, I will look into that aspect.
No, I'm asking from just ordinary question. Okay.
Any other questions? Okay. Thank you, Divya, for your.
Okay, sir. Thank you, sir.
Thank you. And the next presentation is by Sneha Sunil. Sneha, are you there? Sneha, can you hear me? Okay, I think we.
Sneha, unmute your mic.
Is Sneha there?
She has joined.
We are not hearing from her.
Is there?
She has joined the meeting,
but then she has some problem. Then we can go for next, and we'll ask for wait.
Yeah, we can come back to her. Yeah. So next presentation, Ms. Subramaniam, are you there?
Yes, sir. Yes, sir.
Okay. So yeah, the next presentation is by Mr. Subramaniam Kandalu. He will be presenting the work on characterizing the diurnal variation of precipitating clouds as observed by C-band polarimetric Doppler weather radar at Tumba. Subramaniam, please share your presentation and start.
Yeah, hope my slides are visible.
Yes, yeah.
Yeah, thank you, sir. Very good afternoon to all. Thanks for giving this opportunity. Myself, I am Subramaniam from Space Physics Laboratory. So I am going to, talk about characterizing the diurnal variation of precipitating clouds as observed by C-band polarimetric weather radar at Tumba. And this is what the outline of my presentations. I will be starting with the introduction and followed by specifications of Tumba polarimetric Doppler weather radars known as C-band polarimetric radar. And finally, I will be explaining about the results and discussion and concluding with the summary. So, as you all know that the tropical convective systems plays an important role in the rainfall and also general circulation of the Earth's atmosphere. Realizing the importance of diurnal precipitation, there have been numerous studies across the world to understand its structure and its dynamics. So there have been studies, but there have been very limited few studies over the Indian monsoon, especially during the onset of monsoon over the Kerala regions. So these diurnal cycle of tropical precipitation systems are very useful to understand its strength of the monsoon as well as its linkage between the vertical structure of precipitating clouds. So in order to better understand the link between the vertical structure of precipitating clouds and the onset of monsoon, the present study has been carried out to understand the vertical structure of precipitating clouds and the onset of monsoon. And the data I have used for the present study is C-band polarimetric radar. We can show in this middle panel shows the weather radar building, and left panel gives the what is the radar coverage range, and right panel shows the height coverage with respect to the elevation numbers. And this is for the major technical specifications. I am not going to discuss about it due to the lack of time. The main specifications is it's a C-band operating at 5.625 GHz, having the both single as well as the dual polarimetric capability. The peak power is 250 kilowatts with the pulse width of ranging from 0.5 to 4 microseconds. And this shows the top panel shows the spatial distribution of 20 dB's reflectivity occurrence at 2 kilometer height. So in the present study, we have considering as a 20 dB's reflectivities to address the vertical structure of precipitating clouds. Why? Because there have been previous also studies by Gipser, Liu, Wu et al. Using the TRMM. What they have done is they have taken the 20 dBz, 30 dBz, 40 dBz and find that 20 dBz will be gives the better representation of the having a rainfall of 1 mm per hour. So in our present study also we have followed the similar methodology. The top panel shows the 20 dBz occurrence during the onset of the monsoon in 2017. 2018 and 2019, 3 consecutive years. We can see that very interestingly, around 270 to 360 azimuth sector of radar range, we can see that the maximum occurrence of 20 dBz is found over the particular sector. This is mainly because of the interaction of the low-level jet with the radar station. So that is one of the main reason, and it also signifies the importance of the role in LLJ. And the magnitude, if you see their occurrences, 2017, 2018, 2019, more or less it is very good. But overall, 2017 and 2018, it is mostly related to the 270 and 360 azimuth sector, whereas 2019, it is broadly distributed. So it is again depend upon the strength of the monsoon also, it may vary. And the bottom panel shows the spatial distribution of maximum dBz occurrence at 2 kilometer height slice. We can see that very nicely it is spatially distributed over the entire radar range. We can see that around 40 to 35 dBz also we can see that within the entire radar range in 3 monsoon periods. And this will give the spatial distribution of peak time of maximum reflectivity. What we have done is we have find the maximum reflectivity of local time, at what time the maximum reflectivity occurred around 2 kilometer height level. In 2018, 2019, sorry that 2017 I have not shown, we have also done. Interestingly, we can see that from the these 2 years, the maximum rainfall peaks at late afternoon over the land regions, as we know that, and it is applicable to, as done by previous studies also, and also it peaks at early morning over the oceanic regions. Interestingly, if you try to see that closely, inspecting that over the coastal regions, where we can see that the between the land and oceanic regions, we can see that very nicely the rainfall, maximum rainfall peaks at early morning and also late night hours. So this is one of the interesting. If you try to see the same thing with the TRMM, we cannot see this kind of thing because of the high resolution as well as high spatial map of Doppler weather radar could able to reveal this kind of picture. So this will give us the very good information about what is the peak time of the rainfall or reflectivity occurred at 2 kilometer height over the given regions. And further, what we have done is this shows the diurnal evaluation of the 20 dBz occurrence
and we overplotted with the TRMM rainfall also. We can see that the contour gives the 20 dBc occurrence from the Doppler weather radar. It is found that the precipitating clouds peak at 3 local time intervals. One is from 6 to 8 local time, and another one peak at 13 to 15 hours local time, and the third one 19 hours to 21 hours. Whereas the TRMM rainfall, which is a red line, gives only 2 modes. This is mainly due to the when we have this lack of that high resolution of the time as well as the observation also. This may be the one of the reason. Otherwise, you see that 2 peaks it could able to capture by the TRMM. And one more thing is what we have taken the TRMM for the present study is this is actually 2014 mean picture, whereas the weather radar data what we have used is 2017, 18, 19. Since 2000 TRMM we don't have measurements during this period. So in order to represent the rainfall, I have taken the 2014 where we have the TRMM observations, and also the maximum 20 dBs occurrence found to be 13-15 hours with large vertical extent compared to other local times. And further, what we have done is apart from the 20 dBs occurrence, we have also analyzed the 30 dBc, 40 dBc, where we can see the middle panel 30 dBc, bottom panel shows the 40 dBc occurrence. So this picture clearly shows that whereas 20 dBc is the one, if you want to study their occurrence in terms of the precipitating clouds having the 1 mm per hour, which gives better representative rather than the 30 dBc, 40 dBc. And again, this 40 dBc also play an important role. If you want to try to identify what is the deep convective clouds variability, so 40 dBc echoes are the better representative. And also 30 dBc also will give the convective indication. So from this picture, we can see that when we are going higher and higher, the vertical extent of their dBc occurrence is coming down, but at the same time it is peaking the lower heights, as we can see from this picture.
Please conclude fast. You have 1 minute left.
Yeah, 1 minute. So this gives the further what we have done is we have identified the during the onset of the monsoon, what are the deep convective profiles, what are the shallow profiles. So this gives the contour frequency altitude diagram of the reflectivity and differential reflectivity during the June 2017. These deep convective profiles very nicely we can see that the as the height increases, the reflected values decreasing with height, and at the same time the ZDR values gives the around 2 dB, which gives that the dominant hydrometers is having the higher medium drop volumes, and also it becomes in the oblate shape. When it comes to the shallow convectivals, the ZDR dominated into the 1 dB. So which gives the shallow convective clouds is mainly dominated by the lower medium drop volumes indicated by ZDR around 1 dBc, and the reflected values confined to 20 to 30 dBc. Whereas the deep convectives precipitating clouds during the monsoon onset will be dominated by the ZDR of around 2 dBc, having the reflectivity is around 30 to 45 dBc. So thus the study is we characterize the diurnal variation of precipitating clouds during the onset of Indian summer monsoon during the 3 years consequent 17, 18 and 19, and it is found that these precipitating clouds peak at 3 local intervals. The maximum dBc occurrence found to be 13 to 15 hours, having a large vertical extent compared to other local times. And also the oceanic regime within the radar range is characterized by the morning peak as well as afternoon peak. In contrast to the land regime shows a broad peak during 10 to 15 hours and a late afternoon having a peak of 19 to 21 hours. Thus the present study brought out the contrasting features of the diurnal cycle of precipitating clouds over the land and ocean within the radar range during the onset of the monsoon period. So thank you, sir. Thank you once again giving the opportunity for IMSA.
Thank you very much, Subramaniam. Yes. Any questions, comments?
Can I ask a question?
Yeah, please.
Yes, sir.
So can you explain why you get a morning peak over the oceanic areas? What is the mechanism?
Which one, sir? This one, right?
Yeah, morning peak over the oceanic areas.
Morning peak, this is mainly because of the, I will first explain to the land. Over the land, we can see the land will be heating up. So that's what the, with time progresses, we'll be getting the peak over the land during the afternoon. Whereas oceanic time, during the, night already, SST will be very less. It's all subsidized. By the time it will gradually increasing, during the early morning hours, it vertical extent will be rapidly increasing. So it gives contributing. So that is one of the main reasons why we are getting the early morning hours over the oceanic regimes.
Any other questions?
Yeah, I want just advice that it's a very good presentation, but what you have concluded is the distribution of precipitation at different hours of the days, which is quite well known.
Yes,
but with Doppler radar, you have confirmed it. But Doppler radar is a very useful instrument. And this echoes from Doppler radar can tell you a lot of information can be given by these echoes. For example, ice content, water content, size distribution of this velocity of hydrometeors, terminal velocity, and their vertical and spatial extents. So, what I will advise you to do more work in this direction, just for in analyzing the Doppler radar echoes.
Yes, sir. Actually, we have done that one, actually, hydrometer classifications, and also, what type of hydrometer are present in the vertical altitudes. So, but, for this presentation, I have not shown that one. Otherwise, we have done that during the, successive 2018, 19, 2017 during monsoon period. We, like a kind of elaborate study we have already carried out, sir, and which will be, soon it will be publishing, sir. And definitely I will take in, further to expand our studies using the Doppler weather radar data.
Have you studied these type of echoes in pre-monsoon season?
No, sir. I yet to analyze, sir. So
that
I have done during the monsoon.
That is expected to give you more information, because extent of thunder clouds is much larger, much higher than in monsoon season.
Yes, sir. Definitely. We will pursue it in future, near future.
Thank you.
Okay. Thank you, sir.
Thank you, sir. Thank you.
There is one question. There is one question, and from YouTube. What is the minimum detectable signal of your C-band radar in dBg? And starts from 0 dBg you are showing in your color bar. How the deep and shallow profiles are classified?
Actually,
it is from Kapil Dev Sindhu.
Yeah, what we have classified is deep convective profiles. So first we have tried to identify that is there any 40 dBg echo within the radar profile. If 40 dBg echo is there, then what is the depth of that profile? If it is minimum, again cloud top. If cloud top is above 8 kilometers, then we have classified as above 8 kilometers top, having a 40 dBg minimum 1 or 2 pixel, and depth of that what we are taking is if it is beyond 5 kilometers, then we classified as a deep convective cloud profiles. Otherwise, if the precipitating cloud top height is as observed by Doppler weather radar is below 6 kilometers, then we classify it as a shallow convective profiles. So that is how we have followed the methodology, and the minimum detectability signals, as you can see from the this one, we can able to get that minus 23 dBg at 250 kilometers also we could able to get that. That is what kind of accuracy we are getting.
Okay, thank you.
Okay.
Thank you, sir.
Thank you, Subramaniam.
Thank you, sir.
Ms. Sneha Sunil, are you ready now? Sneha, can you hear?
Sneha, you are not audible to us.
Please unmute your microphone.
First of all, you identify yourself either by waving hand or something. You are there, karke. Otherwise, we may have to go for next.
Yeah, I think next is Suganya, right?
Yes, sir. Am I audible?
Is it Sneha or Suganya?
No. It's Sukanya, sir.
Okay. Yeah. Yes. So our next lecture is by Ms. Suganya Patra, and she will be talking on the onset of rain from the base of the warm tropical clouds from the cloud radar perspective.
Okay, I'll share my screen. Is it visible, sir?
Not yet. It's coming. Yes. Yeah.
Is it visible
Yes.
now? Okay.
Yes, you can start.
I'll start then. Good afternoon, everyone. I'm Sukanya Patra from Indian Institute of Tropical Meteorology. My topic entitled "To the Onset of Rain from the Base of the Warm Tropical Clouds, Cloud Radar Perspective." Warm clouds are those clouds which cloud top exists below the 0-degree isotherm or melting layer and hence only composed of the liquid droplets. They are the most dominating cloud type over Earth's surface and have a great impact on the global climate. And the rain formation, which doesn't involve the ice processes, are called the warm rain process. In the topics, roughly 70% of the total rain area is attributed to warm rain. The understanding of the first and efficient warm rain initiation represents a long-standing challenge in the cloud physics community. Despite impressive advances in the rain forecast over the past decades, our understanding of rain formation on a microphysical scale is still poor. Hence, it is essential to investigate the cloud droplet transition to rain droplet, especially its role in the Indian summer monsoon. The fact that turbulence enhances the rate of particle collisions can be considered as being established by the numerical simulation. But so far, there is no observational evidence to prove this point because of the lack of the proper cloud-sensitive observations. In this regard, we studied the transition of cloud droplets into raindrops and understand the role of cloud turbulence behind the transition in warm clouds. Using high-resolution cloud-sensitive observation from K-band radar, Yes, situated over Mandhadev, this cloud radar having very high frequency, due to its high frequency of 35 gigahertz, it is sensitive to the cloud droplets of 0.1 millimeter to 2.4 millimeter, and because of its high resolution of 25 meter and 1 second, it allows us to study those small scale changes inside the cloud. Using the reflectivity, radar reflectivity and velocity, combining these two parameters, we can study when the when the smaller number of larger drops are transforming into the larger drops, and the Gannon-Kingers has been followed to estimate the drop diameter from the fall velocity. Now, to discriminate between the cloud and rain, the reflectivity has been taken from less than minus 20 dBg, and velocity should be less than minus 1 meter per second, and for raindrop it is the vice versa. And only those cases has been chosen when the initial cloud height is below 0-degree isotherm, and also those days should be dynamically inactive to avoid the large scale influence, and also the clear air turbulence to study this phenomena. And also those overlapping of the cloud complex cloud processes are also avoided, and only single cloud entity has been chosen for this study, as confirmed from the range height indicator scan of the K-band radar. And for the same day, the continuous vertical looking observation available for 20 minutes, the high time intensity plot for reflectivity, velocity and spectral width has been plotted here, which shows that in the same time period, both non-precipitating and precipitating cloud systems are present inside the same cloud in the same episode. there is a gradual increase of reflectivity from minus 10 dBg to 0 dBg, and again from 0 to 10 dBg, especially at the lower level of the cloud. And also the corresponding velocity is transforming from updraft to a fall velocity indicated by the negative value up to 4 meter per second. And whenever there is an increase of reflectivity value, which actually means there is a growth of the cloud droplet sizes. Just prior to that, there is an enhancement of the spectral width, and the small and intense spikes of the spectral width can be seen. Now, spectral width is the indication of the randomness of the cloud particles present inside the cloud volume. That means it actually represents the cloud turbulence. The more would be the cloud turbulence, the more would be the value of the spectral width. For the detailed inspection, we have plotted the time series graph of the same three parameters: reflectivity, velocity, and spectral width for the at the cloud base and near to the cloud base, along with the rain rate obtained from ORG and also the diameter estimated from fall velocity. Whenever there is a spectral width value more than 1 meter per second, just after that, reflectivity and velocity, fall velocity, are attempt to increase and also try to cross the threshold value as indicated by this gray dashed line. And after at the third attempt, when there was a spectral width, brief presence of spectral width for almost 45 seconds, that's the time when cloud droplet is transforming into rain droplet, confirmed from the abrupt enhancement of the reflectivity value. When this transformation happened, just after there is a reflectivity flattened to another 6 to 8 minutes time it's taking to grow further up to form bigger droplets. This is the time when the smaller droplets collide. Coalition forces are supposed to be dominated here to form bigger droplets and having to gain fall velocity and to come under the sense of the gravity. Our droplets of having 4 meter per second of fall velocity, it will take another 4 minutes to reach to the ground. When it's confirmed from the that 556 it is having 4 meter of fall velocity, and it reaching at the 6 meter because there is a 900 meter, because the cloud base is situated at the 900 meter above the surface, and the drop diameter also shows that before the transition it is well below the 500 micrometer, which is in the cloud droplet zone, and again it is increasing to 1 millimeter, which indicates the raindrops. Another case shows that there is a.
Can you please conclude soon?
Yes. Another case has been shown here, but here the cloud base, the cloud top is above 3 kilometer, and also the enhancement of the reflectivity value and also fall velocity started from 3 kilometer altitude itself. The role of the enhancement of the spectral width value is also shown in this HDI map. The time series of the same 3 parameters along with the rain rate reveals the same facts like the previous cases, but here the fall velocity is high because of the is as high as minus 6 meter per second, because of the presence of the another peak at around this time when just the transition occurs to gain the fall velocity. Because of this high fall velocity, the rain rate is also much higher than the previous one. The drop diameter and also mass weighted diameter shows that there is a prominent transformation of when smaller cloud droplets transform into the bigger raindrops. Hence, it is the first of a kind study to investigate cloud to rain transition under stable, stratified, and homogeneous background conditions using theoretical threshold and Doppler moments of cloud radar. The transition of cloud droplets to raindrops is efficiently captured by the cloud radar observations. This study provides observational evidence of the fact that the brief but intense presence of cloud turbulence acts as a triggering factor in the transition from cloud droplets into rain at the warm cloud base. About 6 to 8 minutes difference is observed for the formed rain to gain fall velocity. fall velocity and hence raindrop rise and rain rate increase with the increase of warm cloud height. Thank you.
Okay, thank you very much, Suganya. We are skipping the question answer session for your presentation as well as the coming presentations due to we are running very late and the next session speakers are waiting. So if there are any questions, clarifications, please contact Suganya directly. Thank you, Suganya.
Thank you, sir.
Ms. Neha Sunil, are you ready now? Are you there?
Hello, sir.
Okay. Don't hear from her. So we move on to the next presentation then by Ms. Meenu Nair on investigation of cloud vertical structure and turbulence over the core monsoon zone in central India. Meenu Nair?
Yes, sir.
Yeah, please. Please share your slides and start.
Sir, is it visible now?
Hello?
Not yet.
Hello?
Hello, sir. Is it visible now?
Yes. Yeah, please proceed.
Good afternoon, all. I'm Meenu Nair. Today I'm presenting investigation of cloud vertical structure and turbulence over core monsoon zone in central India. The cloud vertical structure provides information on trimodal tropical convection and micro and macro physical classification of cloud. Trimodal includes shallow cumulus, cumulus congestus, and deep convective. Micro includes warm, mixed, and ice phase clouds. And macro physical classification include low level, mid level, and high levels. These classifications are shown in this figure also. So the cloud vertical structure needs to be understood for better predictability of Indian summer monsoon. The objective is to investigate the vertical structure of clouds and turbulence over Bhopal using GPS RS measurements. Bhopal is a site located in the core monsoon zone of ISM, and it is a proposed site for atmospheric testbed in central India. This monsoon core zone is important due to the formation of tropical convergence zone here, and also it shows significant differences in rainfall characteristics during active and break cycle. The ground-based instruments, active sensor satellites, and upper air measurements from radio sonde are usually applied to observe the cloud vertical structure. Cloud radar is considered to be the best tool for observing cloud vertical structure and provides continuous measurements also. But the problem is that the availability is limited. In India, there is only a single cloud radar located in Mandra. Also, the next one is satellite, but the problem is that satellite time resolution is low. So in this case, radio sonde is a good candidate for measuring cloud vertical structure. The disadvantages for radio sonde is that is due to its drifting, and for this relative humidity measurements above 13 kilometers are not generally considered. So this methodology in the study, we used high resolution radio sonde, and a cloud detection algorithm is developed following the method modified by Reddy et al. 2018, following Sang et al. 2010 is used. So in this, in the flowchart of the cloud detection algorithm is shown here. The cloud, the relative humidities below 0 degrees Celsius is converted to relative humidity with respect to ice instead of liquid, and we identify the MoES layers in the atmosphere based on the relative humidity values corresponding to that level, and these MoES layers are classified into cloud layer based on some criteria like maximum RS in these levels, and the cloud with thickness less than 100 meters are discarded in the study. For this turbulence, in the turbulence study, we use EN square measurements, that is turbulence structure parameter of refractive index, which is calculated using S. Rambabu et al. 2013. So first of all, the results part, the validation of cloud vertical structure method using radio sonde is conducted using co-located measurements of radio sonde and radar. This radio sonde was this is at Mandra Devi site. As part of a campaign, radio sonde was launched at the cloud radar site, and we can see that the radio sonde was successful in finding the low level and also the cloud base and cloud thickness also. So the radio sonde is a good candidate for measuring this cloud vertical structure, and this is
as another case for similar case for a cloud vertical structure using radius only, and also we can see that the both of them matches. And next one is cloud vertical structure for a monsoon season during June and July of 2017. And this monsoon, the dates of onset and the information on active and break was obtained from the monsoon report of this corresponding year. We can see that from the monsoon report, we saw that the monsoon onset was completed in this region around this 26th June, and we can see that there is a significant increase in cloud activity in this area, in this site from this day onwards. And during the break phase in this similar months, we can see that there is a reduction in cloud vertical structure, that is a reduction in cloud in this area. And also we found that the pre-monsoon months mostly have single layer and no layer clouds. This is example for another monsoon season, that is August and September 2019. The August and September was considered to receive excess rainfall, and there was no significant break periods during this season. And next we found whether the cloud vertical structure has any effect on CN square measurements. For this purpose, we considered distinct cases of deep and shallower clouds, and we found that when there are deep clouds, there is a significant reduction in CN square near this below the tropopause, that is near the cloud heights. And this is only preliminary results. More investigations needs to be done for confirmation of these results. And we saw whether the monsoon season has a characteristics effect on CN square, and the seasonal features of a monsoon is evident in the CN square values, that the CN square values are higher at lower altitudes from boundary layer to around 12 kilometers, and there's a distinct shape for this monsoon season. So summary of this talk is a radio sonde can be used as a convenient tool to find cloud vertical structure. Co-located measurements of radio sonde and radar has verified the method of finding cloud vertical structure. Onset of monsoon has led to significant cloud activity in the area. There's a signature of active and break spells in these structures, and CN square profiles for few cases of deep and shallow cases were analyzed. For turbulence measurements, we can see that the monsoon have higher values of CN square at lower troposphere. Thank you, IMSP and organizers, for providing this opportunity, and we acknowledge IMT and our radar team for providing the data. Thank you.
Okay, thank you very much, Ms. Meenu. If there are any questions, please contact her directly. And we move on to the next presentation. Sneha, are you there now?
Yes, sir, I'm here now.
Please share your screen and start.
Okay, sir. Okay, good afternoon, everyone. I'm Sneha Sunil. I'm a research fellow working at IITM. And today I'm here to present my study titled Retrievals of Cloud Fraction and its Diurnal and Seasonal Variability over a High Altitude Station in the Western Ghats using ground-based remote sensing technique and comparison with MoES. I'm starting with a small introduction. The cloud fraction is one of the important cloud macrophysical parameters which play a significant role in Earth's energy budget and the global climate system. And it also plays an important role in solar dimming and changes in surface temperature. Also, they have a role in controlling the climate feedback. So it's a vital parameter to detect the climate sensitivity. Hence, continuous monitoring of cloud fraction is required for understanding the cloud radiative effect.
Sneha, please put it on full screen mode, slideshow.
Yes, sir, I have put it on full screen mode.
Okay, anyway, you please proceed. It has not come. Yeah.
Okay.
You please proceed.
Okay, sir, okay. Can you see the slides actually? Now I'm on objectives.
You can see the slide, but not in full screen mode. But please proceed.
Yeah. Okay. The objectives of our study are construct a time series of cloud fraction at a high temporal resolution, compare with MoES cloud fraction.
It is still on the first slide only.
Yeah, slides are not moving out.
Now it's okay.
Okay, then I will play it in this mode then. Or should I go to full screen mode?
It's fine.
It's okay, continue.
You please make sure
Okay.
slides are moving and then present.
Okay, sir. Okay. So the objectives of our study are to construct a time series of cloud fraction at a high temporal resolution, then compare it with MoES cloud fraction and discuss the causes for observed biases, and study its diurnal, monthly, and seasonal variation useful for understanding cloud and precipitation processes over a complex terrain. The data and methodology which we have used in the study are as follows. The study is based on cloud data obtained at a high altitude station, which is situated in the complex terrain of Western Ghats of peninsular India. The figure here shows the topography of the study region. The instrument used in the study is a whole sky imager. It is having both visible and IR cameras, and it is continuously operated at the high altitude cloud physics laboratory. And the sky images captured by the sky imager are used to retrieve cloud fraction at a high temporal resolution of 5 minutes. The retrieved cloud fraction is then compared with MoES cloud fraction during the overpass time over the study region. The satellite passes 4 times per day over a region. That means 2 passes during daytime and 2 passes during nighttime. So we are comparing cloud fraction during daytime and nighttime. The cloud fraction is averaged over a region of 30 kilometers centered over the observational site. Moving on to the result, the first section focuses on the comparison of cloud fraction from the sky imager and the bodies. So the figure here shows the correlation between the observation of cloud fraction from MoES satellite and from sky imager. The blue color correspond to the comparison of sky imager with Aqua, and red correspond to that of Terra. So the first panel shows the correlation between the observation which have been taken during both day and night time, and the second one is taken only during daytime, and the third one is only during night time. So from here we can see that the correlation during the night time is slightly higher than that of daytime. And even if we are getting a good correlation, it is not effectively strong, and there are several factors which contribute to these differences. So while comparing a ground-based sky imager and satellite, there are certain factors contribute to the difference between both the platform observations. And these factors are, first one is the viewing geometry of the satellite. So here when it has been found that the cloud fraction measured at the edge of the scan could overestimate during partial and cloudy condition, and this is dependent on the solar zenith angle and the cloud horizontal extent. And second factor is the field of view of the ground-based imagery, and this is like the sky imagery is looking up towards the sky with a conical field of view. So this field of view is dependent on the cloud base height. So if cloud base height is high, the field of view will be larger, and if the cloud base height is low, the field of view gets smaller. And the third one is the sensitivity in the measurement techniques. So basically the MoES satellite is looking down on the earth, and the cloud detection is based on the contrast. That means the algorithm needs to differentiate between the cloud and the background surface. So the algorithm needs to identify a range of land surface such as land, water, snow, ice, desert, etc. And during some occasions, the algorithm misinterprets the land surface as a cloud, and this leads to the overestimation of cloud fraction. And whereas the sky imager uses a different methodology to identify the clouds. So here we are the first image depicts the pictorial representation of the thermal irradiance captured by the sky imager, I mean the IR camera. So what we have to, like in case of satellite, it needs to remove the background surface from the actual image, I mean to identify between the clouds. But what we have to do is to remove the background clear sky radiance from this image. As it is looking upwards, that's what we need to remove. So once we remove the clear sky radiance, we get the clear sky subtracted radiance image. And once we get this, we apply certain thresholds. For this, we have created an algorithm which identify the clear sky radiance first, and it will be eliminated from each captured image, and afterwards we'll be getting the clear sky subtracted radiance image, and we'll be applying certain threshold to these values, and from that we'll be obtaining the cloud mask, and the cloud fraction will be calculated from this cloud mask. So these are some results. So this first figure is from the visible cameras. So here we can see some thick clouds with fine structures and bright edges, and we can see that the IR camera has also captured this very correctly. The fine features are there, and it has been converted to the cloud mask without losing any fine features. So moving on to the next section, that's the diurnal variability of cloud fraction. So from the retrieved cloud fraction, a time series has been constructed for the period December 2016 to May 2019. And from the figure, we can see that the temporal variability of cloud fraction is highly variable, and it has a systematic diurnal cycle as observed in the years of 2017 and 2018. And the second figure, it depicts the diurnal variability of cloud fraction from MoES. It is observed that MoES cloud fraction showed similar annual cycle as that of WSI, but missed out fine but large variation as noted in the first figure. This is because the MoES is having 3 to 4 instantaneous observation per day, but the sky imagery is having observation for every 5 minutes.
Please conclude soon.
Yes, sir. The next one is the frequency of occurrence, and here we are showing the frequency of occurrence of total cloud fraction, thick cloud fraction, and thin cloud fraction. And it is observed for 24 hours, only for daytime and only for nighttime. And from the figure, we can see that during JJS and October, occurrence of cloud fraction in day and night are somewhat similar. And in all other months, the cloud fraction during the day is slightly more than night. And the occurrence of thin cloud fraction is found during the daytime as compared to night. And next one is the monthly variability of cloud fraction. And the monthly variability of cloud fraction follows the conventional pattern found over the Indian region, with highest cloud fraction during the JJS, and here it is followed by October and May, and the lowest is found during March. And there is no huge differences observed between day and night because most of the variability has been averaged out. And next one shows the seasonal variability of cloud fraction from both whole sky imager and from MoES. And from this figure, we can see that during winter, the daytime cloud fraction is more than nighttime cloud fraction, and the MoES cloud fraction is underestimated in all the season except during monsoon season, where there is a small difference. And maximum bias is observed in the winter and pre-monsoon season, followed by the post-monsoon. And large bias on a regional scale are due to the high cloud fraction variability, and it is because of the fewer satellite observation representing the day average. The conclusions from the study are the cloud fraction is retrieved from the ground-based imagery continuously for 24 hours at a high temporal resolution, and a unique time series is constructed for thick, thin, and total cloud cover. And the retrieved cloud fraction is compared with MoES cloud fraction during the overpass times over the study area. Even though good correlation is observed, more bias is observed during the broken and partial cloud condition. This is due to the differences in viewing angle, sensor field of view, and sensitivity of measurement techniques. And the diurnal cycle of total cloud cover showed high variability in all season except in monsoon due to continuous overcast condition. And the study infers that the cloud events or characteristics observed on a temporal scale get averaged out on diurnal, monthly, and seasonal scales when compared with MoES diurnal and seasonal variability. And large biases are observed on a regional scale due to high cloud fraction variability and, more importantly, fewer satellite observations representing the day average. And I would like to thank the director, IITM, and my guide, Dr. B. Padmakumari, the team associated with High Altitude Cloud Physics Laboratory, the MoES team, and IMSP for providing me this opportunity. Thank you.
Okay, thank you very much, Sneha. Again, if questions, please contact her directly. And the next presentation is by Dr. Madhuchandra Reddy on the role of cloud vertical structure measurements for better predictability of ISMR extremes. Dr. Madhu, please.
Yes, sir. Good afternoon, all. Am I audible?
Yes.
Could you see my screen?
Yes, please start.
Yes, thank you. So the importance key points is the Indian summer monsoon, and another one is the cloud vertical structure. So I am discussing about the importance of cloud vertical structure in the context of ISM extremes identification and possible predictability. So here, this is the backdrop. So Indian summer monsoon, especially Rajiv et al. Find out that central India, mainly based on the central Indian rainfall, during a active phase, this is the lavender color, and bright is this one. So this is the anomaly. So positive anomaly is there during the active monsoon. And red is our radar place where it exists in Mandra Devi in the Western Ghats. It shares the central Indian active things is shared by Gujarat and Western Ghats. So we picked up the active things means above the climatological mean, the active daily rainfall things. So where minimum 3 days is there, those are the active phase, and where the break phases, which is very much less than the climatological mean. So those things are selected. And another thing is the different types of convection, shallow convection, which cannot, which exists below 0 degree isotherm. Another one just crosses the 0 degree isotherm, maximum up to 8 kilometers cloud tops. And another one is more than 8 kilometers, maximum up to tropopause. So these are the convective clouds. So cloud vertical structure is the one parameter which can able to differentiate the cloud vertical structure information, like a shallow cloud which lies 0 degree isotherm, whereas the cloud tops existing above minus 40 degrees centigrade. So those are purely ice clouds. There is ice process, whereas in between minus 40 and 0, they are the mixed phase or mid-level clouds. So this side we have given in the macrophysical classification. This side is the microphysical classification according to the phase change of the water. So this is the main thing, like 5.3 kilometers and 10.8 kilometers we find out from the mean temperature profile over the Mahabaleshwar we have taken. From that we calculated these temperatures, and we find out the cloud. The another important thing is the sixth component is the monsoon cloud vertical structure. Is the one of the 9 elements in the Krishnamurti and Balme is they told. So, but not they exclusively mentioned the cloud vertical structure, but it's hold importance. So this is the cloud vertical structure. The red profile you can see, it is a cloud radar reflectivity which is sensed to minus 45 degrees and minus 45 dBg at 5 kilometers. So it can see minus 60 dBg at even surface. That is the beauty of this cloud radar technology, which can observe at a minus 60 dB at surface. So the cloud vertical structure you can see in a deep one-layer monsoon cloud system where the cloud tops existing up to 14.5 kilometers. So where the another parameter cloud radar can measure in the vertical looking is the reflectivity. Another one is the radial velocity. In a vertical thing, it can provide the fall velocity of the drop when it is raining. Otherwise, it gives the background updrafts and downdrafts. So another is the LDR, linear depolarization ratio, which can tell the where the zero means phase change is where it is happening. There it will give a very good indication. That is the 0 degree isotherm or a freezing level or the bright band. And so during rain time, the spectral width will give the drop side distribution information. Otherwise, it can infer this cloud turbulence. So these are the parameters during a deep cloud day, one complete day, and one shallow cloud day. If you take a so shallow clouds are much lying their tops below 2 kilometers, whereas the deep cloud day, like a low pressure system or the thunderstorm time, so it can reach up to the 14 kilometers. We can find the drop side distribution at the surface also. The drops are more than 2 mm we can see during a deep cloud system, whereas shallow cloud it is much less. So this is our radar region over the Western Ghats. So you can see this mean sea level. So it is almost like 1.4 kilometers from this from the sea. So this is the cloud radar. It can provide the cloud vertical structure. The objective is how the cloud vertical structure data during a active and Central Indian active and break days. Is there any difference? So before going to the genuine cloud profile, so we have to eliminate all the non-cloud importance. So then even a cloud, there is a rain part which is not the cloud, which is a precipitation part, that also we are separated. So after separating, we are getting a pure genuine clouds that is in a blue or black color, whereas a gray thing is a contaminated things that we have to separate. So there the contaminated things is coming either due to the biota or the background noise of the radar noise. So those things we have to eliminate. So they are less than 4 seconds things. So we used a technique and we deleted all those things and only consider the genuine clouds. So genuine cloud during a wet and active monsoon and dry phase, there are clear difference in the reflectivity, velocity and the width. So we can able to identify by using 3 parameters, we can able to identify wet and dry phase. So if you take a continuous 60 days cloud vertical structure for every half an hour, if you plot it, so you can see that first 14 days, there is a shallow clouds, which is lying below 3 kilometers, whereas they are growing up to 8 to 10 kilometers during this is cumulus congestus, whereas the deep clouds are there. Whenever the deep clouds we have seen, there is a descending cirrus clouds we have seen. So we have separated these all days into active and break phases according to the Rajiv Sir thing. So we could see the cloud vertical structure having a 3 states that is called, it is like this. 0 degree isotherm and -40 things. So you can see the ice phase clouds are very much handshaking to give a rains at the surface through a mixed phase things. So whereas that is during a break time, there is a big divide of the cloud can be seen. This is the main difference between this CFED diagram, which is essentially a histogram diagram from each range mean height up to the 14 kilometers reflected.
You have 2 minutes left.
Yeah. So by using this, we could able to see the active and break monsoon microphysical profiles. Also, they are showing a clear distinguished difference. And this, we are extending this study using a cloud radars for 10 years data over the various Indian regions. And this cloud vertical structure during active phase at different places in India, like Northwest and West India, Central India. And we found that there is a clear difference, whatever we found at the Mandra Devi. So such results can be used to identify the, first of all, extreme monsoon features. So this better understanding of the mixed phase regions and cloud multiplication things. So we are working on it, and even we are extending with the radio sounded data and also the RHA things. Here you can see the cloud vertical structure is coming down and interacting and mixing with the low level clouds. So these are the future scopes for our work. So that is thanks for your attention.
Thank you, Dr. Thank you, Dr. Madhu. And our final presentation of this session is by Emmanuel Rongme.
The last presenter won't be presenting, so you can conclude the session.
Oh, okay. So in that case, let us conclude this special session on clouds and its characteristics, specially organized to honor the contributions of Professor Pradeep Kumar. So altogether, we had 4 invited lectures and 1 special lecture by Professor Pradeep Kumar himself, and 12 presentation by young scientists, the research students and PG students, covering all different aspects of clouds and its characteristics. Most of the presentations were on the observational aspects and somewhere on the numerical modeling aspects as well. I request Kamara sir to give your concluding remarks and end this session. Kamara sir, please.
I would like to delay the proceedings, but just I want to say one thing, that I was very happy to see the standards of the presentations. It was very good, and especially pleased to see that participation of some students were given some very good presentations. I congratulate them for that. Thank you.
Thank you, sir. So let us end this session and proceed to the next session.
Thank you very much, sir. Thank you to Anand sir and Kamra sir for chairing this session, for a long section, marathon session. Thank you very much to both of you.
Thank you.
Thank you, sir. So we are now inviting the session 2 chairs, Jnanasilan sir and Pai sir. Please take the floor, and sorry for late. Pai sir and Jnanasilan sir.
Yeah. So Dr. Pai, you can start. Actually, first talk we can delay because Vimal Mishra is busy with another meeting, so we can go to the second presentation.
Okay. Thank you. So what we'll do is that without wasting much time, we'll directly go to the presentation, because already we are delayed by almost 1.5 hours. So we will request all lectures, both invited lectures and students' presentation. They all keep their timing. So just before 2 minutes before your 2 or 3 minutes before your final, we will inform you, and then please try to complete by the time, so that if you keep 2 or 3 minutes, we can add 1 or 2 questions for your presentations. So anyway, thank you. So this is, we have got, for the invited lecture, we have got 3 lectures, 3 important lectures. one by Professor Vimal Mishra, second by Dr. S. Abhilash from CUSAC, and third by Dr. N.R. Deshpande, IITM. So as Dr. Jnanashilan said, Professor Vimal Mishra will be joining later. So I'm inviting Dr. Abhilash. Abhilash is there? Abhilash?
Yes, sir. Yes, sir.
Yeah,
hello.
Please, you can actually put your presentation. So he will be giving a lecture on climate factors on the recent extreme rainfall events.
Dr. Pai.
Yeah.
It's Vimal Mishra. So I have just joined. If now I think slides are up. So after this presentation, can I make presentation?
Yeah. So what do you want? Let us complete of Abhilash and then you can make.
Yeah, I think Dr. Abhilash can complete and then I can make after him.
Okay, sir. Thank you. Thank you, Professor Mishra. So I invite Dr. Abhilash to do your this one. It is for 20 minutes. So please try to complete, within 17 or 18 minutes so that we can have some questions. Thank you, Abhilash. Please.
Okay. Thank you, sir. Could you see the screen?
Yeah, yes, you can see. Go ahead. Yeah.
Yeah. Okay. Thank you, sir. Actually, I would like to thank IMS Pune chapter for giving me an opportunity to present our work on recent extreme rainfall events over Kerala. Actually, this work is there are many collaborators from both from CUSAT, IITM, IMD, and University of Miami. This we know the right panel of this figure is famous Goswami's paper 2006. I am not going to explain that. But the another paper on the same year by Francis and Gargill, they have shown that most of the heavy rainfall events of threshold of like 15 centimeter per day and 20 centimeter per day, they are mostly occurring north of 14-degree latitude. And south of 14-degree latitude, there are less number of such events. Maybe their data period is from 1951 to 1987. This is the background of this entire presentation. And another interesting definition of cloudburst classification. Actually, this cloudburst classification itself is a challenging task because there are many ways we can classify cloudburst, of which the well-known two methods are CBA and CBB. CBA is based on whatever may be the rainfall threshold or rainfall intensity. If cloudburst can produce flash flood kind of things over a mountainous region, that can be classified as cloudburst B category based on Phule 1946. That is well accepted also. And there is, as per IMD criteria, if rainfall of the order of 10 centimeter per hour is mainly classified as cloudburst as per IMD classification. But there is another interesting paper by Deshpande et al. In 2017. They have classified a mini cloudburst event in which a rainfall in 2 consecutive rain hours is exceeding 5 centimeters or more. They are classified as a mini cloudburst event. And they also provide the shown that these mini cloudburst events are very dangerous as far as the probability of flash flood is concerned. They are 3 times higher dangerous than a extreme rainfall event on a daily scale of 20 centimeters in 24 hours. So that is the main crux of that paper. And also regarding the cloud structure from Subramaniam and Kumar, they have shown that most of the deep convective clouds are occurring mostly offshore and in the Headway region along the Myanmar coast and offshore of Western Ghats. And if you look at the heating structure over Western Ghats region, the heating structure is like of, though it is a convective single mode structure, but it is mostly shallow convective type, and over the Myanmar it is mostly deep convective type. So this is the basic background of this work. So we have from few years of INSAT Kalpana satellites and combination. We have used the combination of in brightness, temperature, and TRMM rainfall, 3-hour rainfall accumulation. We synchronize means we utilize both the rainfall and brightness temperatures together to come up with some kind of the contribution of deep convective cloud for the for the extreme rainfall event. So this is just the rainfall distribution during JJS period. There is a primary rainfall maximum zone along the Myanmar and then along the west coast. And if you look at the extreme rainfall events like 10 mm per hour and more, a percentage of frequency of occurrence of such type of extreme rainfall events are very common in central Indian region, and also there is a small portion around this region. And also we can found that if you count this extreme type of rainfall event to the total seasonal mean rainfall, we can see that over this region, maybe 40 to 50% of the seasonal mean is contributing from this type of extreme rainfall event. And if you look at the cloud structure, we have taken the collocated 3-hour rainfall picture from pixel from the TRMM, and also counted those extreme rainfall pixels and counted the brightness temperature from the infrared, and we found that most of the extreme rainfall event occurring over this region is from either from the deep middle to deep, very deep convective clouds, but along the west coast most of this contribution is coming from the shallow convective type of clouds. So, and if you coming to the Kerala specifically, this is the terrain map of Kerala. This is the location. And if you look at the distribution of rainfall, annual distribution of rainfall, we are getting mostly like 65 to 70% of the annual rainfall in the monsoon period. And this is, if you look at the Kerala, we are receiving a flood type situation during the last three years, like in 2018, 19, and 20. If you look at the August, this is unfortunately the reason we don't know the reason for the occurrence of this flood events in August. But if you look at the last 3 years, most of these 3 flood events are occurred during 2008 in August 15 and 2019 August 8 and 2020. Though it was not a large scale flooding event, but there were a lot of disaster like landslides and kind of flash flood event at many places in 2020 on 6th August 2020. So all these flood events were occurred in August month, and here we have plotted the percentage deviation of rainfall that if it is exceeding 100% of the daily climatology, that is shown in red color. So we can see that all these August events are shown in red color, and along with we have used kind of percentile based threshold values also along with that, and daily values are also plotted. And if you look at even if into 2020 September has shown large rainfall in September of the order of maybe 200-300% more, but the rainfall threshold is very less, as climatological rainfall is very less during September month. But if you look at the daily rainfall either on percentage wise or percentile wise or daily threshold wise, these 3 events are the main flood events which occurred in 2000, both the 3 consecutive years over Kerala. So, and we segregated all this rainfall decade-wise and found that in the recent decades, the rainfall variability is increasing, and even the daily rainfall is reaching like 14 centimeter per day. If we consider Kerala as a whole, some of the region may be getting more than 30-40 centimeter per day rainfall on the scale of those thresholds. But still, on an average over Kerala, if we are getting this 14 centimeter per day rainfall, it is very dangerous. And we can show that extreme values are being increased in the decade wise, and also the variability is also increasing. And if you look at the active spells, if you look go back this figure, you can see that there are lot of green shades bars during all these 3 years, but there are only 2-3 red spells. But this spell duration is also like a 5 to 6 to 7 day duration of spell of the order of more than 200-300% of rainfall for a duration of 5 to 6 days is very much dangerous. And if you look at for the last 2-3 years over Kerala, the rainfall deficiency of maybe 20-30% is being compensated by just one or two spells. That is the main dangerous situation as far as Kerala is concerned. Or on a climatological scale, also this type of extreme events are being increased in over Kerala. And if we consider the same IR brightness temperature coincidence with extreme rainfall pixels, we can find that there are occurrence of deep convective clouds over these regions, and there is a offshore region, and it is slightly extending towards the land region, and there is a kind of gap between these two rainfall maximum zones. And if we have taken the rainfall and corresponding brightness values over this 0.5 degree boxes and plotted the latitudinal variation of the deep cloud frequency and the extreme rainfall frequency, and found that deep cloud frequency, there is a kind of dimodal type of distribution in the deep cloud frequency, and also rainfall is also having a kind of that frequency. And earlier I have shown the Francis and Gargill, they have shown that mostly this rainfall peak is concentrating north of 14 degree latitude, but now it is coming towards south. That is the dangerous situation. And if you look at the convective rainfall trend over the Western Ghats, south of 14 degree north, you can see that the convective rainfall fraction is increasing. And if you consider the Southeast Arabian Sea SST also increasing. Not only the SST, the average atmospheric temperature is also in the lower level. Atmospheric temperature is also increasing over east coast of Eastern Arabian Sea region. And also, if you look at the vertical structure of the temperature anomaly and specific humidity anomaly between the recent decades and the previous decades, we can find that the temperature anomaly is positive, especially in the middle layers, and there is a increase in humidity in the lower to middle levels during recent decades. That is enough for contributing more and more moist static energy potential in the recent decades over this Western Ghats region. That is also a major contributing factor to this rainfall increase during these years. And also, if you look at the spatial structure of the convective rainfall trend, which are shown with a 99% of confidence, and we can see that there means a significant increase in convective rainfall over this region, and along the Gujarat region. So that is also very evident. And in response to that, what caused this is that if you look at the Hartley circulation, we can see that the Hartley circulation is kind of expanding, but a small branch of this is being intensified over these decades over along 10 to 13 degree north latitude. And also corresponding to that, the ice content over this latitude, we can see that there is a increase in ice content in recent decades, and there is also an increase in liquid water content in the around 500 HPA level. So this may be kind of we have to look for the precipitation process also. Maybe this liquid water content may be produced from the cloud phase, means ice phase microphysical process, and they may be converting to liquid phase at the melting level. So that is also, we need to look into that factor also. But if individually, if you consider these all three spells, we can find that in 2018, there, if you look at the zonal wind speed, wind shear and all, we can see that the zonal wind shear throughout the season up to 31st August remains more or less same. But if you look at the cross-equatorial flow in terms of moisture transport, we can see that compared to in 2018, there were three active spells, one in June, another big spell in July, and another small spell in early August, and the big spell in around 15th August. So, and during that spell, we could find that the cross-equatorial flow and the meridional transport of moisture was very high. This is from SCATSAT wind analysis data, and this may be one of the reason for 2018 heavy rainfall, one of the reason. And you can see that there is lot of difference in the rainfall pattern, though both the rainfall events were associated with a deep depression over the central Indian or Bay of Bengal. So in 2018, most of this maximum spell was away from the coast, something around the off coast means offshore region, But in 2019, most of this maximum spell happened in the land. So as far as rainfall, mini cloudburst kind of thing, a cloudburst kind of event might have happened in 2019 over the land. That is the main factor we have to consider. If you look at the IR brightness temperature, we can see that IR brightness temperature of the order of less than 200 Kelvin is actually intruding towards the land in 2019 as compared to 2018. So in terms of rainfall distribution also into 15th August 2018, we are not getting any rainfall means frequency of the order of 30 millimeter per hour. It is very rare in 2018 even, but in 2019 we are getting even like 50 to 60 millimeter per hour rainfall events in 2019. So, and also in response to that, we analyzed the vertical profiles of hydrometers from GPM, G profiling software, G profiling data sets, and we found that there are a lot of evidence of snow water content and ice content over this 10-degree latitude, and that also signifies the presence of very deep convective clouds and the cold cloud process, the microphysical process also in 2019. So this is the 5-day. This is also in accordance with the previous slides where I have shown that the active duration is also increasing along with the spell. The one spell can compensate for the seasonal deficiency. So that means if you look at this is station-wise rain gauge data for 5-day period during this extreme rainfall event, we can find the size of the circle is in accordance with the intensity of the rainfall, the accumulation of the rainfall during this 5-day period, and it's also scale according to this color. And we can find that in 5-day, some stations received of
Dr.
rainfall.
Abhilash, can you please stop in 2 more minutes?
Yeah, it's only one slide left, sir. Yeah. So we can see that in 5-day rainfalls of the order of 120 centimeters we are getting over many stations. That means 120 centimeter in 5 days is like double the monthly rainfall expected during that period. So this is the actually the dangerous situation. This might have been contributed from the vertical development of deep convective clouds that is rare during previous decades, and the atmosphere is also getting conducive for all. And I am not neglecting all other large scale factors, though the large scale factors are different during all these 3 years, but the common factor is the vertical development of deep convective clouds along this. So we need to have a better forecasting in terms of quantitative precipitation forecast. We have seen that none of the global models were able to capture this rainfall intensity of this order, maybe 1 or 2, 3 days in advance. So if a global model which is not predicting the quantitatively, which is not predicting this type of extreme rainfall event even at 1 or 2 day lead, it is not at all useful. But we can give probability forecast, but there we have to look for another ad hoc approaches, the previous approaches, like even if the global models are run at 10 kilometer resolution, they are not able to capture the spatial variability or the terrain with respect to the terrain. We have to depend on kind of regional models. This is a kind of regional model forecast from WRF for this 2020 event. We can find that at a 3-day lead, some kind of this Munnar event, the landslide event occurred on 6th of August. We could able to get some kind of quantitatively some kind of heavy rainfall, maybe 3 to 4 days in advance using the regional model at different resolutions, different configuration, and this we have run with bias corrected SST from CFS SST. So the main summary from this study is that duration of active spells and rain intensity is increasing in recent decades over Kerala. Changes in cloud structure is putting God's own country under pressure, and the quantitative precipitation forecast at shorter lead time is the need of the hour for a better disaster management preparations and all. So I would like to acknowledge the funding support from National Monsoon Mission Program. Thank you.
Yeah, thank you, Abhilash. Any questions, please? 1 or 2 questions we can take up. Yeah, Abhilash, So, are you hearing me?
Yeah. Yes, sir.
Yeah. See, you have been in your conclusion saying that in a recent decade, there is an increase in the heavy rainfall, the active rainfall and then intensity. But when we are seeing extreme rainfall, except for last 3 years, there has been a trend of decreasing trend. How do you explain that?
You mean over the west coast, south of
Kerala? I'm talking about Kerala.
Kerala. Okay. So up maybe till 2017, that trend was okay. It was like decreasing trend, but from 2016 onwards, we cannot tell like this trend and all. It is actually I would like to see it as a variability, like the intensity and duration together is contributing the disaster more severe. So that is what the duration of that active spells is for. Earlier maybe 2-3 days of active spell duration is changed to 5, 6 or 7 days, and of the order of like 10 centimeter per day over entire Kerala. So that is becoming very common in last 3 years, at least in the last 3 years. So that is very dangerous features.
See, similarly, last 2 years, this is 2020-19, if you see that, we had a good monsoon in the second half, and so you also get a good heavy rainfall in August in both the years. So do you feel that large scale features are responsible, have got any role in that?
Yeah, sir. The 2018, 19 and 20 was entirely different. Large scale features was entirely different. So means I didn't see any kind of common large scale features for these three events. 2018 is like first half was very good, and second half from August 15 onwards, rainfall came down. So it is a kind of different distribution, and 2019 it was entirely different. That IOD also might have played a role. And 2020, the initial phase of monsoon in terms of low-level jet and all was very weak, but still in the second phase we got a good spell. So large-scale features were different during all this. There is no common large-scale features in this three at least these three events, but what was common is that the cloud structure is being changed.
Anyway, Janashilan sir, you have got anything?
Yeah. See, your experiment with the CFS, the SST corrected runs, so they could represent it. So do you think that the clouds responding to those SST are responsible for that?
Yeah, actually I have not presented the entire experiment details, but we have tried with a different combination of the parameters, like we replaced the land use categories, and finally we come up with a combination of microphysical and other parameterization schemes. And when we run it with observed SST and then GFS forecast, GFS analysis without any SST forecast, and then with the CFS forecast. So what we found that CFS without bias correction is overestimating, very much overestimating the rainfall. So then when we correct the SST bias, it is slightly coming down to a reasonable values. So we cannot conclude from this one or two.
Thank you. Thank you, Dr. Abhilash, and you have done excellent presentation. Professor Vimal Mishra, you can share your presentation. Coming back to Abhilash, you had a very nice presentation. I think everybody can personally ask him. Actually, he is well known to all of you. IITM, he has been working earlier in IITM, so you can have direct question to him. Now I invite Professor Mishra for his lecture on drought and flood under warming climate in India. Stage for you, Professor.
So Dr. Pai, can you see my screen? Hello. Hello.
We cannot, please.
Yeah, I think your presentation is not being seen. Initially it was seen.
Yeah. Now we can see.
This is now. Yeah.
Okay, so and can you hear me well?
Yes, please.
Okay, so thank you very much for inviting me in this, India Meteorological Society Pune chapter, and Dr. Pai and everybody from IITM and MoES for organizing this workshop. And I think we are already running late, so I'll go very quickly as soon as possible to finish my talk. So I'll be talking about droughts and floods in India under warming climate, and the entire understanding is like whether we are moving towards experiencing more hydrological or hydrometeorological extremes as we are moving into 21st century, right? So there is no doubt we are living in unprecedented time. If you see the history of last 2020 years, and I saw this a day back. So data comes from pages 2K and some other observations. And you can see that with reference to 1901 to 2000, how the last 5 or 6 decades have been unprecedented warmer than the history. And the entire global temperature has already increased about 0.8 or roughly about 1 degree Celsius. And that has implications basically for when we talk about hydroclimatic extremes. And drought and floods are two big extremes that we come across almost every other year. Floods for certainly every year in India during the monsoon season. So if we look at India, this 1951 to 2018, and you can see on your left that these are the change in temperature in different seasons based on the IMD data sets. So winter, pre-monsoon, monsoon, and post-monsoon. And we can say that in all these seasons, at least a significant part of the country has experienced warming, roughly about 1 degree or so. And if you also look at the global reported natural disasters by type from 1970 to 2019, we also see that there has been a tremendous increase in the natural disasters, and flood and droughts are being the two most prominent extreme climate or hydroclimatic events. So, in next few slides, I will discuss like what is happening in terms of floods, what is happening in terms of extreme rainfall, and a few results on the drought that our lab has conducted and published recently. So, we did some work looking at what happens to warming climate and extreme precipitation event. And these are the results, based on the station observations from global summary of the day. That data set is available globally. And you can see that with warming climate and based on the Clausius-Clapeyron relationship, we expect that roughly about 5% or more increase in extreme precipitation per degree rise in temperature. And this is more closely associated with the rise in dew point temperature than surface air temperature, especially in the tropics. And that negative relationship can be explained because of the cooling that occurs after the rainfall. Like in India, monsoon rainfall also provides cooling in hot temperature that we experience during the summer period. So what we get from this that as we increase the temperature, atmospheric water holding capacity increases, and atmosphere can hold more and more water vapor, and that falls in terms of extreme rainfall events, and that may or may not create flood events. So certainly warming climate has implications for extreme rainfall or extreme precipitation events. Whether that converts to flood events or not, we will see in next few slides. This is also sub-daily observations from different data sets like GSOD, TRMM, CHRIPS, and 3-hourly TRMM, right? Daily and 3-hourly T. And what we see again that sub-daily rainfall extremes are more sensitive to warming in comparison to daily rainfall extremes. So when we talk about the hourly rainfall extremes, as we move into warming climate, we are going to see, or we are already witnessing more and more intense or heavy rain events of short duration time scale. And that has basically tremendous implication for urban flooding, right? Because now if you look at last decade or so, I mean, in India, most of the cities are witnessing flooding during the monsoon season, and that occurs because of extreme sub-daily extreme rainfall events are increasing. We also looked at that what is happening to the annual maximum precipitation, especially during 1979 to 2015. And you can see the top panel. There are regions where there has been an increase in annual maximum precipitation, but there are also regions, especially Indo-Gangetic Plain or the Gangetic Plain, you can say, there has been a decline in annual maximum precipitation. And the bottom row tells us that how the dew point temperature has been increasing over India. So we see that there is an increasing trend in dew point temperature, and this data set comes from ERA interim reanalysis data. So because dew point temperature is increasing, and we have already seen that increasing dew point temperature and surface air temperature has implications for extreme rainfall events and the intensity of extreme rainfall events that can create flooding. So in one of our papers, we have also looked at what are the observed changes in precipitation characteristics over India. And if you see like this, these are the results for 1951 to 2016, I guess. And total rainfall has declined in a large part of the country, especially over the Gangetic Plain and part of central India, Western Ghats. So this is the total rainfall change which you see in the red or yellow colors. But what is more important here to understand is that the number of days with low intensity rainfall or the amount of low intensity rainfall has also declined across the country. And then we see that there is an increase in high rainfall intensity in certain regions of the country, like Western India, especially Gujarat and Rajasthan, and also part of central India, you can see in the patches, but not except the Western India, we cannot say that there is a large part of the country that has been experiencing extreme rainfall event. But there is a very robust decline in the low intensity rainfall, and that has again implications for water resources or water availability, especially groundwater recharge. Now, let's talk about floods. So extreme precipitation are projected to increase or likely to increase under warming climate, and should we expect that floods will also increase? One thing we can note that rising extreme precipitation is sufficient to cause urban flooding, right? Because urban areas are completely different, but the river basin flooding may have a different response to increased precipitation, and that I will explain in a minute. So here what we did, we selected the Godavari river basin. We set up our hydrology model, and on your left, you can see the comparison between observations and hydrologic model simulated flow in red, and also how the model simulated flow captures the peak or peak extreme flow or floods in the scatter plots. So we can say that model is doing a reasonable job in capturing the peaks of extreme flow at different locations within the Godavari river basin. So what we found here that if you look at the annual maximum precipitation at different locations or in different sub-basins within this Godavari river basin, there is an increasing trend across the river basin. But when we look at the stream flow, we don't find a significant increase in stream flow for the same period. So what we see that the river basin flooding is controlled or governed by many other factors rather than just extreme rainfall. Of course, extreme rainfall is very important, but also the soil moisture or what are the basin initial hydrologic conditions are. So combination of wet soil moisture and extreme precipitation creates flooding in river basin scales. Now, what is going to happen in future climate? So we again did the simulations based on the downscale bias corrected data within the basin, and we looked at how precipitation extremes are going to change in the future. So there is an increasing trend if we go in the future and under different RCPs like 2.6, 4.5, 8.5. And there is also increase in extreme high flow conditions in the basin. And these are basically because in future we are going to get more sort of more rain or more intense rain, and that creates prolonged wet conditions in terms of soil moisture within the basin. And whenever heavy rain occur in the basin, it causes floods. Then sort of we replicated that analysis across all 16 river basins, major river basins in the country, and we looked at how floods are likely to change. So once again, we used downscaled and bias corrected projections. We estimated 3-day duration extreme flood events that are exceeding 20-year return period in the historic climate, that is 1966 to 2005. Also future climate, 2 periods and 2 RCPs, 2.6 and 8.5. And as you can see, this is the difference between the number of events occurring in the historic 40-year periods versus in future 40-year periods. And we can say that across the river basins, there are going to be more and more flood events suggested by these projections. And of course, there is a great difference between RCP 2.6 and 8.5 that suggests that if we are going to follow RCP 8.5, the number of floods or massive floods of 3-day durations can be even higher in the future climate. Now let's talk about droughts. So I mean, in terms of floods, we can say I would like to highlight, like, given the size of our country and also the problem of floods, I mean, there is a need to do a lot more work on the river basin or urban scale flooding. Number of studies on floods in India are tremendously low, and we have to work more in that direction because flood is becoming more and more important every year. So we also looked at what is happening in droughts, and we did like analysis or assessment based on the historic droughts, area covered by different droughts in different years. As you can see, 1965, 2002, these are based on SPEI. And then we looked at what is going to happen in future, or what are the projections given the uncertainties we have. So in one of our recent papers, we looked at using CESM 40 different ensemble members, and this data set is known as LENS, Large Ensemble from Community Earth System Model. So it is 40 different ensemble members. So these are the projections for India, how that 30-year moving with respect to 1971 to 2000, and we say that roughly about 6 to 7% increase in rainfall is projected, about 3 to 4 degree rise in temperature, and along with, because of increase in temperature, and there is also increase in atmospheric demand, that is potential evapotranspiration. And since water availability is based on the difference between rainfall or precipitation and potential evapotranspiration, we also see that number of dry events are also going to rise. Hot events are rising even much more significantly, and the concurrent hot and dry monsoon seasons are going to rise in the future, regardless that there is an increase in rainfall under the warming climate. But when we do the analysis for annual time scale, this could be even more significant, because during the dry season, the increase in atmospheric water demand could be even more significant. So we also looked at one of the problems in the GCMs is that there is not very good not very, I mean, you would not find many GCMs that have reasonable skill over the Indian summer monsoon or South Asian summer monsoon region. So what we did, out of 40 or 50 different CME5 GCMs, we found like 5 or 6 GCMs that simulates the monsoon feature reasonably well. And then we compared the projections against the multi-model ensemble mean of all 32 GCMs that you can see on bottom panel. So what is the difference?
Please summarize in another 2 minutes.
Okay, so I'm almost done. So what we see here that there is a difference. So once we look at the skillful models, we see that the dryness is going to increase in the models that have higher skills. But the models, if you do the multi-model ensemble mean, we may see that there is a lot more rain occurring there, and that is because of the higher sensitivity of these poor GCMs for convective precipitation towards temperature. Now, one other new type of extreme event that is known as flash drought, and the idea is that these occurs during the monsoon break season, and because temperature is high, so soil moisture depletes within within a few weeks time period in a very rapid sense, and that can create another extremes called flash drought, and that is also going to increase in the future because of these intra-seasonal monsoon variability. So think about, you have the monsoon break, and then you have a rise in temperature, and that creates a quick or rapid depletion in soil moisture, and that increases the frequency of flash droughts during the monsoon season in India. So here are the conclusions. I mean, I don't think I need to repeat, but there has been a considerable or significant increase in temperature. Both daily and sub-daily rainfall extremes are sensitive to warming. We have seen that there are increases in extreme precipitation in parts of the country, but there has been a considerable decline in low intensity rainfall across India. And a combination of that with wet soil moisture can create more and more floods in the future climate. Thank you very much.
Yeah. Thank you, Professor Mishra. Any questions, please? Quickly from audience. One question. Professor Mishra, so you told that annual precipitation is increasing. So, however, we are seeing the monsoon, which season that you are seeing? There is a trend of decreasing, slightly decreasing precipitation in the monsoon. So, which is the time period that you are seeing that annual precipitation is increasing?
So that is annual maximum precipitation. So you see the maximum value in entire year. Okay. Whether there is a trend. So this is not total precipitation, rather this is just single value. That is the highest precipitation in a year, and that is increasing only in Western India and part of this coastal or Odisha, and which is consistent with these results here also, where we say that high intensity rainfall is increasing in those regions.
Yeah, in fact, you had a very interesting result you presented with warming climate impacting flash floods or flash drought events, short-term drought events or seasonal drought, etc. But anyway, because of lack of time, we don't have a lot of time to discuss here.
No worries, Dr. Pai. Thank you so much for inviting, and I am glad I made it. And
thank you. Nice lecture.
Thank you. Bye-bye.
Thank you. So we will go for third lecture. Yanashilin sir?
Yeah, she's already there, Doctor.
Yeah, so we will invite Srimati Dr. N.R. Deshpande for making, you can share the presentation. Yes. She will be giving a lecture on devastating floods on the lee side of the Western Ghats of India.
Am I audible?
Yes, please.
And my PPT is also visible to everybody, no?
Yeah. No. You can share your PPT. Share your screen.
Is it visible?
No.
Please share your screen.
Just a moment, please.
Are you seeing that open share tray? And click there.
Screen, just.
Yeah.
Now it's okay? No.
No, we are not seeing.
No, is it okay?
No, we are.
Yeah, it's coming. It's coming. Yeah.
Coming?
Yeah. Okay.
Yes.
Please make it a presentation mode. Okay. Thank you. Please go ahead.
Thank you.
So good afternoon, everybody. Here I will be talking about the devastating floods of August 2019, which hit the lee side of Western Ghats, many districts of Madhya Maharashtra, specifically Kolhapur and Sangli districts. Widespread heavy rainfall for prolonged duration, that is, it started on 27th. Just a moment, please. It started on 27 July and it went up to 12th August. It was very heavy rainfall over Satara, Sangli and Kolhapur districts. They were flooded. Now, IMD report on monsoon 2019. It mentions that 2019 monsoon rainfall was 10% above its LPA. And during this 2019, 8 cyclonic storms formed over Arabian Sea, out of which 5 were on Arabian Sea. They were very intense, generally 1 in 5 per year. It is the general frequency, but this year, 2019, 5 storms out of 8 formed over Arabian Sea, and Maharashtra along with Bihar adversely affected due to these heavy rains and floods. Now, in this picture, we see that many districts from Madhya Maharashtra, that is Nasik, Pune, Satara, Sangli and Kolhapur, they were not Sangli. These districts, they received the very large excess rainfall, more than 60% of their average rainfall during this monsoon. However, Solapur, Latur, these 5 districts, they were deficit, but Pandharpur and surrounding area in Solapur experienced very heavy floods during this August 2019. This is upstream heavy rainfall of Bhima Basin here. Now these are some pictures of the flood of Kolhapur and Sangli districts. Here we see that Panchganga Nadi river water, it gushes into the many Kolhapur city. Major part of the cities were underwater for 4-5 days. And if we compare this storm or this heavy rainfall with previously occurred 2005 phenomena, then it has been observed that 2005 flood or 2005 heavy rainfall occurred in 2 spells. First one was 23rd to 28 July and second was 31 July to 4th August. Middle period was still lull or there was no rainfall in this duration. While 2019 rainfall was the continuous heavy rain spell, daily many stations received more than 10 centimeters of rainfall in Kolhapur district. Now this is the remote sensing picture which shows Sangli and Kolhapur districts. Here we see that this is the main Krishna river in blue color. This is the Varana river and this is the Panchganga river. Here we see that, and this pink area shows the flooding over on the river banks. Sangli did not receive the heavy rainfall over in this period, but in spite of that, it was affected by floods. This is because of confluence of this Varana and Panchganga river, and Sangli has very flattened river bed, and confluence of these 2 rivers made the low-lying area of the Sangli state district make more worsen flood over this Sangli. And Kolhapur, here we see that Radhanagiri and many river dams over different rivers in Kolhapur district, Dudhganga and Panchganga, they were attended their they were under full capacity. And here we see that Radhanagiri, Koyna and Varana dam at the end of July, they were fully filled with water, and after that rainfall continued up to 8 August. So these water from these rivers, these dams were released, and the simultaneous occurrence of the rainfall over the free catchment as well as catchment area give rise to this flooding. Here we see that Krishna River was worst flooded in 2019, which was more than previous big flood of 2005. At many locations in Kolhapur and Sangli, the water level crossed the previous highest flood level recorded by CWC. Here we see that this is the warning level, danger level, and this is the highest flood level. And water in 2019 was above that. Government of Maharashtra appointed a committee to study this event. 10 members were involved in this committee. Different experts from institutions like IMD, IITM, MRSAT, WRD were involved in this committee. I represented IITM. This committee brought out a detailed report on various reasoning of this occurrence of flood, impact of backwater of many structures in Karnataka. Report also suggested the technical measures to be undertaken in the future. Now, some of the reasons were shown that widespread prolonged heavy rainfall, sometimes it exceeded 200-year return period value. In Kolhapur, many stations, nearly 50% stations showed more rainfall than their previous value. Water were released from the many dams at the same time with the occurrence of the heavy rainfall over free catchment area. It has been observed that actual rainfall in various catchment as well as free catchment area was more than the 10 times of its normal value. Because of such abnormal high rainfall in free catchment aggravated the floods in Sangli and Kolhapur. Similarly, it was seen that reduction in the natural drainage area, that is the natural draining capacity of the river, was reduced due to the siltation and dumped debris in that one. Similarly, uncontrolled human encroachment on the floodplains. It was observed that in the blue line, that is 25-year return period flood, and red line, which is equivalent to 100-year return value flood, many human encroachment, many constructions were done in this area. So our committee recommended we gave some suggestions for reducing the severity of flood situation, such as the restoration or removing the dump debris or siltation or vegetation developed or man-made encroachment in this river or river bank. The raising the low river banks to restrict the inundation. Sangli, mainly Sangli, because of low-lying area, it faced the flooding. So raising of low river bank has been suggested in that area. Converting the spillway of Radhanagari. Radhanagari dam is the fully automatic, so it should be made manually operated, that we have suggested. Similarly, strengthening of the meanders. There are many meanders in the Sangli districts where confluence with Varana and this Yerla river with Krishna. So strengthening of this meander is also suggested there. Planning and managing all these reservoirs in integrated manner, that is, decision support system should be maintained. Integrated or coordination between state Karnataka and Maharashtra, it should be also maintained. And creating the temporary flood cushion. This is the temporary storages should be made available to store the excess water, which is general practice in all the Himalayan river. It is commonly available, but in peninsular rivers, we should make this temporary flood cushion for the excess rainfall. Now coming to the rainfall analysis. This is the daily rainfall pattern I have shown here for 3rd August to 10th August. Actually, heavy rainfall was received starting from 27th July to 12th August. This is the 8-day pattern. Here we have used IMD graded rainfall data to display this pattern. Here we see that nearly all days this Kolhapur district received more than 10 centimeter rainfall at many stations. Now coming to the synoptic pattern. Here we see that IMD forecasted low pressure area on 3rd August over Bay of Bengal, North Bay of Bengal. This system moved in the west-northwest direction and intensified. On 8th August, it intensified into the deep depression. And because of this deep depression, effect of this deep depression, here we see that offshore trough was also existing at that period. Similarly, this monsoon trough was slightly tilted to its south position. So combined effect of all these three synoptic situations gave very heavy rainfall over Konkan area and Madhya Maharashtra. Mumbai radar picture, here it also shows some convective cells embedded in the certiform rainfall over this area, lee side as well as some area. On 5th, it was shown over the lee side area, some convective as well as certiforms. And reflectivity was more than 30 dB Celsius, which shows the deep convection over this area. Now coming to the past studies, here we have considered data from 1951 to 2019. Daily rainfall data at many stations in these three districts, Kolhapur, Satara and Sangli. Here we see that monsoon rainfall for Kolhapur, it was nearly double of its average value. But this was the highest, 2019 was the highest. But for Satara Sangli, if we see that 2019 rainfall, seasonal rainfall, means previously it has been observed in the previous period also. Here for Satara district, we see that it is a significant rise in the seasonal rainfall. Coming to the heavy rainfall events for these three districts, this is the decadal distribution of heavy rainfall events, that is 6.5, shown in blue color. Then orange color indicate more than 10 to 15, and this is more than 15 is indicated by yellow color. Here we see that for Sangli district, it is very uncommon to observe such rainfall event of 15 centimeter and more. But for Kolhapur and Satara, it is very common. Coming to the Satara district, here we observe that these extreme events, that is events more than 6.5 and above, they are increasing significantly. And events more than 15 centimeter, their count is also increasing. Now, during this 2009 episode, Gagan Bauda in Kolhapur, Mahabeshwar, Satara districts and Karegaon in Sangli district, they recorded rainfall 34, 30 and 7 centimeter. Radhanagari in Kolhapur also received 34 centimeter of rainfall on this duration. Then from this table, we can see that coming this 2019 event, these all values, 1 day value, 2 day value and 3 day rainfall value, they are much below than the previous record. But here we observe that this previous record, they observed in at different times at different locations. But coming to the 7 day continuous total of this rainfall, it indicates that over this Kolhapur district, many stations has crossed their 7 day rainfall total in the previous record. All these stations, show that they have crossed their 7 day rainfall total, which have occurred in the previous year. Now, just to see that how this rainfall is rainfall pattern over the Western Ghat rain shadow area and this west coast or midwest side. So we have plotted these stations here. This is the elevation map of Western Ghat or west side of Maharashtra here shown. These stations lying on the leeward side, these are the annual rainfall values we have shown here. Here we observe, and this is the crest line. Black line shows the crest line of the Western Ghat. From this figure, we observe that there are many stations lying on the lee side of the Western Ghat, receives rainfall more than 150 centimeters. From this is the table which shows that this station, nearly 13-14 station, lies on the lee side of the East Western Ghat. They received the rainfall more than 5,000 millimeter during the monsoon of 2019. Now, this is contradiction to our general assumption that rainfall decreases on the lee side, from windward side to leeward side, it decreases. But there are many stations which receives record rainfall on the being on the lee side. If we notice that many of our dams are also located in this region on the lee side, where rainfall is received in substantial quantity. Our past study, here we have identified one station, Kamini. This is in the lee side, located in the western part of the Pune district. Here we have shown that rainfall at this station, Kamini, it is equivalent to the station lying to the windward side. This is in contrast with the widely accepted view that the rainfall decreases from the windward side to leeward side. This station recorded 69 centimeter of rainfall in one day during the 2005 episode on 26 July, and 3-day rainfall was 1055 millimeters in 3 days. So what will be the reason behind this heavy rainfall on the lee side? Here I will tell something about this new concept, hydraulic jump. Actually, this term comes from the hydrology. When dam water, it rushes down from the spillway of a dam, then after falling down on the ground, it splashes again upward. So this is the concept of hydraulic jump. Here, same term is applied to the in atmosphere. First time it is used. This term is used by House on his.
Two more minutes.
Yeah, okay. He mentioned in the article of orographic effect on the precipitating cloud, which has been published in 2012 in the Review of Geophysics. Here he mentioned that with a lee side supercritical flow accelerating down to the mountain, it returns to equilibrium state after forming the hydraulic jump, and again it produces the precipitating cloud there. Bhushan and Barras also shown the same characteristic. So hydraulic jump, how it is formed, it depends on the Froude number. Froude number is nothing but it is given by this formula. It is the speed, UH is the speed at height h, N is the Brent-Vaisala frequency, and h is the height of mountain, and which is given by this, N is given by this formula, where all these theta, G, they have their notations, usual notations. If this Froude number is very big than 1, then indicates the flow as supercritical, and then wind passes over the mountain. If FR is less than 1, it indicates the flow is subcritical, and then wind does not cross over the mountain, but it takes around the curvature, or it moves around the mountain. Then hydraulic jump occurs when this flow moves from supercritical to subcritical state. In the present study, we have calculated this FR value or Froude number using the sounding data taken from the Wyoming University website from atmospheric sound data, and at some where it is available at some station. Then it was observed that conditions were conducive for occurring the hydraulic jump on the lee side of the Western Ghats during this period of 2019. These are some stations I have plotted. Here we can see that more than 200 centimeter occur over the west side of this crest, and this green color is marked on edge region or hydraulic jump region. Here we observe that rainfall is in between 80 to 200, and this rain shadow area rainfall is less than 80 centimeter. These are some stations showing that during edge region, during this episode 3 to 10 edge region, they received rainfall more than 1000 millimeter in this 8 days duration, while in the same district, some stations received rainfall less than 100 millimeter. We have analyzed some dynamical parameter also during this period. This is the vertical velocity. We calculated it for windward, then hydraulic jump and rain shadow region. Here we see that for windward and edge region, large negative values have been observed at both the hours 0 and 12 hours, which indicating the vertical, this is the vertical structure of omega, existence of convective clouds over this area can be seen here. Similarly, coming to the vertical heating profile, this is the picture shown by House in his paper, Schumacher and House. They showed that pattern for stratiform, that is cooling in same we observed in this August event. For this, we have used era interim data. The same result we have seen in the running WRF model. This is the details of WRF model, and these all results supports our theoretical and observational findings. Now coming to the conclusion, I will not go in details because already they have shown here. But since this has been, such study has been carried out for the first time for Western Ghats. So we claim it is as the phenomenal discovery of the monsoon rainfall studies. And such heavy rainfall due in the HA region or immediate recent region needs to be validated for monsoon simulations by numerical models for improving the monsoon forecast.
Okay. Thank you. Thank you, madam. Gnanashilin sir, you have got any question? Dr. Gnanashilin or anybody else? A quick question. Okay, madam, your presentation of our hydraulic jump is very interesting. We would have liked to discuss more on that. Just a question in that same area, what is the contribution of a low pressure system which is coming from the east? See, leeward is for the winds which are coming from the west, but systems which are coming from east also can contribute. So what do you take on that?
Yes, generally Vidarbha and Madhya Maharashtra, they receive very heavy rainfall if any system is moving in the easterly direction. But combined effect of, I think that Ayantika paper, one paper by Ayantika Day, it also shows that the combined effect of easterly moving system as well as offshore trough and common effect gives very heavy rainfall over this area, Konkan and Madhya Maharashtra.
Okay. Thank you, madam, for your very interesting lecture.
I went very far because of time constraint.
Yeah. Thank you. So all the invited lectures were within the time and were very interesting. So all of you can actually write to them or contact them directly. All of them are well-known people, scientists. So you can contact and clear your doubts. Now we will go to the next session, presentation by young scientist. Gnanashilan, you want to say anything?
No, please. To the next session? No, it's okay. Please go ahead. Please call them.
Yeah. So we will move to the first lecture.
Can you mute the mic, madam?
Yeah. Okay. So Ratika Kanase is there. Ratika from IITM. Ratika Kanase. So we will have an oral presentation by young scientist.
She is not presenting, sir.
Acha, anybody else in her place?
Okay, we will go to the next one. We can move to the next one.
Go to the next one.
Okay, thank you. So now I will invite Ashwini Ranade.
Yes, sir, I am available.
Yeah.
Yes.
Please project your presentation. You can share your presentation and start. So please understand it is only for 10 minutes. So you should try to complete by 8 minutes so that we can have a 2 minutes question. Okay?
Yes, sir.
We will
whether my presentation is visible?
Yes.
We will,
Is it visible? Yes.
Yes. Yeah.
Okay. It's in the full screen mode, right?
Yes.
Kindly confirm.
Great.
Okay. Thank you. Thank you so much. So today I will be talking about the unusual life cycle of Indian monsoon 2020 using meteorological information system. So this meteorological information system is a new area of research. I should say a step ahead in the meteorological activity. Once we are already acquired lots of model output and weather charts, analysis and forecasted weather parameters from various operational agencies. So the main idea behind to develop this system is to provide the customized weather information, for example, about the heavy rain events, wet spells, or maybe whole about the intensification of the whole monsoon circulation, etc., to end user meteorologists in various sectors. So actually this MIS comprises of the mainly 3 parts. One is the preparation of the customized weather charts. So whatever the charts we have already available from the model output that we need to analyze and customize so that it will be more useful and more readable to the end user community, and then gives some identifiable conceivable numerical values and some effective short write-up. So I want to show what are these 3 types of components of the meteorological information system works. So before that, the main motivation behind this MIS or the perspective is that to consider the monsoon in a new way, that as we all know that monsoon is a massive thermally direct tropical circulation, and what we understand here that it evolves in association with spreading and intensification of equatorially atmospheric thermal condition. Means here it means that warmest and thickest troposphere and lowest pressure and vertical circulation structure like lower tropospheric convergence and upper tropospheric divergent and highest precipitable water. So these are the things which are available over the equator throughout the year, and we understand that it is the spreading of this type of condition northward to get as a monsoon. So as we all know that we can see the monsoon in 3 different layers. So if you see the wind system, then we can have in the lower level 1000 to 850 HPA that we are having the cross equatorial flow. It sweeps the Indian continent and then converge with the Eurasian westerlies, as well as it converge with the Pacific easterlies. Then in the middle level, Eurasian westerlies enters into the Indian continent. They form a whirlpool type of cyclonic circulation over the central India, and again they converge, and part of it they make exit from the Asia Pacific sector. And if you go to the upper level, then we can observe the huge upper tropospheric anticyclone. We call it as a Tibetan high over subtropical Asia, and its directed outflows are directed all over the globe, and in the return flow from all the subtropical highs from the lower level, it takes various meandering courses and again converges into the monsoon region. So this is the overall structure of the monsoon, and with this understanding we move forward for the meteorological information system. So major component of MIS is the customized weather chart. So here we are having 4 types of weather charts. First is the equatorially conditioned global charts. As I say that we have considered the equatorially atmospheric condition as a reference. So by taking the anomaly from the equatorial value, we have prepared the equatorially conditioned weather charts in, we call it as a EC. So EC precipitable water, EC MSLP, level wise EC temperature, as well as EC tropospheric temperature, level wise EC geopotential height and EC thickness, as well as we are also having the global weather regime. So this is also another new concept, that if we combine the EC temperature and EC geopotential height, then we can divide the whole globe into 4 types of weather regimes, like warm low, warm high, cool low and cool high weather regimes. I will just show the pictures of that. And then the third is the area under monsoon conditions. So in this global regime, warm low regime, where the equatorially temperature is higher than the equator and geopotential height is less, and if we add the MSLP and as well as the precipitable water, then we can get the area under monsoon conditions. So, and last one is the departure from normal weather charts. So main idea behind to develop the charts is to visualize the monsoon on day-to-day basis. So then in the second part, we also want to give the quantitative information, that is the area averaged values of the different atmospheric parameters for the whole globe, hemispheric, zonal and 54 geodomains across the globe. And then we have defined the criteria, or we are giving the criteria for defining the start and end of the effective summer and winter season for the northern hemisphere as well as southern hemisphere. And in the third step, start and finish of effective global atmospheric thermal condition over 19 subregions of the country, and then the start and finish of effective Indian monsoon condition over 19 subregions. And end after finishing is that start and end of the monsoon rains over the subregions of the country by giving the different rainfall thresholds. So this is the picture of the equatorially conditioned parameters. So EC tropospheric temperature, left panel shows EC TT, then EC thickness, EC MSLP. So these charts are on the peak period of the monsoon in 31st July 2020. So you can see that in the peak period of the monsoon, tropospheric temperature, EC temperature is 8 to 10 degree higher than that of the equator, or then geopotential height can go up to 100 to 150 meter more than that of the equator, and also very intense MSLP field 10 to 15 millibar lower than that of the equator. And then this green color indicates the precipitable water almost 10 to 20 millimeter more than that of the equator. So I just want to show the animation that how throughout the season from 1st May to 31st October, how this equatorially conditioned parameters changes their structure and how it spreads all in the monsoonal area. So similarly here MSLP and precipitable water, I just want to show you that. Yes, sir. So these are the charts, and then what I am talking about the global weather regimes. So these are the 4 weather regimes which I am talking, that you can see that this is the green, it's a 700 HPA weather regime. This is the green part, which is the warm low regime at lower level, and this is the warm high regime at the upper level. So day-to-day basis, these types of charts can give us the information about the extent of the monsoon. So this is at the 700 HPA. At the peak period of the monsoon, this extent is changing, means up to 400 HPA. Also sometimes we can see this warm low regime as well. Now if you add the MSLP and precipitable water as well, then you can see that this is the blue area, which is showing the area under monsoon condition at any particular day across the India. So this is the area where monsoon condition is prevailing. Now any rainfall within that monsoon region, we can say that that rainfall is a monsoon rainfall. So this is the 5-level approach we have adopted to evaluate the Indian monsoon. I'm not going into the details, but first we need to analyze all these charts, define the thermal condition, and then go to the defining the dates of the monsoon. So the tropospheric temperature thickness index is the index we have developed to understand the whole monsoon condition. So this is the based upon the tropospheric temperature and thickness. So for each hemispheric zone and subzone we have defined, and we find it that the effective global atmospheric thermal condition usually started on 22nd May, means started on 22nd May in the year 2020. So you can see that here throughout the season, this TZI index is much higher than that of the normal in 2020 for northern hemisphere as well as for southern hemisphere. And if you see the northern hemisphere, southern hemisphere contrast as well, it is much higher. And in the Tibetan area also, it was comparatively to the normal, but then afterward it regains its intensity. So based upon this in different parameters, we have defined the give the criteria for the start and end of effective Indian monsoon condition for 19 sub-regions of the country. And then after attaining the Indian monsoon condition, we can go for the Indian monsoon range. So here the threshold can be subjective based upon the end user requirements. So here we have used the rainfall threshold, mean rainfall of 10 days before and 10 days after the normal starting date, and we got in the year 2020 as the 29th May is the start of the monsoon rains over the Kerala, and the 25th June over the Northwest India sector, and also similarly for the departure dates or withdrawal dates, I should say. So in total, I just want to conclude that the effective global atmospheric condition is in the year 2020 is 4 days earlier and 11 days later, while the monsoon rainfall in southern peninsula started 4 days earlier and over the extreme North India 4 days later, while the rains finished in the extreme North India 3 days early and 20 days later. And in total, the effective Indian monsoon condition started 1 day earlier than the Indian monsoon condition and finished 3 days later across the country. And from the MIS, what we have observed can conclude the performance of the monsoon to 2020 is that the troposphere was warmer and thicker throughout than normal throughout the year and over across entire globe. So there was a warm low regime, that green area, lower tropospheric warm low regime, that was much larger and spreads over the Indian domain and also Bay of Bengal and Arabian Sea. But it was not that much spread in the northern part of the India. While at the upper level, warm high and anticyclonic circulation, which we have seen in divided into the two anticyclonic cells always, but in the 2020 they are most stretched extreme westward as well as extreme eastward. So in total, the warmer and thicker troposphere which was observed throughout the boreal summer, the monsoon circulation was in days, and that's why produces higher than normal rainfall over large part of the India, but not in the extreme North India. So thank you so much. I would like to acknowledge Director NIH and DST SCRB for funding support, and as well as IMSP Pune for giving me the chance to give the presentation here. Thank you so much, sir.
Yeah. Ashwini?
Yes, sir.
Ashwini ji, so it was
yes,
a nice presentation. Did you develop the software by yourself or?
Yes, sir. Actually, right now I have analyzed all these charts. We have analyzed from 1979 to 2020. All charts are means lakhs of charts I have prepared, but now my next step is to use the GIS geographical information system, because we are adopting the architecture of GIS to make it on the real-time basis. So the real-time basis, how to do it, that I am working on that. So that on each day we can give these types of charts to visualize the monsoon condition and rain producing weather system. But we have used that MIS for various extreme events as well.
See, one user interactive web-based MIS will be maybe very useful for forecasters and researchers.
Yes,
so
sir.
if
Yes,
you
sir.
interact with the forecasters and researchers, you can develop this type
Yes,
of
sir, yes.
visualization system that will be of very use.
Yes,
Anyway,
sir, I'm
thank you
working on that.
for lack of time. We will not go for more discussion. Thank you very much for nice lecture. Now I will go to the next lecture. It is by Mr. Harveer Singh, NCMRWF.
Yes, sir.
Yeah, so you can share your presentation and start immediately.
Yes, my presentation visible?
Yes, yes. Harveer,
okay.
Please.
Yes, sir. Yes, good evening to all. Actually, I'm presenting this special verification for cyclones Amphan and Nisarga for using MAT or MAT plus mode. So here is the outline. So I'll go to the introduction part. So this is the object-based diagnostic evaluation is a special verification method which provides information which is not possible to obtain using general tradition grid point based verification methods. It objectively identifies simple objects in rainfall fields at different thresholds which could mimic what human call regions of interest. So this process is multi-step, one which called the convolution thresholding technique. It basically involves application of a simple circular filter, which is in terms is a function of a convolution radius. So data set I have used here. This is for IMERS data I have used, and which is available half hourly. It's a 10 kilometer resolution, which I converted into the daily 03 GMT to 03 GMT. Then model forecast data I have used. This is NCM, and that is National Center for Meteorology and Weather Forecasting Unified Model data. And this is 12 kilometer resolution, which is again converted, degraded to the 0.1 by 0.1 degree, that is 10 kilometer. So here's the motivation is if suppose we have forecasted two events, like here is given forecast and observation events A, B, C, D, and E. So first four events, if they are for predicted, so which is the better? So here for the correlation and other statistics are coming around nearly zero. So for the case of E, so it is giving some skill. So that is my forecast has some skill, that is model has some skill to predict the weather. So methodology I am using here is which is given the Davis paper 2006. So it's step one is just the raw data. Here is I am considering precipitation, and apply here for the convolution threshold, then masking the region, then again finding out the its attributes. So convolution and masking, that is convolution is just the threshold for the rainfall, like 10 millimeter, 20, 50 or 100 or more than that. For heavy cases I have used more than 100 millimeter sometimes. And masking region, actually for that particular threshold we have masked the that field, and it make some objects. Then finally we have to compute some attributes. Here given lot of attributes, so I may be showing here one or two attributes. So going through this Amphan cyclone. In Amphan cyclone, actually I'm presenting there the 20th May, the cyclone hitting near the coast of Kolkata or that region. So it is observe rainfall and giving for the IMERS observation. So day 1 to day 5 here is presented. So here is the threshold, rainfall threshold greater than 120 millimeter, that is very high rainfall. And here is the matching objects. This one is for the observation, other are the day 1 to day 5 objects. So similarly for the third row,
third row is for 140 millimeter, and again it is very well matching objects. So up to 200 millimeter, we can see the at the day 4 there is a mist, or we can say the model has predicted that rainfall, that amount of rainfall, one greater than 180 or 200 millimeter rainfall, that is slightly eastward. So the object is not matching with the observation. So here it will not give any of the statistics for that case. But for day 5 it is matching. So it will give some statistics. So like here is one example for this one. So here it is day 5 forecast that is valid for 20th May, and here it is giving its statistic. So this figure is giving here the observation objects with the forecast outlines, and which is very well matching the objects. So here it will give some statistics like here it is center distance. Center distance is the quantitative measure of forecast spatial displacement. So how much the displacement error? So it is 2.35, that is the grid size. So grid size is 10 kilometers, so around 23.5 kilometer is the distance. This center distance is there. Angle difference and so many things are there. So total interest is equal to 1, which is good. 0 is the worst and 1 is the best. So here is the forecast area and observed area also. It is giving in the grid squares. So in grid square actually it is giving like 128 by 136, 0.94. So it close to 1 is very good. So that is provides an object measure of whether there is an over or under prediction of areal extent of the forecast. So same some other statistics also like symmetric difference. Symmetric difference is summary of statistics for how well forecast and the observed data matched. Small is very good. So finally coming to the total interest. Total interest is a summary statistic derived from the fuzzy logic engine with the user defined interest maps for all these attributes plus some others also. So close to 1 is very good, as I mentioned earlier. So samely I'm presenting for the Nisarg. Nisarg case also it is giving. So here total interest is coming 0.95, that is very close to 1. So it is giving also very well in the day 5 forecast. So at the 80 millimeter.
2 more minutes.
Okay, sir, I'm just finishing. So finally coming to this object based diagnostic. So you can see 20 millimeter, 40 to up to 100. Actually earlier Amphan was a super cyclone and this was a cyclone. So that much the intensity of rainfall. So 100 millimeter rainfall is in day 1 actually it is giving very less, means very small objects. But day 2 onwards it is giving the very good means rainfall of objects. So it is giving the good objects. So here is the summary. So from the object based diagnostic evolution, so central distance is nearly 23.5 kilometer, area is close to 1. So total interest also close to 1. So thank you.
Yeah, nice presentation, Harvir. Just one question: how you get that observed rainfall based on what data that you know that object you create area, extreme rainfall area?
Yeah, actually the what is I called it is a convolution threshold for that particular object. So it will mask the region, the particular threshold. Only that threshold or greater than that value will be masked, and
you can get from forecast, but what is the observed data that you use?
IMERS data, sir. Observed IMERS data 10 kilometers. Yes.
Okay. Thank you.
Okay.
Thank you.
Thank you.
So because of lack of time, we will not have question. Now I will invite Raghavendra Ashri. So please share your presentation. Dr. Ashri is there? Yeah.
Yeah.
Yes, please.
Can you see my first slide?
Yes.
Now I'm making it in full screen.
Yeah.
Thank you. I'm going to discuss quickly about the extreme rainfall events over Mumbai in recent years and what are the forecasting challenges and how we perform.
I think a full screen is not.
Full screen is not coming up.
Yeah.
It's coming, right?
Not coming.
I have made another login and I am able to see the full screen.
Okay. Please continue.
If anybody else is like, can confirm, it will be good.
No, we cannot see the full screen.
Sir, it is not full screen.
Very strange. I'll just unshare and share again.
Yeah.
Please share this full screen.
Yeah, that's what I did. There seems to be some problem when we do the full screen.
Sir, first you full screen, then share.
Okay, I'll try to do that.
Please share the full screen.
No, not now.
Okay, it's coming. Now it's coming. Now open the presentation.
I am not seeing that.
Please open the presentation. So click the presentation.
Yes. Maybe I will share. I will without making the full screen.
Yeah.
I'll share it.
Yeah, please. Let us not waste.
What I can just maximize it.
Yes. Yeah. Please continue.
Okay. Technical glitches always add to further delay. Just to go through is extreme events have always, like we already know it, because of climate change they are increasing, and especially with reference to the Mumbai region, the extremely heavy rainfall, which IMD defines as a threshold of 21 centimeters, that is like making a lot of news in recent years, and it often leads to a lot of flooding and things like that. What is happening is there is a lot of promise from the modeling activity, like high resolution models show improved capability, but however there are a large number of uncertainties and things like that. I'm moving to the next slide, and this is just to highlight the events during 2018 and 2019. We can clearly see that very often we have rainfall activity breaching the 200 millimeter threshold. So we had several events, nearly 5 events during 2018, and also during 2019, almost again a repeat of that kind of number. Moving to next slide, I am trying to show here from the observations for 5 events: 29th June, 2nd July, middle panel, 27th July, as well as 4th August and 5th September. These are like 5 times in 2018 when Mumbai experienced extremely heavy rainfall events, and we see that it is not just confined to a small region or something like that. It's actually a very widespread and affecting large parts of that region. Just to highlight that this is based on the merged satellite and gauge observations. And similarly, from other satellite derived products also, we could clearly see that this is fairly widespread heavy rain activity. And also we know from historical studies and that these are associated with metropospheric cyclones. And here we have just shown it with circulation anomalies, like for the 5 cases, and we clearly see troughing or the full cyclonic type of circulation anomaly in the neighborhood of west coast of India near Mumbai and Gujarat. This is a very, very well defined large scale type of this thing. So any reasonably good model should be able to produce a good forecast of this. At NCMRWF, we have the modeling suite, unified modeling system, which is used for medium range prediction. We also have a 4-kilometer mesoscale system as well as the global ensemble prediction system. The three modeling configurations highlighted in red square where I'm showing in the cursor, these are the ones I'm trying to pay attention and see how we are performing and how I'm moving to the next slide where I'm showing our region of interest would be like the west coast of India, which is very complex topography, and we can clearly see here we have a very dense network of rain gauge observations here, and which is what we have used for evaluation. Moving to next slide, this is for the case of 2018. Simple analysis clearly indicates that by and large the models tend to underestimate the rainfall. I have compared the observations from satellite into 3 different analyses. So models normally don't capture the peaks, although they have tendency to indicate it, but however the peak actual amounts are not captured. That is just to indicate in day 1, day 3 and day 5 forecasts. However, relatively we have found that the 4-kilometer regional model is performing better compared to other models. So going ahead for this year 2020, we had picked some cases. This is I'm showing evolution of rainfall spell in the early July, like bottom panels show rainfall activity from 2nd, 3rd, 4th and 5th of July. These are some of the cases. Similarly, we have for August also. I will not dwell into each and every panel. And if we clearly see like for top panels indicate for 4th and as well as in the month of August, we can clearly see here. I don't know if headings are visible. Yeah, this is for 4th of July and this is for 5th of August. The middle panels are from the regional model, 4-kilometer regional model, which is performing much better compared to the global model, which is also fairly good. This thing, it is able to predict rainfall excess of 8 centimeters and things like that, which are like it's a big rain. Still, the peak amounts are missing in the global model. So this is some of the challenge that we have. Generally, we have displacement errors and things like that. By and large, overall, for accounting for the whole season, this is the type of statistics that we get. We have the 4-kilometer regional model slightly doing better compared to the global model. The correlation, the scatter plots all indicate that your regional model is performing better, and it could be used for flood forecasting and things like that. And that's the reason yesterday, like Dr. Hosalikar was showing, this model forecast is used for Mumbai I-flow system. What I would further highlight is this is not adequate. We need further to carry out methods to further improve the forecast, and this is one example which I'm showing here. Without calibration, these are the types of biases that you see in blue dots, and after bias correction and calibration, this is the type of improvement that we can achieve. That is what is shown here. These are the types of improvements that we are trying to carry out in NCMRWF. These are some of the challenges that we are trying to overcome so that improved products could be used for applications of flood forecasting. In addition to this, we have ensemble system. This is one example I can show where for this particular case of say 5th August, okay, the right panel shows the case of 5th August where you have rainfall exceeding like 16 centimeters in 24 hours and all over different parts of eastern part of Mumbai and things like that. And we see that ensemble based products, these are the probabilistic forecasts. The top one is for based on 2nd, middle one from 3rd and bottom one from 4th. They clearly indicate probability, higher probability of extreme rains and heavy rains. That is what we see, which some of the information that is missing from the deterministic systems can provide and like extremely useful for decision making. These are the last 2 slides which I showed. One is the bias correction and use of ensemble products. These are the 2 types of improvements that we wish to carry out, and in the coming years these 2 will be mainly put to test. That's all from my side. I have just listed out with focus on rainfall of 200 millimeters and things like that. It's a big challenge, and like models, although they produce, either they overestimate or underestimate, there could be false alarms and things like that. But to overcome the uncertainties and all, we need ensemble prediction system, and the products from ensemble have to be applied for flood forecasting. In addition to that, the bias correction for location specific forecast, which is definitely needing, it means it needs a lot of background data, a lot of large, like 50 years of 100 years of data where we have data from the locations. But it could be still a challenge, because like many of the extremes maybe we will not have during the training period, so it could still be a challenge. That is where the ensembles come into picture, and effectively this will be useful for extreme forecasting over Mumbai region. Thank you.
Thank you, Dr. Ashrit. It's a nice presentation on extreme rainfall over Mumbai and how that has been predicted by NCMRWF and its performance. Because of lack of time, we will not go into that. So thank you very much. We will go to the next speaker, Anumeha Dubey. So Anumeha is there?
Yes, I am present here. I'm just going to share my slides.
Yeah, please.
Are my slides visible?
Just wait.
Yeah.
Yes.
Yes.
Okay. This is just a sort of a continuation from Dr. Ashrit's presentation, as he was just mentioning that there is a calibration required for the location-specific forecasts, particularly over Mumbai city, and for that we need a long-term data. So this is just the first step in that direction for the calibration. What we have tried to do is analyze the observed maxima of rainfall over two locations over in Mumbai, that is Colaba and Santa Cruz. So we have carried out a kind of a statistical analysis of the observed rainfall over these locations. So the objectives and the motivation behind this study is, first of all, we want to analyze the spatial and the and take into account the spatial and temporal variability in the maximum rainfall during the monsoon season, as just looking at the climatological average or a long-term average of rainfall is not enough, particularly for a decision-making process, and we need to take into account the kind of spatial and temporal variations that are present in the rainfall, particularly even if the two locations are quite close to each other. So for this, we need to do a statistical analysis of the intensity of rainfall at a particular location, and this is achieved by performing a frequency analysis. And one of very important products that we obtained from the frequency analysis is the return period rainfall values, which can be of immense use in disaster management and policy making processes. So coming to the methodology, we have, as I said, we have performed a frequency analysis of observed rainfall for Colaba and Santa Cruz stations in Mumbai. These two stations are located around 20 kilometers, at a distance of 20 kilometers from each other. The rainfall that is available at Colaba is for 100 years, that is 1915 to 2014. We have taken in this analysis. And for Santa Cruz, it's about 66 years from 1949 to 2014. So the kind of spatial variability is seen in the time series plot here. So during the 2005 case of heavy rainfall in Mumbai, the observed rainfall at Santa Cruz stations was in excess of 940 millimeters per day, whereas at the same time, just 20 kilometers apart, at Colaba, it was in excess of around 200 millimeters per day. So that kind of variation is seen in a small city where the stations are very close together, and a huge difference in the rainfall intensity is seen there. So in the current study, we have used the maxima of the rainfall, the annual maxima, which is essentially just the maxima of the rainfall during the monsoon season, because these two stations mainly receive rainfall during the southwest monsoon season. So in the frequency analysis, what is really done is theoretical distributions are used, and they are fitted to the observed variable, and the parameters of each of the distributions are estimated based on those observed values. So the distributions that we have used are very commonly used for fitting of rainfall observations. They are gamma, V-bull, log normal, log logistic, Gumbel, and the generalized extreme value distributions. So GEV actually is obtained from the extreme value theory, which is used mainly used for the statistical inference of rare or extreme events. And this distribution combines three kinds of distributions: type 1, type 2, and type 3 extreme value distributions, that is the Weibull, Fréchet, and the Gumbel distributions together. So the parameters of each of these distributions are estimated. So we have actually used two methods for estimation of parameters: the maximum likelihood estimation and the minimizing distance or the maximization of the goodness of fit statistic estimation of parameters. So how do we ascertain that a particular distribution is the best fit? Is by using the goodness of fit tests, and three different kinds of tests are used in this case: the Kolmogorov, Smirnov, Anderson-Darling, and Kramer-von Mises, which are very popular goodness of fit tests. And the distribution which has the lowest value for these goodness of fit tests is considered to be the best fit for that particular observation. So coming to the frequency analysis, so we see that for both the stations, Colaba and Santa Cruz, when we plot the observed density, so we see, and then we have the PDFs, the probability density function from each of the theoretical distributions. We find that in this case, the Weibull and Gamma are these two curves which are very, which are actually not providing a good fit, but the others are pretty close by, especially if we look at the log logistic, the GEV, and the Gumbel. They are actually providing a pretty good fit in both the cases for both Colaba and Santa Cruz. Similarly, if we look at the empirical and the theoretical CDFs from the data as well as the theoretical distributions, we again see that Weibull and Gamma are the ones that are furthest away from the empirical curve, and the rest are pretty close together. So we can say that the log logistic, GEV, and Gumbel are the best fits looking at these figures, and Weibull and Gamma are not really working out in this case. Another way of looking at the best fit distributions is by comparing the quantile, and the probability plots. So we can see from the quantile plots also that the curves which are really aligned along the 1:1 line are the GEV, log logistic, and the Gumbel, whereas the Gamma and the Weibull are very far away. In fact, the Weibull distribution is underestimating at lower quantiles and it is overestimating at the higher quantiles. But one thing is common for all the distributions, that the outliers are not really captured, particularly for Santa Cruz, where we have that huge rainfall of 900 millimeters per day. So a probability plot essentially compares the cumulative distribution functions of the observations and the theoretical probabilities. And once again, we see that the ones that are aligned along the 1:1 line are GEV, Gumbel, and the log logistic. So it's essentially stating the same thing here, that Weibull and Gamma are not really fitting the distribution, the observations quite well. So another thing that the objective of this study was to compare the estimation of parameters by using different parameter estimation schemes. And by this time, we had already found out that the generalized extreme value distribution, or the GEV, was the best fit based on the goodness of fit tests. And so we wanted to see if the estimation of the estimated parameters would have any effect depending upon the scheme that we had chosen. Yeah, sure. I'm just finishing up. So we have found out that in this case, the parameter estimation done by the maximization of goodness of fit is actually doing a much better job as compared to the maximum likelihood estimation. And so we have decided to go ahead with that. And since the parameters of any distribution are estimated based on a limited observation set, so we have also decided to find out the 95% confidence interval for the parameters by using bootstrapping. And this is the pictorial representation of the CDFs based on the 95% confidence interval. And we can easily see that the empirical CDF lies within the 95% confidence interval in all the cases. And this is the 200-year return period rainfall and the 95% confidence interval for that, the same thing. And we see that the dots, that is the observed return periods, are always lying within the return period, the 95% confidence interval. And once again, we find here that the parameters that are estimated by using the MGE method are actually fitting well to the observed return periods as compared to the other one. So the major conclusions is that the GEV distribution is able to provide a very good fit to the maximum observed rainfall at the two stations in Mumbai, and the 95% confidence interval for the return period as well as for the parameters is also able to fit the maximum return period of from the observations. And as I said in the beginning, that this is a basic step, that is the first step that can be used for correcting the biases and the calibration of forecast to obtain a location-specific bias-corrected forecast. So thank you very much. That's it from my side.
Thank you, Animeha. Very nice presentation. So because of lack of time, we will move to the next presentation.
Absolutely, yeah. Thank you.
Sahadat Sarkar
Yes,
from
sir.
IITM. Please share your presentation.
Are you able to see the presentation, sir?
Yes. Yeah, you can make it full screen. Good.
Yeah.
Please continue.
So I'm going to present the anomalous synoptic activity during August 2020. So we'll use the approach like energetics approach, and also I'll try to evaluate the GFST on 534 model in capturing the processes. So if you see the August 2020, it was very active in terms of the low pressure system. According to the IMD report, so August 2020 was witnessed 27 days low pressure days compared to the normal 15 days. So the question that we are going to address here is that what might be the reason for this extreme synoptic activity, and also we'll see that how the mean flow and the synoptic eddy interaction processes and how the GFS model is able to capture the process. So if you see this picture, so there is a like back-to-back system has formed in the August, and the GFS model has a very good fidelity in capturing this. The solid line shows the observed track, and the dotted line shows the GFS track. So GFS is able to capture the LPS track in pretty well, with slightly deviation in the with the increasing lead time. So to understand that, actually we are using the sum of the mean kinetic energy budget and the synoptic EK and the ISO scale energy processes. So left side shows that this is the August mean kinetic energy based on the climatological value, and right side shows the GFS analysis for August 2020. So it clearly shows that the mean kinetic energy for August is more compared to the climatological value. But how the GFS model has performed in capturing these processes, this mean kinetic energy. So this is the forecast for 24 hour and 72 hour and 120 hour. That is the 1 day lead time, 3 day lead time, and the 5 day lead time. So GFS model has captured pretty well this mean kinetic energy processes, mean kinetic energy for the August 2020. So now the question that we are going to ask that the August 2020, the mean kinetic energy was more than the climatological value. And the Sarkar et al. 2017 has shown that if the mean kinetic energy more, that is the background, if it is strong, then it will transfer that energy to the eddy scale efficiently. So if that is the true, then here we will expect that there will be conversion from MK to EK. So this is the background step to the synoptic scale conversion. And again, the left side shows the climatological value of August based on 1998 to 2015, and right side shows the values for August 2020. So we can see that over the Indian region, and so the this energy conversion processes is more. The negative means that there is a conversion from the MK to EK, that is the background to the synoptic scale. So the synoptic scale, it's showing that in August 2020, the synoptic scale was more active than the climatological value. And this is the GFS model fidelity in capturing the conversion in 24 hour, 72 hour, and 120 hour lead time. So model has captured pretty well So this is the, you can see this is the, say this one is the observation, and if we compare with this one and with the model forecast, so model has done a pretty good job, but only if the lead time has increased, so this conversion process has slightly underestimated. But the question is, as there is a conversion from MK to EK, so we'll expect that the synoptic scale eddy kinetic energy will increase. So this is the synoptic scale eddy kinetic energy at 850 HP level. Again, the left side shows the climatological value and right side shows the values for August 2020. So it clearly shows that the August 2020 has the more synoptic scale eddy kinetic energy than the climatological value. So that may be helping the synoptic scale system to gain the energy from the background state. And if you see the model forecast, although the model has slightly underestimated, but the model is able to capture this synoptic EK over the Indian region. If the synoptic scale energy is getting energy from the background, so how is the ISO scale energy? So this is the ISO scale kinetic energy at 850 HP level. So left side shows the climatological value, right side is the August 2020 value, and this lower shows the 24-hour forecast, 72-hour forecast, and 120-hour forecast. So the climatological value, you see that it is over Indian land masses, it has a more active ISO scale energy, but for August 2020 it is slightly less compared to the climatological value. This means that the synoptic scale was more active than the ISO scale, and synoptic scale is also extracting energy from the ISO scale. That we have analyzed this AD-AD interaction, and it shows that there is a positive conversion from the ISO to the synoptic scale, although we are not showing it here. And the synoptic scale is also extracting energy from the background. And if you see the model forecast, model has also able to capture this positive isoscale kinetic energy at 850 HP level with sufficient lead time. But now the question is, if the mean kinetic energy to eddy kinetic energy conversion is increasing, this means the mean energy should decrease. But I have shown in the first slide that the mean kinetic energy is also increasing. Then the question that we are asking that how the mean kinetic energy is maintaining its energy, if because the conversion from mean kinetic energy to the eddy scale or the synoptic scale should decrease the mean kinetic energy. So here is the answer that the mean available potential energy. Mean available potential energy is nothing but the thermally direct circulation. If there is a heating in some places, so this will create the mean available potential energy, and then this mean available potential energy will convert to the mean kinetic energy, and once the mean kinetic energy is strong, so that mean kinetic energy will transfer to the eddy scale. So if you see that the August 2020, so the mean kinetic energy, mean available potential energy to the kinetic energy conversion was more compared to the climatological value. So this has helped the mean kinetic energy to strengthen during the August 2020. And which has helped the synoptic scale to extract more energy from the mean. So if you see that the model forecast in 24-hour, 72-hour, and 120-hour lead time, so model has also able to capture this mean available to mean kinetic energy conversion and with sufficient lead time. At least in 5-day lead time, also model are able to capture that. So here I am summarizing the thing. So we have a background state. So this background state, the synoptic scale eddy kinetic energy is extracting energy from the background state. But the background state, how it is maintaining its energy? Because there is a conversion from mean available potential energy. That is the conversion from the
2 minutes, 2 more minutes.
Yes, sir. Yes, sir. So from mean available to there is a conversion to the mean kinetic energy, and then mean kinetic energy gives the energy to the synoptic scale system, and also the ISO scale is helping the increase in the synoptic scale system. So this is the eddy-eddy interaction, and this portion shows the mean flow and eddy interaction. So this is my conclusion. The MKE for August 2020 was more than the climatological value, as the background state to the synoptic scale conversion is more for August 2020 as compared to August climatology based on 1998 to 2015. So due to that, the synoptic kinetic energy is more for August 2020 as compared to climatological value, and then this MK is maintaining the energy due to positive conversion from mean available to mean kinetic. And the GFS model has a good fidelity in capturing this energy conversion process. Thank you, sir. So thank you for your attention.
Yeah, thank you, Sarkarji. So now we will move to the next presentation by Mr. Avijit Day.
Yes, sir.
Yeah.
I am just sharing.
So it is on intra-seasonal fluctuation of ISMR and its relation with MJO and mesophases.
Are you able to see my slides?
No.
No?
No, it is not seen.
1 minute, just 1 minute. I'll share it again then. Now also no?
No, Mr. Day.
Oh, is there any technical?
Jnanashilan, are you able to see? I am not able to see.
No, not.
So,
Avijit, just first you open the presentation. Then
I think
share the
he
screen.
has left and again coming back, I think.
Click open share tray, then share it.
I think, he has logged out and again coming back.
Oh, okay.
So meanwhile, you want to say anything?
It's okay. So this is the last presentation.
This is the last presentation.
Yeah.
So our
Actually,
Emmanuel and Sunil Kumar is there, no?
We can ask some questions on Sagadat's presentation.
Yeah.
Any questions?
Any
questions from the audience?
Yeah, from audience regarding GFS model fidelity on anomalous synoptic activity,
especially energy conversions.
Yes, yes. So as you know, August there was a lot of low pressure area activity, almost 27 days of activity were there, which was more than normal. So whether GFS was able to capture this?
See, Avijit, first open the presentation, then click open share tray.
Avijit, are you back? Yes.
Yeah,
great.
Fine.
Great.
So, presentation mode. Okay,
great.
Okay,
yes.
Good.
Please. You can start, Avijit. I think your mic is mute.
Your mic. Avijit,
unmute karo. Your mic is mute. Unmute karo. Mic.
Unmute your mic.
Yes.
Now presentation mode.
You can make a full screen. Avijit, are you hearing us?
Yes, yes.
Yeah. So you can now project your presentation, make it full screen. Here is the last presentation. Try to complete within 10 minutes.
I am not able to see here. Some problem is there.
No problem. You are right to it. Make a full screen and start presentation.
Yeah, we are seeing.
You are seeing my screen, right?
Yeah. You please go ahead.
Go ahead.
Make a full screen.
1 minute.
Presentation. Please make it presentation mode.
slide share karo.
Again, I'll share.
Array, why did you leave?
Sorry, sir.
Don't go out, don't go out. Just to share only.
Now,
Yes,
is it okay?
Fine. Please
Yes,
go.
sir.
Start.
Okay. So I will be talking about interseasonal fluctuation of Indian summer monsoon and its relation with MJO and MESO phases. So as we know that northward propagating MESO and eastward propagating MJO, these two are the most dominating mode of interseasonal fluctuation. Although MESO exists only during the summer, but MJO exists round the year. But MJO is weak during the boreal summer and it peaks only in boreal winter. Although MJO is weak during boreal summer, but still it influences climate and weather phenomena during the monsoon season. In the current study, we will examine the relationship between the interseasonal fluctuation of Indian summer monsoon rainfall with the phases of MJO and MESOs. These are the data set I have used. I have used IMD graded data set Pi et al. 2014 and IMD TRMM merged data set Mitta et al. 2009 and NCEP Anchor zonal wind I have used and NOAA OLR I have used. And principal component of MESOs are computed based on the extended UF analysis of Suhas et al. And pieces of MJOs are computed based on extended UF analysis of Day et al. And I have, for time filtering, I have used Lange's filtering. So these are some of the result I will show. So here what I have done, I have calculated during mid-June to mid-September, I have calculated all active and break days from 1998 to 2018. And this in the left panel, I have plotted for those active days MESO pieces in the scatter diagram. And similarly in the right panel, it is for break days. And in the lower panel, I have plotted the frequency of active days with MESO phases. And similarly, in the right side, it is with break days. So if you see this diagram, it shows that during phase 2 to 5, most of the active days occurs during MESO phase 2 to 5. And most of the break phase occur during MESO phase 6 to 8. So there is a clear-cut relationship between the MESO phases and active and break days. Now here I have plotted the same for MJO phases. So if we see the for MJO phases, it shows that during phase 3 to 6 most of the active days occur, but some few active days occur during phase 7, 8 and even during phase 2 also. And most of the break days occur during 6 to 8 and during phase 1. So, but for MESO we have seen there is a clear-cut relationship, but for MJO that relationship is not so clear. Here I have plotted the phase composite of unfiltered rainfall anomaly for 8 MESO phases, and in the upper panel, and in the lower panel it is for 8 MJO phases. So like phase 1, 2, 3, 4, like that up to phase 8. And from this phase composite plot, we could see that during phase 2 to 4 and 5 also, during MESO phase 2 to 5, we see the northward movement of the rain band, and most of the active days occur during those phases. And for MJO, during the phase 3 to 5, most of the active phases, active days occurs. and there is a lag. If you see the phase 1 composite for meso, it is more or less similar to, it looks more or less similar to phase 2 composite of MGO. So MGO composite leads mesophase composites by roughly 1 phase. Here I have shown the same phase composite for unfiltered OLR and wind at 850 HPA anomaly. Here also this plot also show similar like phase 2 to phase 5, it is showing active like condition, although there is a few days lag compared to rainfall composite. Here I have plotted Hofmuller diagram of from the same phase composite averaged over 65 degree east to 95 degree east. So these are the phases, phase 1 to phase 8, and again this phase 1 to 4 and phase 4 to 8 are repeated for the display of continuity. So this shows that for precipitation, for meso case, there is a strong and organized northward movement, but for MGO that movement is not that much strong. And in the lower panel, I have plotted the same for OLR and vorticity at 850 HPA anomalies. So from there also for meso, the northward movement is strong. And here one important thing to notice that negative vorticity anomalies is located to the north of the negative OLR anomalies. So that wind and circulation and convection, they are coupled. So both the meso and MGO, they propagate as a convectively coupled system. Now I have shown the phase composite for the meso and MGO filtered rainfall. For filtering, I have used regression-based reconstruction. So pieces of meso and MGOs are with the rainfall parameter, they are regressed for a longer period, and regression coefficient are obtained. And from that, we have reconstructed the meso filtered and MGO filtered field. These reconstructed field are much more organized compared to unfiltered field. And here the Hofmuller diagram of the reconstructed field, that also shows much more organized northward propagation. And in the right panel, I have shown the explained variance percentage, explained variance in percentage by meso reconstructed rainfall, and in the middle panel MGO reconstructed rainfall, and in the lower panel meso and MGO both. So from this explained variance plot, we see that meso explain much more variance, that spatial extent is also much more northward compared to MGO. So these are the conclusion that active days mainly occur during mesophase 2 to 5 and break days during mesophase 6 to 8, whereas the active days frequency is high during MGO phase 3 to 6 and break days frequency is high during MGO phase 6 to 8 and 1. And Hofmuller plot of unfiltered rainfall for meso and MGOs both show northward propagation. However, the signal is strong for meso compared to MGO. And the spatial extent and percentage variance explained by meso reconstructed rainfall with respect to 20 to 90 days filtered rainfall is much more compared to MGO reconstructed rainfall. These are the studies I have referred. Thank you for your kind attention.
Thank you, Mr. Abhijit De. So it's very interesting to know that how MGO and meso is impacting the intraseasonal. And you are finding meso is much better explains
yes
the intraseasonal than the MGO. Thank you very much. So we had all the 6 presentation from our young scientists and 3 presentation from visiting invited lectures. All were within time and very interesting. So because of lack of time, we could not discuss more on that. However, I thank all of those lecturers who came on invitation and presented their lectures, and all the young scientists. Dr. Jnanashilan, anything you want to add?
Yeah, so I thank all the speakers. So and mainly for keeping time. And we had an interesting session covering many topics, that MIS and then the numerical weather prediction schemes, validation, and the last two were mostly on the GFS and the MJO cycle GFS. So they are very interesting. They are new works. So good. So good session. Yeah. Thank all the speakers.
Thank you.
Yeah. Over to
Organized.
Yeah. Madhu. Yeah. Madhu is there. Sagadat is there. Hello. Anyway, thank you, Dr. Pai. So I think people have left. So
yeah, no problem. We will thank each other. It's a fine. So we can have for tomorrow. We will again starting at what time?
It will start at 9:30.
9:30. So we will see all of us again, all of you again at 9:30 tomorrow. Yeah. Thank you.
Thank you. Thank you all. Thank you all for watching. Okay.
Yeah. Good day, everyone.